morning, ladies and gentlemen, dear colleagues. Welcome from Busan, the wonderful city at the ocean in South Korea. Our conference today, the IBS conference on high-resolution Earth system modeling, is dedicated to understanding, to presenting some recent highlights in Earth system modeling. In particular, we will focus on the new doors that we can open for science by going to a much higher resolution. My name is Axel Timmermann, and I'm the director of the IBS Center for Climate Physics here in Busan at Busan National University. And the center was founded in 2017. And on behalf of all our members, team members, and the organization committee, I would like to welcome you to this conference, which is dedicated to high-resolution Earth system modeling. Our center right now has about 42 members, including staff, scientists, PhD students, and 3 professors. Before I talk about the challenges and opportunities in Earth system modeling, I would like to just give a brief introduction into what we do here at Busan National University in the ICCP, the IBS Center for Climate Physics. So our mission is to enhance the understanding of natural climate variability and man-made climate change, and to improve the ability to predict climate impacts on the hydrological cycle, ice sheets, sea level, and regional processes. So our center provides basic scientific knowledge on the evolution of the climate system and its potential economic impacts. Much in our center is dedicated to simulating the climate system, but we also pursue theoretical approaches and observational approaches. Recently, we completed a state-of-the-art isotope laboratory for reconstructing past climate changes on the Korean peninsula. The workhorse for our high-resolution climate model simulations and for our simulation efforts is a computer that we purchased in 2019 together with the IBS headquarters. The computer's name is Aleph, and it has 3 main components. The main component is, of course, the compute nodes, and we have 468 compute nodes, each of them having 40 cores with 192 gigabytes. We also have data analysis nodes with higher memory. Also, we have a storage system, a parallel file system with about 8.5 petabytes, and a tape archive system that is able to store 43 petabytes of data, which is very useful for these high-resolution model simulations. The Aleph computer is Korea's second fastest academic computer right now, and in 2018 it was also in the top 500 list of the world's fastest computers. So with these facilities, we are now able to conduct cutting-edge research, and we have 3 main thrusts right now. One of them, and that's what also this conference is dedicated to, is of course high-resolution model simulations. And for this purpose, we used the CESM, the NCAR CESM 1.2.2 version at a 1/4 degree resolution in the atmosphere, at a 10th degree resolution in the ocean, and we are able on this machine to run about 3 years per day. That's the simulated years per day as YPD. And in total, over the last 2 years, we ran about 500 model years under this high resolution. And it's a fully coupled model. Then currently, we are having a joint collaboration with the NCAR CSM team to conduct a 100-member large ensemble with the CSM2 model. It has a 1 degree resolution in the atmosphere, 1 degree resolution in the ocean, and we are able to do about 30 years per day. And in total, we have already conducted 12,500 model year simulations. And last but not least, we are also embarking on transient climate model simulations. In particular, here we use a coarse resolution version of the CSM, and it is fully coupled to an ice sheet model, the Penn State ice sheet model, and that allows us to do essentially glacial, interglacial transient simulations where also the ice sheet builds up, the sea level goes down, and so on. So in this particular model configuration, we can run even 400 years per day. That's pretty good performance for coarse resolution models. Okay, let's start to talk a little bit about the challenges and opportunities here for Earth system modeling. I would like to touch on resolution and realism, that interesting kind of pair of important aspects that we want to resolve. Simulating and understanding, on the one hand, of course, we want to create very high resolution simulations. On the other hand, we need to be able to understand them. And understanding the dynamics means also simplification. So again, we are creating enormous data sets. How do we actually make sense of the complexity of these data sets? I will also talk about my own experience with statistics versus visualization. I found that visualization in these high-resolution model simulations sometimes gives us enormous insights, much more so than just the statistics. I will briefly discuss some new frontiers and mention some challenges ahead for our research discipline. Okay, what you see here is animation of ocean currents from our present-day simulations with this high-resolution model. And what you can see immediately is there is a large diversity of scales that we can resolve. We see the main Kuroshio current, we see the large meanders, we see large fluctuations, daily or synoptic fluctuations in ocean currents. We even saw some variability, I will run it once more, some variability that's driven by very fast tropical cyclones that also spin up ocean current anomalies. So this all looks amazing. We seem to be able to resolve a large number of scales here. However, it means resolving the small-scale processes does not necessarily mean that everything will come out realistically. And that brings this next challenge that we need to also tune and optimize these large models with high resolution, which requires a lot of computing time, of course. Okay, so the next little animation is for the atmosphere. And what we're seeing is the cloudiness, or actually it's the outgoing long-wave radiation simulated by our model. And we're seeing essentially also all these beautiful convective systems in the tropics. We see the extratropical storms. Every once in a while there is a tropical cyclone running through. So this all looks really realistic if you compare the qualitative structures with the satellite data. However, again, even though we seem to be able to resolve a lot of relevant scales now in the atmosphere, this goes the wrong direction, it does not necessarily imply that we simulate everything realistically. And this is illustrated here. We see in the top panel the observed annual mean precipitation, and in the bottom we see the model simulated annual precipitation. And there clearly we can see that the overall structure of the intertropical convergence zone and also the South Pacific convergence zone seems to be relatively well resolved, but it's far too strong. So again, the same story, high resolution, even though we can resolve important processes, does not necessarily translate into more realism. This is another illustration. We are seeing here in white colors the water vapor in the atmosphere, and in blue we see the winds, blue and red we see the wind speed. And clearly you see the tropical cyclones that move in summertime towards Japan and Korean Peninsula. And some of them even have a little eye in the center. So it looks actually quite realistic, and also the statistics seems to come out quite well. However, then if we look at the number of tropical cyclones, the climatology, for example, in the Indian Ocean, in an area where the sea surface temperature bias is relatively small, we see that in comparison with the satellite data, we see a really good match between our model simulation and the observations. However, then in the Atlantic, where on average we have a relatively strong negative sea surface temperature bias, we see also that the tropical cyclones are severely underestimated as compared to the observations, the IBTRAX data here in black. So resolution and realism, of course, we would like to go to more and more higher resolution models and capture more and more of the important processes. In particular, when we increase the horizontal resolution, we are then able to resolve important topographic features, coastal processes. Coastal ocean currents are being resolved much more realistically, and we will have later on a presentation by Boris de Witt about the Peru upwelling region. Frontal systems, Niklas Schneider will talk later about the dynamics in frontal systems, atmosphere-ocean interactions. Extreme events, Kyung-Ja Ha will talk later about extreme events, how well are they resolved in these high-resolution models, and also new dynamics can be resolved. Furthermore, we can also increase the vertical resolution, and in particular, oceanographers are very keen on this, in particular because you can start to resolve the interaction with topographic features much more realistic. Also mixing instabilities, vertically propagating waves, and stratification become much better resolved. Also for the atmosphere, going to the higher stratosphere with high resolution also will allow us to resolve the quasi-biennial oscillation, for example. Then we also have to make the choice, are we going to use a hydrostatic model or are we going to use a non-hydrostatic model, which will allow us to resolve convective systems. In the ocean, non-hydrostatic models will improve the representation of water mass transformation. But one key issue also to consider here is we also need to make sure that the model scales well, so all the increases in resolution need to be manageable on a supercomputer system. And also we need to make sure that the main properties, energy and mass conservation and so on, are all fulfilled. Okay, so here is the other question. On the one hand, we want to simulate all these processes realistically. We will generate a huge amount of data. On the other hand, we would like to understand what's going on in our climate model. So simulation is essentially making it more complex. Understanding means we are trying to make it simpler. And in this graphic, we have on the x-axis the number of components for different types of Earth system models. On the y-axis, we have the resolution, and it's very schematic. On the lower left, you see the conceptual atmosphere-ocean models, statistical models, stochastic models, relatively simple forms, and very often our understanding projects back onto this model category. Conceptual Earth system models, similar to the ones that Barry Salzman introduced about 20 years ago. Then we have the intermediate complexity atmosphere-ocean models, which were very popular at some point in the El Nino community. And then since the 1990s, also Earth system models of intermediate complexity have become very popular tools, in particular for paleoclimate modeling, because you can run them for a long time. Then nowadays we have the typical Earth system models, CMIP5, CMIP6, and beyond that we have the high resolution models, so the next level essentially of resolution. But the question is also, if we go to more and more, if we can resolve more and more of these high resolution processes, what about the climate sensitivity? Is it going to stay the same? So this is an interesting research question. The more of these processes, mixing processes, for example, resolved, is this really going to change our projection of future climate change? It's an open question that I hope we can also discuss during this meeting. Okay, making sense of complexities, essentially the question. So on the one hand, of course, we use these high-resolution models to make better predictions or projections. On the other hand, we can use them also for sensitivity experiments to test hypotheses. So this is essentially a way for learning, for probing the system and its sensitivity. Then, much of what we do is essentially statistical analysis. We look at this enormous output, we try to determine essentially what's going on, what are the main statistical properties, how do they change with future climate change, for example. And essentially the toolbox that we have in hand is mostly a toolbox of linear models that we apply. However, when we start to resolve these fine scales, we are getting actually into this regime where we should be looking also at time scale and spatial scale interactions, which requires also the understanding of nonlinear models. So that is something that I would like to advocate also during this meeting, that our community should embark much more on, engage much more with the climate dynamical systems community that has developed tools to better understand actually scale interactions. Okay, so making sense of climate complexity, this is essentially an invitation to all of us to think a little bit more about complexity science. And there is a big community out there, in particular the dynamical systems analysis community. They have introduced some wonderful concepts that in some point can also be applied in our framework. Of course, the non-normal operators, synchronization, phase synchronization is an important concept. Chaos theory is of course something that embeds already the concept of nonlinearity. We have bifurcation theory, tipping points, I don't like the word, but it's part of this bifurcation theory framework. We have unstable periodic orbits, mixed mode oscillation. So there is a wide, well-developed language to describe complex dynamics, complex phenomena in this community. Also, there are other communities, for example, that look at self-organization, self-organized criticality. Could be interesting for convective systems, could be interesting also for ice sheets. The maximum entropy principle has been successfully applied, for example, for vegetation models. So these are all ideas that we can try to infuse also in our analysis of high-resolution model output. Stochastic dynamics, and we have nonlinear statistics. Nowadays, of course, machine learning, artificial intelligence is one of the keywords, a tool that is very successful in predicting certain patterns and events. Extreme value statistics, very descriptive, but also very relevant way of characterizing dynamics. And we have scaling and fractals. So this tree is not even complete, but I just wanted to highlight here that this is a world of mathematics, dynamical systems analysis that we have not yet fully tapped into, but that might be very relevant for future analysis. Okay, now my little comment here on statistics versus visualization. So on the upper left, we see the simulated changes from our model simulations of tropical cyclone density for a CO2 doubling. And this is, of course, an aggregated statistical quantity that we're looking at. On the other hand, you can look at animations of these tropical cyclones and how they interact with the oceans. So in the background, you see the ocean sea surface temperature. On top, you see the tropical cyclone wind speed. And in principle, by just looking at individual events, that's what I learned from this experience, we can learn a lot about the dynamics. So it's not only that we take the output and we put it into our famous statistical tools, but that we should really look at the individual events and go into details. Here is another example, the power of visualization. What you see is, of course, the sea ice around Antarctica, and if you just do statistics, you may miss some interesting features. There is a Weddell Sea polynya, There are coastal leads that open up regularly when the wind blows in a certain direction. We even have little sea ice eddies on certain areas, and we also have sea ice wakes when there are islands in the way. So these are all interesting features that come out in these visualizations. If we just took the mean sea ice concentration or the variance, we would be missing this interesting dynamics. So my pledge here is essentially, please simulate, I think I pressed the wrong button, please simulate and animate. So the new frontiers that we have in front of us include essentially building up the dynamics on the dynamics of Earth system model components on longer time scales. And that includes in particular ice sheets and also the carbon cycle. Another new frontier is of course the resolution of convective systems. So cloud resolving models are possible now. Still, we have not been able to conduct cloud resolving transient global climate model projections yet fully coupled, but this is also something that will happen, I guess, in the next couple of years. Then also there is an interesting question about fires in the climate system. Small-scale fires can actually have a large influence on aerosol loading and even CO2. So we have an interesting feedback here that operates on a very small scale. So resolving these fires on a smaller scale and their impact on the climate system may actually be really important frontier to further engage in. Then high-resolution data assimilation and the IHASP collaboration between NCAR and the Qingdao lab. They are developing now high-resolution data assimilation capabilities. That's also really cutting-edge science that is extremely interesting to follow. Then other frontiers include, of course, what happens if suddenly we can resolve mesoscale features or sub-mesoscale features in ecosystems. Is this going to change our view? Is this going to change the sensitivity of ecosystems to future climate change if we resolve also these small scales? There are other efforts right now, for example, Caltech, Tapio Schneider's group, and at the ECMWF, the Extreme Earth Consortium. They are really trying to build that next generation of Earth system models with many more components included, high resolution, and also infusing essentially observational data through AI. Another interesting frontier would be nowadays, of course, the human component is pretty much prescribed by parameterizing urbanization, emissions, and so on. But we could think of a much more dynamic human component in our Earth system models, which could be accomplished by implementing agent-based modeling, for example. And again, the subject that I mentioned earlier on, it's important really to bridge the physics and the dynamics, and that's really something that the climate research community has not really fully embraced, that possibility that dynamical systems analysis can give deeper insights actually into dynamical processes. Okay, so with these new opportunities, of course, we also have interesting challenges ahead. So one of them I mentioned already. Even though we can resolve these fine scales now, it does not mean that everything will come out realistically. So in principle, we have to go back and retune and recalibrate these high-resolution models. And that is a lot of computing time. So also, it's much more complicated because now changes in the mean state, biases, they can also affect the variability, but also the variability will feed back on the biases. So this is actually the tricky game right now. How do we have a strategy already to tune these high-resolution coupled models? I mentioned the including carbon cycle and ice sheets is important to understand climate carbon feedbacks, but also sea level rise in principle. And this requires also that we implement shelf processes, circulations, ocean circulations underneath ice shelves. But in principle, including these ice sheet components means we have to have extremely long spin-up times. So we need to think also about acceleration methods. Then diagnostic methods. We have this enormous data set. What are we going to do with this? Okay, we can plot our typical global mean temperature and some El Nino indices and so on, so do the type of standard statistics, or we can go to the next level and try to understand a little more about scale interactions in the system. Do we have really the language available to describe these scale interactions? And that's, again, my invitation to all of you to embark in maybe collaborations with experts in the respective fields. Okay, data storage is perhaps one of the biggest technical issues. So we have the I/O bottleneck. So when we run these high-resolution models, the computer is not necessarily the problem, but the input-output frequency, the bandwidth is becoming the main bottleneck for these high-resolution model simulations. Again, we would like to share the data with the community. What are we going to do? What are the best ways of allowing access to these large models? And also there, we should think about good strategies in future, whether we use OpenDAP or LAS type of servers, where essentially data can be shared online with a wider community. Okay, so that concludes a little bit my brief introduction into some of the opportunities and challenges of high-resolution modeling. I would like to quickly introduce our conference. So we have several sessions. We have atmosphere session coming up next, ocean session, sea ice. We have a regional processes section, extreme events across scales, climate statistics, and then on the 14th, on Wednesday, we also have a high-resolution workshop, which is going to be via Zoom, completely online. And this essentially includes 2 tutorials, one for ParaView, a wonderful animation software, and one for CDO and NCO tools. Again, I would like to encourage you for the next sessions to become very active in submitting questions through the process that we outlined in our previous emails to you. It's essentially very simple. You go to your web browser, you access slido.com, you type in the code HESM 2020, and then you join the event. And while the speaker is talking, we would like to ask you to submit your questions, not only at the very end, because I will see these questions on the screen. I will select 3 to 5 of these questions, and they will be shown then eventually to the speaker, and the speaker has time to address those. So please, in this regard, get very active. I know it's kind of tempting if it's an online conference to shy a little bit away, but we really would like to engage you to participate through asking lots of questions. If there are any other questions or technical issues, please don't hesitate to ask our staff. You have all the email addresses. And with this, I think we can start with the first session. So the first session is the atmosphere session, and I would like to see the speakers. Okay, great to see you all. I see Shangping Xie, Justin Small, Masaki Sato-san, and Niklas Schneider. Welcome all, thank you for joining, and our other speaker is Dr. Jongin Chu. Let me just make a very quick introduction. Shangping Xie, our next speaker, is the Revell Chair at the Scripps Institution of Oceanography in San Diego. And Justin Small is a project scientist at National Center for Atmospheric Research. in Boulder, one of the pioneers of fully coupled high-resolution Earth system modeling, and Masaki Sato-san, from a professor from Atmosphere Ocean Research Institute, University of Tokyo, is one of the also pioneers in high-resolution model. It's a great pleasure having you. And Niklas Schneider from the University of Hawaii, director of the International Pacific Research Center. Welcome to the four of you, and Dr. Jongin Chu. She's a researcher and project leader here at the IBS Center for Climate Physics. With this, I think we can start the session. I would recommend that all the speakers turn off their YouTube if you watch YouTube. Otherwise, you may have some feedbacks. So, Shangping, we are looking forward to your presentation.
Okay, so I need to share the screen. Yeah, somehow the screen sharing is not enabled yet.
Can you enable slide sharing, please? It's enabled now. Could you give it a try?
Okay, I can try. Host disabled participant screen sharing. Not.
Still disabled. So they're working on it.
Yeah.
Just give us a sec.
Yeah. No problem.
How's the weather in San Diego?
Oh, it's pretty nice. It's pretty nice. Okay, I just going. Maybe I just share the slideshow, right?
Okay, now
Instead
we
of
can see something.
Yeah, just share the slide. So I guess is that better? I don't know.
Yeah.
Maybe
We can see your
do you
screen
see
now.
the? Oh, okay. Do you see the full screen?
Yes.
I guess you see, right? Oh, you are seeing like what are you seeing? You are seeing the
presenter.
Presenter view. Okay, swap.
Yeah. Perfect.
Okay, now it's showing the slideshow view. Okay, good. So this is fine, right? Yeah. Okay.
Please go ahead.
So thank you, Axel. Really pleased to join the workshop you organized. I think this is an exciting time, as Axel highlighted, in using high-resolution ocean atmospheric coupled modeling to understand the Earth system and ocean atmosphere system in particular. I guess when Axel asked me to give a talk, honestly, I was a little hesitant just because I haven't been doing a lot of high-res, at least the cutting edge high-resolution modeling much these days. But I thought maybe I can offer an angle. You know, I like to think myself not to be very old, but but maybe I'm a little old. So I thought, you know, maybe following the wisdom or the saying, you know, knowing the past sometimes helps us see the future better. So I offer to share some personal experiences in terms of analyzing high-resolution satellite observations and some of the high-resolution ocean atmospheric simulations. So I think this is, in this sense, this might be quite complementary to Axel's talk, but maybe from a slightly different and more personal perspective. So I like to kind of, at least for young people, you can have a sense, you know, when why people people were doing this kind of work. And some are well known and some are not that well known. Okay, so I guess in the 1990s, there was something really revolutionary that was happening. In other words, satellite observations, see visible channel or infrared channel are kind of limited by the presence of clouds. But in the 90s, several microwave sensors were flown to satellite orbit. They have not super high resolution compared to visible, but at the resolution about half degree or so. In terms of measuring ocean surface, sea surface height, for example, and then measuring the vector wind over ocean, and then even measuring the sea surface temperature and rainfall. And another thing is, just from 1997, people even loaded precipitation radar on satellite, so that allows more direct measurements of rainfall. In the case of the trim satellite, limited to tropics, and now the GPM expanded to almost global. So it was kind of that was an exciting opportunity. I think now these sensors, especially, these sensors are kind of well known and widely applied. But in the 90s, late 90s and early 2000s, these are really the cutting edge data sets. and then at the same time, I was really fortunate to be at IPRC to have the opportunity to collaborate with our Japanese colleagues. And they have the world's fastest machine computer at the time, Earth simulator. So I guess I'm sure Masaki Sato is going to highlight great achievements by developing the global cloud system resolving model NICAM. So I will yield that part to him, but I would like to briefly kind of highlight a revolutionary simulation done by our Japanese colleague called OFAS, Ocean GCM for Earth Simulator. So that was the first multi-decadal hindcast forced by atmospheric variability at the resolution of 1/10th degree. So basically a global eddy resolving model, ocean hindcast. So I'm just going to give a few examples. Hopefully I can go through the slides, but if not, I can stop anytime. Anyway, so this is a slide I think I used in about 15 years ago. So I was arguing the global climate model at the time had the resolution of hundreds of kilometers, but the satellite observations were one order magnitude finer in scale. So I was arguing, the cutting edge high resolution models could help us to bridge the existing computing the global model simulation versus the global scale satellite observations. So again, I guess that Axel mentioned, that enabled us to study ocean atmosphere interaction on the frontal or eddy scale, as Nicholas Schneider is going to give a more detailed discussion, and some orography effect in ocean and atmosphere. So I just want to kind of briefly introduce my very first satellite study. I was, when I was young, I was more kind of theoretically motivated, right? But I was asked to join a satellite research program, and had to do something using satellite. So at that time, I just thought, the EIS, the European remote sensing satellite, carried spectrometers, and I heard, I think maybe PM Yale and the University of Washington, Stan Hayes and Mike Wallace, they'll find some covariability of the surface winds with oceanic waves called the tropical instability waves. So sure enough, when I kind of superimpose, plotted the Hofmann diagram at 3° north across the Pacific Ocean, so that's where we see the largest variability of TIWs in sea surface temperature anyway. And then when we did the divergence calculation from the EIS satellite vector wind, you can see kind of a very pronounced, beautiful co-propagation in the winds. And this was later explained when you have a sharp front. In this case, this would be a meridional cross section, and SST has a front at 3° north, and then the atmospheric adjustment is over much larger scale. So you would generate unstable stratification on the warmer side, and the stable stratification on the colder side of the front, and that's going to destabilize and stabilize the wind profile and causing intensified winds when the winds across the front. And that was kind of a beautifully illustrated by Dolly Charlton's paper in 2001, using a much better satellite called the QuickScat. So you can see kind of a strong, the waves, the more kind of a visually and also associated with the associated wind divergence. So this is all, I believe Nicholas is going to give a much more in-depth and beautiful explanation and description of what happened there. Yeah, maybe I'll just skip this. It's just too much to talk about. And then when I guess Justin Small was also a colleague at the International Pacific Research Center, we were analyzing the co-variability of surface winds and sea surface temperature. And somehow I don't remember the detail, but I just remember when we plotted the correlation between the high pass SST and wind speed. This is something quite dramatic. In other words, almost everywhere you see like a positive correlation between the wind SST on the shorter scale. I believe we filtered by something like 1,000 kilometer in zonal scale to retain the high wave number variability. And then and along the mean strong ocean fronts, like the equatorial fronts and the coastal extension, Southern Ocean, and so on, you see like the correlation is extremely high. And this is kind of exciting in the sense that this cannot, the prevailing theory for extratropical LC interaction is the atmosphere driving the ocean, but this cannot be the case. This actually implies the ocean must be driving the atmospheric variability. And then I guess, maybe the first NCAR attempt to couple eddy resolving ocean with a reasonably high resolution atmosphere, as presented by Frank Bryan's paper in Journal Time 2010, largely reproduced this kind of enhanced positive correlation along the major oceanic fronts. So that, again, this is something, I just thought, we were, just reflecting back at about 15 years ago, I guess we tried to make a case that at least in certain circumstances, ocean does affect the atmosphere. So this is a kind of a kind of a result of our effort to show that. And then these days, I guess it gets quite quite a bit of attention. I think Hilde Sale and Larry O'Neill, they organized this LC mesoscale LC interaction working group as part of the US Carbon. So I look forward to their discussion and reviews and other activities. Okay, so I would like to switch gear to talk a little bit about the first global eddy-resolving multi-decadal timecast driven by atmospheric reanalysis. And ultimately, we actually used quick-scale high-resolution WINT also. So this is one of our workshop. Like I said, here the key person is this person, right? Hideharu Sasaki. He basically single-handed set up the model and everything. And he was really kind of a friendly and collaborative. So he did a lot of work, try to giving the huge, tremendous amount of data. I remember our IPRC programmers, they go to Japan carrying suitcases because that seemed to be most efficient, safe way to carry the hard disks that store Hideharu's OFAS simulation. So that's what we did at that time. So anyway, so this is just tremendous success, with a great interest. And I'm just going to show maybe one quick example. Just, ocean mixed layer is hugely important for various reasons. So if you go to look at the low resolution ocean simulation, you're going to see the mixed layer looks terrible compared to observations. This is Japan cross shell extension, right? So cross shell extension features the shallowest some mixed layer, whereas in model it's the opposite. But when in Hideharu's simulation, when you go high resolution, you kind of get slightly better, but not exactly the same as that. And then you have like a jet structure and eddies and so on. So there's a lot of things that we analyze. And one analysis, a methodology we developed, I thought was pretty nice, is to compare, in this case, in the monsoon region of Bay of Bengal, we compared the subseasonal ocean surface height variability between the altimetry observation and Hideharu's run with a quick-scale variable winds. So I guess the shading is just a standard deviation. I think you see that the eddy activity looks pretty realistic. And then Hideharu had another run where he kept atmospheric forcing to be a monthly countology. So the winds are not variable from one year to another. And then you kind of see it recreates this part of variance, but not the variance along the coast. And then we went even further, by correlating the quick-scale force OFAS with observed altimetry variability. And you can kind of see in the tropics, you actually in the equatorial waveguide, you see high correlation, and then on the coast, you see kind of a high correlation. That means the high correlation indicates the subseasonal variability is largely driven by observed winds, right? The realistic wind variability. And then there are a bunch of other things we kind of analyze. Maybe I don't really have time to go into all this, but I thought one major kind of surprising finding is all the equatorial waves in response to Melvin-Julian oscillation in the equatorial ocean. It's kind of an interesting but not terribly surprising. But I thought that one surprising thing is we kind of I don't know if we are the first, but we kind of noticed there are kind of eddy shedding events from the delta of Myanmar. So this delta of Myanmar here, and you kind of can see even the phase is kind of a this eddy phase of eddy is closely related to the coastal carbon wave generated by Melon-Joint oscillation. And then we turn to the quick-scat OFAS, right? So you kind of see this is really remarkable. It's kind of a well simulated, both in terms of the track of eddy and even the phase of eddy looks pretty good. And then Xu Hua and Jay McCurry, they wrote a nice paper in 2018 illustrating these are the wave kind of radiation plus nonlinear organization. So I don't know much of detail, but I just saw the paper. I thought this is a very nice paper. Okay, so lastly, really quickly, to echo what Axel has touched upon a little bit. So this is a elevation map of South Asia and East Asia, so Tibetan Plateau and Western Ghats of India and this Myanmar mountain, and then the coastal range of Vietnam, and then mountains on the Luzon Island and Taiwan. So in summary, at least you have prevailing winds from the west, right? So you might expect to see kind of a mountain anchored convective organization, right? So this is indeed what we find when we turn to the revolutionary precipitation radar observations for JJA. So rainfall month, right? So you kind of see this Western Ghats rain band and this Myanmar coastal rain band, and then the rain band trapped by the mountain on Vietnam and on the Philippines. So what and also the rain band active convection on the southern slope of the Himalaya mountains. So what is still puzzling and remarkable is those orographic rain bands, at least on the east coast of Bay of Bengal and off the coast of India. The maximum rainfall is not even on the coast, certainly not on the slope of mountains. Rather, they are displaced upstream in the open ocean. So I still don't know why this happens, but anyway, for all the details aside, it just illustrates, the rainfall distribution, especially over the continents, over the land, is largely determined by mountain ranges, and certainly by the mountain ranges play a role in kind of a geographically fixing the convective activity. So I skip all the stuff, and then you might think, right? So if you go, so that we did it like in 2004 or 5-ish, and then we looked into this AFAS atmospheric model for Earth simulator around the same time, and then JJA, right, rainfall, and the Western Ghats was good, but Bay of Bengal terrible. And South China Sea terrible, because if it's a chicken egg problem, right? So the winds in the Bay of Bengal, instead of westerly, it becomes southerly, right? So the winds fail to impinge on the coastal mountain range here, and it fail to impinge on the mountain range, Luzon Islands or Philippine Islands in general. So I would say, the atmospheric high resolution model seems to be rather trickier, just because there's a lot of physics involved, radiation, convection, clouds, right? So this is just an example. When you raise resolution, it doesn't necessarily give you better results. And then another example is, I think maybe Masaki is going to talk about this a bit more. So there's a global class system resolving model 14 kilometer, very high resolution when you compare to the observation. Yeah, it's pretty good compared to the previous results, but you can see a couple of different things. And another important thing is, in order to get this result, they have to couple the AMIP, in other words, the prescribing SST is not going to cut it. So they have to couple with the SLAB model and restore the SLAB SST to observe the SST. So there is some thing that is not well understood in terms of energy fluxes between continents and ocean. So I'm skipping everything and I'm just saying, high resolution modeling for ocean, it looks like the resolution almost immediately leads to certain improvements. But atmospheric simulations seem to be trickier for the reasons I've discussed. And then, I think that the field is wide open in terms of how the couple systems can work and in terms of climate change. So that leads to something I would call, it's a competition or maybe a call for young talents, right? So I guess in an avenue for modeling, coding and developing physics, there's a wide avenue for modeling, and also there's a wide avenue for diagnostic in terms of making sense of the simulations, right? So as somebody who has been around for a while, so I would echo, usually when you have new tools, new methods, new instruments, new data, usually you will lead to discovery of a new phenomena, discovery of new insights, new connection, new applications. So I think here there's a big avenue wide open for young talents. I'm just going to stop here. Yeah.
Thanks.
So sorry, it's a fast walkthrough.
Thank you very much, Xiangping. So there are about 40 people in the audience currently clapping. So you can't see them, but they're in the back.
Yeah, sure.
That was a wonderful introduction and also a historical perspective on high-resolution modeling. Thank you very much. We have one question actually that came through on Slido by Professor Kyung-Ja Ha. So the question is essentially what kind of resolution is needed for Asian summer monsoon studies when you want to resolve the strong convective systems?
I think Masaki probably is a better person to answer this, but I feel, I guess they argue like a 10-kilometer resolution is, based on their experience. So I think that might be true, but on the other hand, I think it's more than a resolution issue. If another thing is if you want to predict or simulate heavy rainfall events. In Asia, we know, like in summer, there are orographic blockage of atmospheric moist water vapor transport, right? So that in that case, it's very important. And also, the cost resolution models, they tend to locate rainfall distribution not quite well. So maybe by resolving those models of mountains, you have a kind of physical reference, right, for where the mountains are, that we cannot change. So that might be a pathway to anchor the large-scale convection. So I still think for summer convective system, monsoon included, it's still the fundamental lack of insufficient understanding of physical and dynamics interaction. Convection versus large-scale circulation.
I have one short question actually, but maybe more asking for your past to future statement that you mentioned earlier on, so that we can learn from the past to something about the future. So with all these new scales being resolved, do you expect any surprises in terms of climate sensitivity?
Oh, okay. So that's I think there's certain people who expect, hoping that's the case, just because Masaki's cloud system resolving, the cloud refers to deep convective clouds. So these have a intrinsic scale of 10 kilometers, whereas the shallow clouds, uh, they are really the type of clouds that hold the key to climate sensitivity. So the shallow clouds require a lot more resolution just because they are shallow in vertical scale by order of magnitude. But yeah. So I guess if you want to use the brute force to resolving those shallow clouds, then you have to go one order of magnitude higher resolution. I hope that's not the only pathway.
And we have time for one more quick question from Professor Jeannie Lee. Is there any seasonality in the SST wind stress relationship for small-scale disturbances?
Yeah, there is. So usually local winter features a stronger SST gradient meridionally. So that's the time you can see a larger SST mesoscale variability and therefore larger atmospheric variability as well. So I don't know, I know Nicholas has much better idea on those issues. Yeah.
Okay. With that, actually, we switch over to Niklas Schneider. Thank you again very much,
Yeah, thanks.
Xiangping,
Yeah.
for your presentation. Okay, Niklas, are you there?
Yes, I'm here. Can you hear me?
Yeah, we hear you and we see you well.
Okay,
yes.
Let's see whether I can share my screen. Let me put this on. Now which one do I want to share?
Looks like you also have some nice weather there in Hawaii.
It's okay. You can take a peek.
Understatement.
Okay. Let's see if we share this. Can you see my slide or do you see my presenter's notes?
No, your slide.
Okay, good. Well, thank you very much for this opportunity to speak to you on these issues of the scale interaction or the scale and Rossby number dependence between wind responses and the ocean mesoscale sea surface temperatures. Again, I'd like to thank IBS Center of Climate Physics and Axel Timmermann for this opportunity to speak to you. This is a topic that has been occupied me for quite a while since I was inspired by Xiangping Xie when he was at the IPRC showing me this sort of work. I will present to you an observational study that takes advantage of some of the microwave instruments that are flown on satellites that have shown the strong covariability of the sea surface temperature at the ocean mesoscale and the atmospheric wind speeds. And that's shown here in this figure. That is a figure, again, from QuickSCAT, equivalent neutral winds. So this is basically wind observations from QuickSCAT and AMSR sea surface temperatures. The winds are shown in the color with the scale on the side here, the wind speeds. And the contours are mesoscale sea surface temperatures. All of them have been bandpass filtered to focus on the ocean mesoscale. And what you see is this very strong covariability that Xiangping Xie already alluded to between the sea surface temperature and the winds. Where the sea surface temperature is warm, you have an increase in wind speeds. Where sea surface temperatures are cool, you have a decrease in wind speeds. So this is a well-known observation, has been over a decade of studies exploring this. And so basically what I would like to show you that relationship actually includes lags and is dependent on the scale and on the Rossby number. The framework I'm applying here is all linear. So the idea is that this provides a way of thinking about this and that we may use in the future to then explore some of the scale interactions of this imprint of the ocean mesoscale on the boundary layer winds, and then explore further how that might influence the storm tracks and some of the highly nonlinear interactions in the atmosphere. Okay, so this relationship between the sea surface temperatures and the winds that I'm showing here is typically characterized by a regression. Let's see how this goes forward. Here we go. So where we say, okay, we have the observations of the winds from the scatterometer and the observation of sea surface temperature from a radiometer. And they are co-located. Regression coefficient is sought, and that's typically called a coupling coefficient. And this is from a paper by Larry O'Neill, showing here for the Agulhas region very nicely this very tight correlation that you find between the perturbation sea surface temperatures and the perturbation equivalent neutral winds or wind speeds. So a very nice correlation. However, there are a number of reasons why you might expect that it's not just a co-located relationship between the winds and the sea surface temperature, but there should be some lags. There has been numerical studies by Justin Small, again by Larry O'Neill, by Michael Spall, that based on the advective properties or advective components in the heat budgets and the momentum budgets, we expect a lag response. So a response between the winds and the sea surface temperatures that is not co-located, but is lagged. Furthermore, there are studies again from atmospheric, high resolution atmospheric model studies that show that the surface winds are sensitivity also to the large scale winds and their direction relative to the sea surface temperature features. And so what that suggests is that this simple co-location between the winds and the sea surface temperature is not sufficient, but we have to extend that and at the minimum allow for lags. And one way to do that is to say, again, we take the same observations of winds and the same observation of sea surface temperature, but now look at the relationship that includes lags between the position of the winds and the positions of sea surface temperatures. And then formally, this becomes a response that's not just a local regression, but it becomes a response with an impulse response function or a Green's function approach, where this A is the impulse response function takes the role of the coupling coefficient, but again, allows lags. Once we allow lags, we also have to be a little careful in the direction of the lags. Which direction of the lags are we interested in? And that depends on the large scale winds, both the directions of the large scale winds and the wind speeds. So this is the approach that we'll take and explore, basically try to determine this impulse response function from the observations of quick start winds and AMSIE sea surface temperatures. Just to hark back for 1 second in the coupling coefficients, you see the coupling coefficients is a special case of this impulse response function, namely if this impulse response function is simply a delta function, only non-zero components right at the origin, then this formulation simply collapses back to the coupling coefficient approach that I showed you previously. So we're simply doing a coupling coefficients, but we're allowing for lags. And we'll do that again from Quickscat and AMSIE sea surface temperature observations. The study region is Agulhas return current, just to the south and to the east of the tip of South Africa. The data is from 2003 to 2008, and we're using daily values, daily averages, because everything depends on the large scale winds, and the large scale winds are modulated there by the storm track, by the synoptic atmospheric variability. So we have to resolve this. Now this approach is sort of fitting. It's a fitting approach between the winds and the sea surface temperature. This actually works quite well. At this point, for time reasons, I'm just going to ask you to believe that. If you're interested in this, you can look at the paper that describes the study that was just published last September in the Journal of Atmospheric Sciences. So this approach works pretty well. And the question is now, well, what does this regression coefficient, what does it actually look like? And this is a plot of this regression coefficient. Let me just orient you. This is basically the lag in the direction of the large scale winds on the x-axis. On the y-axis is the lag perpendicular to the large scale winds. So large scale winds blow from left to the right. And we have 4 panels here, which are distinguish the speed of the large scale winds. It's a very weak large scale wind, a stronger large scale wind of 6 meters per second, 11 meters per second, and 16 meters per second. At the origin where the of zero lag is right here where these 2 dotted lines meet. Let's just look at the panels B and C, where we see co-located with the origin a very strong increase in the winds as indicated by the color. of about 0.5 times the unit here. Unit is sort of strange because this is an impulse response function. So that's a wind response for a delta function SST impulse of 1 degree Kelvin that acts over 1 square meter area. So if you want to translate into wind response, you say, okay, let's just make this 1 degree Kelvin temperature anomaly that acts over an area of 100 kilometers by 100 kilometers. Then this pattern would simply give you the response in meters per second. So we see a change that is co-located in change in wind speeds, right, co-located with the SST very nicely, and that's consistent with the coupling coefficients and the previous studies. But we also see a lot of lag responses. See, lag response have a very interesting pattern. If you look at this 6 meter per second wind, strong response here, and then we have a wake in the downwind direction that extends, let's say, 200 kilometers, maybe 250 kilometers away from the sea surface temperatures. This lag is asymmetric, right? On the left side, looking in the downwind direction, large-scale downwind direction, it's weak. On the right side, it's very strong. On the right side, we have an anticyclonic turning of the winds. That's not seen on the left side. And we see dependence on the wind speeds themselves. Strong at 6 meters and 11 meters per second. For the very strong winds, it becomes weaker. For the very weak winds, you see the response is weak, but you see you have a pattern of the winds that goes circular in a clockwise manner around this warm sea surface temperatures here at the origin. So that's simply consistent with an Ekman response to a warm low. So this is basically what we find for the regression coefficients. And what I'm trying to show you next is what does this look like when we apply it to other sea surface temperature patterns, and what are the underlying physics? In particular, what are the physics of this wake? So what this approach that we are using here, the sort of Green's function approach with the impulse response function, what that allows us is to take the observed regression pattern, the observed sea surface temperature pattern, and then estimate the response of the winds to synthetic made-up sea surface temperature patterns, just patterns that we find interesting to elucidate the physics. The sea surface temperature patterns that I will use is simply an undulating front and an SST monopole. So we take the observed regression, the observed impulse response function, and apply to synthetic sea surface temperatures to look at the response and try to understand the physics of this response. So let's do that. And the first pattern that we'll use is an undulating front. This harks back to work by Dr. Shelton, where he introduced this very classic schematic of what the response looks like. So this is a schematic of a sea surface temperature front indicated by this black color. And to the north, above this, the sea surface temperature is cool. Below it, sea surface temperatures are warm. And the basic observations of the co-location of the wind speeds and the sea surface temperature would indicate that over the warm winds, the speeds are higher than over the cold winds. So if you have overall a large-scale wind blowing from the upper left to the lower right, you get lower wind speeds here, high wind speeds here, and you would expect a wind divergence or wind stress divergence when the winds cross the front at right angles, and you get a wind stress curl when the winds go parallel to the front. Now let's see what our reconstruction gives us. So this is that reconstruction to the same sea surface temperature front. So front is here, and it's cold above, and it's warm below. On the left side, I show basically the response in the wind speed, and it shows us expected reduction of the winds on the cold side and increase of the wind speeds on the warm side. This is now we have more information. We don't just do it for one wind component, but we do it for both wind components. So we have wind speeds and wind direction. And we see positive values downwind of that front here, indicating a turning of the winds. And that depends on how the winds across the front. We also see the divergence that we highlighted here, just as expected. When the winds, large-scale winds, blowing again from the upper left to the lower right, when they cross the front, we get large divergence over the front, as expected from Shelton. But we also have divergence that occurs when the winds go parallel to the front. Wind stress curl, again, largest when the winds go parallel to the front, just like expected. But again, there's more action, there's some non-local action. So let's try to understand these other processes. So overall, our wind response recovers the basic features that were put forward by Charlton, but there is more structure to this response, and that's basically what we're trying to understand. Let's look at another response, and again, just try to see whether what we're doing is consistent with observations or observational structures, results that have been put forward in the literature. And we now look at the response, again, the observed impulse response function applied to synthetic sea surface temperature anomaly, and the sea surface temperature anomaly is an SST monopole that's located here. It has an amplitude of 1 degree and has a Gaussian shape away from the origin. And on the top panel here, I show again in the space of a downwind distance versus crosswind distance for large scale winds that blow from left to right at a speed of 11 meters per second. I'm showing here the wind divergence. And as expected for this monopole, we have a wind divergence on the leading edge of the monopole and a convergence on the lagging edge. Now that we can compare with observations. This is a plot from Frenger et al. Study in 2013 that did a composite of the wind divergence based on eddies in the Southern Ocean. So they collected all kinds of eddies and then simply composited the wind divergence, and you see a very similar structure with wind divergence on the leading edge, convergence on the trailing edge of the winds that blow here equally from left to right. The order of magnitude is of the order of 5 times 10 to the minus 5 times 10 to the minus 6. Here our units are 10 to the minus 5, but we have 0.1, let's say 0.5 times 10 to the minus 5. So the same order of magnitude we find here. So it's very consistent. Note, however, this shows us additional information that there is an asymmetry in the divergence. The divergence upstream has a weaker magnitude than the downstream convergence. Let's look at the curl for a minute. Again, there are some other studies which I'm not going to show you that look at the curl. In particular, they look at the Ekman pumping. Ekman pumping is a dipole. Wind stress curl and Ekman pumping is a dipole that straddles the crosswind flanks of that dipole, and again has of the same order as observed in again composite studies by Gaub, but again it has this interesting downstream structure with the positive curl extending in the downstream direction and sort of switching sides from the right flank to the left flank of the wake behind this SST monopole. So let's try to understand these physics that occur there. And for that, we actually look now simply at the winds themselves as we reconstruct them based on the observed impulse response function, or as the observed estimate of this impulse response function applied to this synthetic sea surface temperature anomaly. And so these are the winds. Again, this is very similar to the impulse response function that I showed you before, since that's simply a Gaussian that's shrunk and extended to a delta function. But overall, we see now here the increase in wind speed of about half a meter per second, 40 centimeters a second, right over the warm sea surface temperatures, slight shift downstream. We also see the turning of the wind to the left, which is anticyclonic in the southern hemisphere. And so we have this interesting directional response right over the sea surface temperatures. And we see this downstream wake that we discussed before, where the winds turn anticyclonically on the right side of the wake, and we get a strong response on the right side of the wake. On the left side of the wake, downstream wake, the response is much weaker and even has a zero here, about 150 kilometers downstream of the sea surface temperature anomaly. Now, this is very interesting. This asymmetry is very interesting, and one indication that what the underlying process might be is simply a scale. If we look at this length of this arrow, this is the distance that a particle would travel at a speed of 11 meters per second during half an inertial period at this latitude. Inertial period at this latitude is about 17 hours. So this is the distance air travels in about 8 hours. And you notice that within this half an inertial period, the winds basically reverse direction. So that indicates that the Coriolis turning basically a Lee inertial wave may be an underlying process or is an underlying process, which gives us, basically tells us, again, rotation is important. Secondly, one might hypothesize that we expect downstream of this warm sea surface temperature that the air should be warmed by the action of the air-sea fluxes over this monopole, and this warm air should be carried downstream and should generate a wake of low atmospheric hydrostatic pressure. So that would give us a pressure gradient force into the warm low hydrostatic pressure that would rotate anticyclonically, just like the wind vectors do on the right side, but on the left side it rotates cyclonically, unlike a Lee inertial wave. So we'd expect some resonant interaction on the right side of the wave, but destructive interference between the pressure gradient force and the inertial turning of this Lee inertial wave that might expect, explaining this asymmetry. This is a lot of words. Let's try to test this. And to test this, we have actually a linear model that we developed a number of years ago, which is based on or considers the boundary layer response, just like we have here, to mesoscale sea surface temperatures, due to both the pressure effect, due to modulation of hydrostatic pressure due to the sea surface temperatures, and also modulation of vertical mixing. And we do that in the presence of large-scale winds, in this case, blowing from left to right. Basically, this model, and I'm going to show you the equations in a second. This model considers the heat, momentum, and mass balance linearized around horizontally homogeneous sea surface temperature and a modified bottom Ekman spiral. Let's just look what this model gives us. And this is the results of this theory of this model. Again, same sort of speed, 11 meters per second going from left to right, the background speed. It's shown here by this lower arrow. This model, again, the background state of this model is an Ekman spiral, and this is forced by a geostrophic wind, which is given by this long arrow. And again, we're using a sea surface temperature monopole here of 1 degree with the same sort of radius and properties as the observations, as we used in its observations. And so it's very nice what we see. We see the same sort of turning, increase in wind speed right over the SST monopole. We see a little bit of anticyclonic turning, just like we have co-located with the monopole. And we see the wake that extends downwind a little bit further than in the observations. But we see this nice asymmetry of the stronger response on the right-hand side of this monopole versus a weaker response on the left-hand side of this monopole. Now I'll show you in the next plot the equations, but we'll spend very little time on this. I just want to focus on the heat equation mainly. For this theory or for this model, we have a very simple heat budget in the atmospheric boundary layer that is simply a homogeneous layer in the reduced gravity model adjacent to the boundary. The winds above this, the top of this boundary layer that's kept by inversion is simply 0. Very simple model. So for large-scale winds that are given by our modified Ekman spiral or background state that act on the air in this boundary layer, and this advective tendency is balanced by the air-sea heat fluxes, which are given proportional to the temperature difference between sea surface temperatures and the air temperatures. A very simple heat budget. But in terms of the processes, how does that include the momentum budget? It includes both the hydrostatic pressure gradient, simply due to the changes in the air temperature, and it modulates vertical mixing. Now, this is a little bit complicated form. We simply say the vertical mixing depends on the air-sea temperature difference, and then modulates by a certain amount of changes in the vertical eddy coefficients in this layer that act on the background wind shear. So this is simply our pressure effect or the imprint of the sea surface temperatures on the atmospheric hydrostatic pressure. And this is the change in the vertical mixing that, let's say, for cold air going over warm sea surface temperature would be an increase in the vertical mixing that acts to mix the background vertical shear and brings the strong momentum from aloft. So these are the two processes that we're after. Because this F applies to the momentum equation, we don't have to belabor this point. That includes advection, includes Coriolis, includes back pressure to the changes of the inversion, and includes simply the background mixing applied to the SST-induced winds. And then, of course, we have boundary conditions, mass conservation, and we have a whole bunch of parameters that we have to determine and we pick sort of reasonable observationally based values for these parameters that determine the solution to the system. Let's go back to the system. So this is basically the parameters that we choose. Again, let's not belabor this. These are these very nice observations. These are nice, what I consider a nice correspondence between the observations and the theory. And what this model allows us now is, if you recall back, sorry, if I go back here to this equation, we can separate in this linear model the impact of the pressure effect and the vertical mixing effect. We can simply look at the solution to only this term as the pressure effect and only this term as the vertical mixing effect. And so in the model, we can simply look at these solutions. The linear model, the two will simply add up to this total solution. So let's do that split. And so this is now the same solution that I just showed you in terms of the total winds. This is the response due to the vertical mixing effect, and this is the response to the pressure effect only. Superimposed in the solid lines, let's talk about these first, is the ground sea surface temperature. In this panel here on the right in C, it's shown the atmospheric air temperature. And you see the atmospheric air temperature is becoming warm as the air passes over the warm sea surface temperatures, but then carries this warmth over some downstream wake for a certain distance that depends on how fast the atmospheric air sea fluxes bring the system back. So this is sort of a length scale, how far the air goes in sort of a typical adjustment time scale of the temperatures in the atmospheric boundary layer. So, and solid and dashed line in the center panel simply show the difference between the air temperature shown here and the sea surface temperature shown in the left panel. And so as the air passes and encounters the warm sea surface temperature, first the air is colder than the sea surface temperatures. As it passes over, it gets warmed a little bit and carries that warmth then downstream over now back ambient sea surface temperature, such that the air temperature is warmer than the sea surface temperatures. Now we can look at the wind response to this. So this is the response in terms of the errors that is due to the vertical mixing process. And we see it's very strong, almost dominant right over the sea surface temperature anomaly itself, but then it reverses sign in line with the change of the air sea temperature difference according to our parameterization. That's very nice. Now the pressure gradient shows us, of course, a response that's informed by the wake of warm sea surface temperatures to the lee of the warm sea surface temperatures. But this shows, again, the sort of asymmetry between the right side and the left side of the response. Again, this arrow down here scales the distance that air travels at 11 meters per second during half an inertial period. And so we see exactly this is consistent with what we had before. The pressure effect on this side, on the right side of this wake, of this warm wake, turns in resonance with the anticyclonic inertial turning of the winds and gives us a strong response on the right side, versus on the left side, the pressure turns cyclonically, the anticyclonic lee wave wants to turn anticyclonically, and so you get a destructive interference on this side of the fan of the wake, giving you a stronger response on the right side of the wake.
Niklas,
so what we see here,
1 more minute.
Okay, what we see here is simply a lee wave. Okay, and so then I will skip the Rossby number, even though that's very nice, but that will take too much time. And I come to the conclusions that basically we looked at the response or at the processes that govern the response of the surface winds to the sea surface temperatures. We see co-located with sea surface temperature, the speed increase and anticyclonic turning to the vertical winds. And we have a strong Lear inertial lee wave that is stronger on the right side of the background winds in resonance with the pressure gradient force. Now, the stuff that I could not show you is actually the scale dependence, and that shows that actually in wave number space, the response is a very strong function of the Rossby number, with the vertical mixing dominating for large Rossby number, the pressure effect dominating for the small Rossby number, and order 1 Rossby number. All of these effects are important. Thank you very much.
Thank you very much, Niklas. We have one question from Justin Small. Does your model include the effect of strong and fast-moving atmosphere fronts?
No, This model does not include the effect of atmospheric fronts. This is a very interesting effect. So basically, if you think of a classical mid-latitude cyclone, then I think this model may be relevant in both the warm sector and the cold sector, but not at the border between the two, at the atmospheric fronts. So this is actually a very interesting area of research that we are exploring right now. To what extent does this model explain some of the smaller scale features in the wind divergence that we see over the western boundary current regions that are in part due to the atmospheric fronts, but also in part due to the imprint of sea surface temperature.
And Junie is asking one more question. Considering changes in background state in response to global warming, do you expect any future change in structure of wind response and coupling strength?
Now, that's a very interesting question. So you have to ask, so within this context of this linear model that I have, to what extent do background sea surface temperatures inform this response? And they inform the response because under warmer climate, you might expect that, for example, the adjustment time of the atmospheric boundary layer becomes shorter because of the stronger effect of the latent heat flux. And so there may be some shift in the parameters of that solution. So yes, I expect some response, but I think it's going to be subtle.
Okay, I have one more question. So currently your SST is of course given, and you calculate the atmospheric response, but the atmospheric response will feed back on the SST itself. Correct. Have you looked at the fully coupled problem, and is there any way of generating patterns or new scales from the coupling?
That's, again, a very interesting question. So, for example, if we look at this pattern here, we have an Ekman pumping response associated with the winds, which should feed back on, presumably, an eddy that is associated with the sea surface temperature pattern. So this is a very interesting question. However, there's one complication, and that has to do with the different timescales of the eddies and the atmosphere. And this is all informed, the direction response here is informed by the background wind direction. And that, of course, changes in the mid-latitudes from day to day with the atmospheric synoptic variability. So what an ocean eddy, which has time scales or evolution scales more of weeks to months, they will integrate this response as the background winds rotate around. On that can, I think that will introduce some very interesting effects, but this is something, again, where we're in the process of exploring it.
And one very quick question by Aoyun. SST wind relationship is determined by boundary layer stability or pressure gradient along the ocean and atmosphere front. I guess is the SST wind relationship determined by boundary layer stability or pressure gradient along the ocean and atmosphere front?
In a way, I consider the stability that's induced by sea surface temperature itself. So whether the sea surface temperature is warmer or colder than the air temperature, that informs the vertical mixing in the boundary layer. Now, you could also argue that there should be actually, in addition to this non-equilibrium response, where air temperature is not in balance with sea surface temperature, there could be an equilibrium response if you have overall a lapse rate in the atmosphere and the warmer sea surface temperature gives you a deeper convective response of the boundary layer. That's not in this model. It can be included, but it's not in this model. But I could put this in.
Thank you very much, Niklas, for your presentation. We move on to our next speaker, Sato-san Masaki Sato from Atmosphere and Ocean Research Institute at the University of Tokyo. And Masaki also wrote a very interesting and useful book on, I think it's published in Springer, on atmospheric dynamics and also climate modeling. So please take a look. Okay, Masaki's talk is about the robustness and uncertainties of global cloud resolving models, evaluations and improvements of clouds with a seamless approach. Thank you very much for joining today, Masaki.
Okay, thank you. Can you hear me?
Yes.
Okay, can you see the slide?
Not yet.
Not yet? Okay.
Yes. No, it's there, but...
You did. It is okay?
Yeah, it's fine.
Okay, thank you. Okay, I talk about this title. This is a collaboration work of the Project Diamond. It's managed by DKRZ in the Germany. And this work in our part is mainly work in the USAB role. He's working in my laboratory. So my talk is showing the recent results of the global resolving model intercomparison project and some my thoughts on the evaluation improvement strategies. Okay, so the next slide. Okay, this is the Project Diamond. So Project Diamond is a dynamics of the atmospheric circulation models on non-hydroscopic domains. This project starts about 2 years ago, and recently the summary paper has been published. First authored by Bjorn Stevens, and this is published in this journal. This is the first inter-model comparison project of global atmospheric circulation model with storm resolving grid scale. This means grid mesh spacing less than about 5 kilometers. Then the models, 9 groups have participated in. ICON Germany, NICAM group, MPAS, US, NASA GEOS, FV3, SAM. These are US, United Kingdom. This is French. This IFS European Centers model. So on the summary, there are some similar characteristics across the models and also differences. So I say robustness is a similar characteristic. I'll show later OLR and upper cloud structure similarly, and the mesoscale structure is reasonably represented these high resolutions. And precipitation, I show this zonal mean precipitation very similar. It's one of the amazing results. Tropical cyclone characteristics. And uncertainties, I may focus on the vertical cloud profiles. This is very different. For longer simulation, model produce their own climatology and difference in precipitation dispersion. Have a zonal mean precipitation amazing consistent. So I also have a review paper of this cloud resolving model. This includes the definition or terminology of this naming. Okay, this is a snapshot of the 9 model results with one observation. I believe one in the middle is the Himawari geostationary satellite. And the 2 model resolution of the IFS is increased, so there are these numbers. So from this view, the older model reproduces kind of realistic cloud profiles. This means upper cloud structures. If you see each of them, you may think this is, looks like a geostationary satellite. This can be possible in the real atmosphere. So this is the first impression in the older model reproduces very realistic cloud, complicated or fine structure of clouds. But in details, you may see differences. Maybe the difference cloud fraction or cloud thickness or the shallow cloud behaviors are differences. There are also differences from this first quick slide. Okay, this is another view of the different models, different resolutions. Along the tropics, you may see, even though the thickness of white is different, but the structure is similar. Here is a tropical cyclone. Not only this is just a 40-day simulation initialized from the European Center's initial condition, and spin up for 40 days. And these tropical cyclones are reproduced because some information is included in the initial condition. This is could be you can imagine if you forecast model can produce a tropical cyclone about 1 week or longer. But the point is mesoscale structure, like here, this is ITCZ. Here is some very similar structure, and also here, similarity between all the models. Okay, this is further closed look view. This is tropical cyclone. Tropical cyclones are reproduced of the models. And these structure also are calculated similarly. So this includes the mesoscale circulation like cold pools and the cloud organization. Mesoscales convection systems are naturally resolved in this kind of resolution. So even if the initial condition is kind of relatively coarser, kind of, I say, 10 kilometer or more, after that, mesoscale circulation system, including cold pools and cloud organization, are representing these kind of models across the global domains. So this is one of the characteristics. Okay, the differences can be found. Tropical cyclones will capture after initialization, but these characteristics are different. This is the most intense tropical cyclone plane view. So the tropical cyclone consistently simulated by the older models. However, their track structure and intensity depends on models. This may be we experience in the regional models and the forecast models. So they may depend on both dynamics and physics of models. And even though the grid spacing, grid lengths are similar, but the effective resolution is different. These are dependent on the detailed dynamic core. And of course, physics, particular cloud microphysics and turbulence schemes affect these structures. So this is snapshot of 10-meter wind speed of the strongest storm for each model at the time of peak intensity. Okay, this is the similarity part. Zonal mean OLR. You may see this is Ceres profiles. We think this is a best observation result. So the older model have a similar range. So it's not amazing because the models are generally tuned for OLR first. But maybe surprising because some models are first experienced to run this kind of high resolution. So but I think this kind of similarity is based on after repeated tuning of the models. If you have bad OLR, you may first retune the model by changing cloud microphysics and something. This is precipitation. So this is a latitude and intensity. And one of the observation, GS map high resolution satellite-based observation data in gray scale. So I think this is one of the important result in this intercomparison. All the models have similar intensity and they also have a similar range. Because traditionally, the general circulation models have a stronger precipitation compared to observation, and people say did not think which is better, observation models. But in this similarity or coincidence, we may confidence something about this is a realistic value of precipitation. And also interesting behavior is this departure, because the GS map based on the GPM, this is not good for retrieval for the high latitude. So this consistency across a model suggests the reality is in the modeling side in this latitude. Okay, and the on contrast, Northern Hemisphere is similar in between observations models. Some difference seen in the Southern Hemispheric ITCZ region. This is maybe a weak point in the GCRMs in this variability. Okay, I go in details in the more cloud characteristics. This is analyzed by Usab Law, submitted the JMSJ special edition on the Diamond project. So this is Atlantic region. OLR, this observation and different models. So at first, you may see the similar ITC's characteristics, but in detail, configuration and intensity are something different. But we say this is a better similar similar characteristics. OLR is a similar characteristic of the model. But we go analyze the vertical profiles. Before that, the shortwave radiation is more diverse because it reflects shallow cloud properties. So these are more difference in the cloud fractions. Okay, this is one of the vertical profiles here. This is height. This is mixing cloud water mixing ratio. This is cloud ice mixing ratio. So you may see cloud model, these are kind of order magnitude differences. NICAM is here, relatively smaller, and this is some models have a very much liquid water above the melting levels. Cloud ice also have a very different. NICAM is here, and these are differences. So all the models report the triple modes of cloud system like shallow, congested, deep clouds. This is a similar characteristics, but the magnitude is different. And also this is the first experience to compare global domain cloud microphysics model. Cloud microphysics are different. So some models didn't show, didn't output all the categories of cloud. So this is cloud ice. Some models are counted in the snow and cloud ice separation is different depending on models. So if you include the snow, this may be some different view, but this is not available currently. And also global also affect the results. So this is resolution dependency on the vertical profiles of the cloud water and cloud ice. Here is a cloud, this is liquid part, this is ice part. Resolution dependency, we can show the NICAM 7 and 3.5 kilometer. ICON, this is German model, two differences. IFS, European Centers model. So generally, resolution affects the cloud water. NICAM ICON increase cloud water of shallow clouds. Here, higher resolution decreasing. IFS decrease cloud water of congested clouds here. For cloud ice, the older models show some increase. Older model increase cloud ice in higher large resolution experiment. And NICAM shows smaller increase in cloud ice than ICON, and after the resolution becomes higher. And also some height difference can be seen. So resolution dependency, some similarities, but not all the models have similar results. This is cloud fraction. So cloud fraction is not physical quantity, so we should be careful for defining the cloud fraction. In our case, we use a threshold of this value for clouds to define the cloud fraction. So cloud fraction depends on this threshold values. This is the impact on the cloud fraction. The fraction for triple modes and clouds are different among the models, like here. So this shows the NICAM here, ICON here. Data is observation based on CloudSat Calypso data here. And here is a different model, IFS, GEOS, and some here. Some models have differences here. So this is a not so physical intercomparison. So overcome this one, we use a satellite simulator. This is CloudSat Calypso observation. Observation have their own cloud fraction depending on their signals. This also depends on threshold, but they are consistent cloud fraction by observation. And satellite, we apply satellite simulator, we can same way define the cloud fraction. Yeah. So use of satellite simulator for consistent evaluation. We developed joint simulator for satellite sensor. There are Several satellite sensors in the world and the climate community uses common too. But in this high resolution, we use our own in-house satellite simulator. This is very good for consistency on the model and the observation. Anyway, this is consistent evaluation. So NICAM have experienced tuning, improving based on these observations. So there are some similarities here. Like here, this is CloudSat Calypso. Shallow clouds is always a problem. So because in our resolution 3.5 kilometer, without the shallow clouds good scheme, we don't have we have a very few cloud fraction at current simulations. This is one of the more detailed analysis. This is probability density function of ice water pass. This is ice water pass and the probability density function for two resolution. This is highest in this value. The models show some similar behavior like here, but in detail difference. Interesting point is dependence resolution. So then I can show the decrease here, increase here, increase here, like here. European Center have a similar structure, but this area is different. If you focus on thin high clouds, this area, thin high clouds is increasing in NICAM cases, but the IFS is decreasing. So this may be a concern or affects the climate sensitivity issue if you think of a cloud change in the future. Okay, these are evaluation part. So at the rest of the few minutes, I introduce how our strategy to improve evaluate the models. Okay, this is an evaluation improvement class with a seamless approach. In NICAM, we can use our model in different way. Normally with a uniform resolution model like here. In this case, cloud resolving high resolution model can be simulated. But we may focus on some particular area by changing this mesh configuration. Like this way, we call this is stretch model. And also this person developed a regional model approach. We just pick up this one tile like here and simulate. This is exactly the same approach as a regional model. So anyway, this can reduce the computational cost and but share the same physics and dynamical core in the different configuration. So if you have intensive observation in this area, we can repeat many observation in this, many comparison in the simulation in this domain. And the results can be directly reflected in the global model and climate simulations. This is recent work by Usaburo and Seiki Tatsuya Jamstek. We improved the southern hemisphere mid-latitude clouds. This is observed system. This is A-train tracks. Two different models simulate this structure similarly, like here. We show this vertical cross-section along this line. So observations show this height and latitude, shallow clouds and convective clouds. This is backscatter by Calypso, depolarization ratio by Calypso, radar reflectivity by CloudSat here. This is observed shallow clouds existing here. Now I come to kind of microphysics scheme, single moment, double moment scheme. Single moment scheme didn't capture this shallow clouds here, no shallow clouds. Double moment scheme, in general, our double moment scheme is very good. Shallow clouds calculated like here, and depolarization is also represented here. So what we do is by referring to double moment scheme, changing this scheme by one step by step, and improve this scheme to represent this shallow clouds. So this is what Seikan Rowe, this is recently published. He did a step-by-step approach and introduce many improvement. So eventually, this single moment scheme have captured ice cloud like as represent ice categories and this one. Okay, what we did is this test by the box model and the stretch model result. So once we developed this scheme, this is observed shortwave radiation, and this is original scheme have a more reflective, less reflective. So after the improvement, we have a more reflective shallow clouds and the improvement. So this is our one of the approaches currently. So next, we are proposing the further systematic observation and modeling comparison. So there are, you may say, the supersite, many observation sensors are placed in the same location. So in Japan, we didn't have a supersite, such a supersite, but we think of Tokyo metropolitan area. There are very lot of sensors, remote sensing sensors. Polar radars, cloud radar, here is a NICT, Doppler radar, wind profiles, phase array radar, and others. So this is, we propose this for the scale satellite. This is ground observation site for NICT, and also JMA operation sites. So phase array radars, polarimetric radars. This is one example of last year, September, cloud radar. This is in the upper view. There are severe windstorms. One example is a typhoon 1915. This is attacked in the metropolitan area. Here's observation. We have done two simulations. This is very fine resolution, 1.5 kilometer by stretch. So this is observed cloud radar profile. So we are comparing this one and to see the difference and similarity to improve the cloud microphysics. This is our strategies.
3 more
okay, this is, okay, finishing. Okay, this is summary. We did an intercomparison project. What we think the robustness is we compare the diamond results or the model the cloud distribution compared to Himawari, geostationary satellite, OLR, and precipitation. However, a lot of variability exists for vertical structure of clouds. Cloud evaluation using various observations are required. To evaluate and implement use of multiple satellite observation and satellite simulators is important. Use of ground observation, remote sensing, SIS data. Use of seamless approach with a unified global regional model is possible. We propose the ultimate initiative. Okay, thank you very much. I finished my talk.
Thank you very much. We have 2 questions. I will just read them quickly to you. Is the fact that global cloud resolving models simulate OLR and precipitation zonal means better than vertical cloud profiles or cloud distribution inherent from model construction?
What's the later part? This is the horizontal.
So I guess the question here is whether the better simulation of OLR and precipitation zonal means relative to the vertical cloud profiles, which are more diverse, is just triviality.
Okay, I cannot see the question, so I want to show the one.
Can you post the questions?
Okay,
they should be up on the screen soon.
I see. Yeah, I have a lot severe experience on vertical. You're talking vertical resolution?
Yes.
Yes. Yeah, we have.
No, not vertical resolution. The vertical cloud profiles. They seem to have a lot more scatter. Were less certain than the OLR and precipitation zonal means. And one of the people sending the question probably wonders whether this is by construction.
Yeah, I cannot answer the question. The details are very depend on many factors. So, yeah, zonal mean, consistency of zonal mean, OLR is, I think, by the tuning. But precipitation zonal mean consistency, we cannot explain the reason. because the energy budget, they say, is not constrained is 40 days simulation. And in the detailed horizontal distribution, they may depend on many factors like dynamic core and the physics. For example, physics, cloud microphysics affect the cloud precipitation evaporation, then they affect the cloud organization. So after that, they may have their own evolution. But statistically similar results, this have in some range of the similarity of the physics construction. That's what I can answer at the present.
Okay, thank you. And the other question by Kyungja Ha is whether when you go to cloud resolving models, whether you also increase the vertical resolution.
Yeah, this is another issue. Some groups are trying to see the effect of vertical resolutions. We did have experience. So in general, vertical resolution affect more the results. So people do not touch easily the vertical resolution issue, but in fact there are very lot of difference, particularly the cloud depth and cloud thickness. In general, yes.
Okay, we have one question, anonymous question. Does this very high resolution SST force model recover the topographically induced rain bands in the Indian Ocean and Western Pacific that Changping Xie has pointed out? Oh, it was posted by Niklas Schneider.
Okay. So as you may understand, the SST forced model have some problem if in the region like South China Sea or the Western Pacific, if the cloud feedback on the ocean is important. We have a relatively stronger bias in the precipitation. Tropical induced rain bands, I don't think so much influence is because topographic forcing. So, yeah, in my view, it's a separate behavior. It's forced model, topography forced model, precipitation.
So my question is, if you go to cloud resolving models, do you actually have to retune your cloud microphysics?
Yeah, we don't say tune. We want to improve the cloud microphysics by comparing the observation. We can use a lot of observation, satellite and ground remote sensing data. But even though we have some rooms for tuning, for example, we have a tuning for conversion from cloud ice to snow, and also the terminal velocities are commonly used tuning. But ArcGIS satellite can observe vertical velocity, terminal velocity of clouds. So after that, we cannot use it for tuning. So I hope it answers our message.
Fair enough. Okay, thank you very much, Masaki Sato, for your wonderful presentation. We'll move on to our next speaker, Justin Small from NCAR. Are you there, Justin?
Yeah, hopefully, can you hear me?
We hear you. We can't see you yet, and we can't see your presentation. Oh, we can see you? Yeah.
Great.
And just a quick introduction again for those who are new on the YouTube channel. Justin Small is a project scientist at the National Center for Atmospheric Research, and he has spent a lot of his career looking at small-scale air-sea interaction processes. And must be quite dark there already, so nighttime for you.
Yeah, not too late. Well, thank you to Axel and G, I think, and all the people at IBS for inviting me to this workshop. I'm here on behalf of quite a big consortium. It's the International Laboratory for High Resolution Earth System Prediction. It's known as IHES, and it's a partnership between the Qingdao National Lab for Marine Science Technology, Texas A&M, and NCAR in Colorado. And the principal investigators are Ping Chang, Xiaoqing Zhang, and Gökhan Danabasoglu. But there's been huge contributions to this work by many people in the author list I show there. So it's really quite a team effort.
Justin,
and
can you use the presenters mode for PowerPoint?
Yeah. Is that okay?
Perfect. Thank you.
What have we learned from our high-resolution simulation? So that's the topic. And so I'll have a brief introduction, and then I'll follow that by overviewing the schedule of our simulations. And then the main part will be what have we learned. For example, how does the simulation of natural variability in response to anthropogenic climate change depend on resolution? How do multi-scale interactions affect the large-scale climate variability? And to what extent can knowledge of climate variability gained from low resolution be carried over to high resolution? And I'm not going to talk about the topic in red, which is about model biases. There's several of those, as usual in most climate models. They were addressed in the paper by Small et al. 2014. And in fact, I was interested to see Axel was actually showing them again this morning. So there's things that need to be improved, but there are some nice enhancements of resolution. And I'll end with the way forward. So for people that aren't familiar with the system being used, it's the Community Earth System model. CSM version 1.3 is used here. The current version for standard runs is version 2 of CSM, but we have not tested a high resolution version of CSM2 with high resolution and atmosphere. So we're still using a slightly older version, which has CAM5, so now it's CAM6, and a slightly older version of the sea ice and the land models. The ocean model is fairly up to date. And just to put it in context, on the left side here is a diagram I put together around about 2015 showing some examples of high resolution climate models. And on the x-axis is the ocean grid spacing in degrees latitude, and on the y-axis the atmosphere grid spacing. And we're in this kind of range of 1 degree or less on both ranges, and the standard resolution, for example, for CSM is about 1 degree in both components. And we were, back in 2014 or so, we were trialing out 1/4 degree atmosphere and 10th degree ocean. The first person to do that, I think, in the global model was Julie McLean and co-authors. We had a simulation published in 2014. And this is the same grid that's been used by the IBS group and the IHES group. So we're down here. So this is in the eddy resolving regime for much of the ocean, and it's in the kind of mesoscale convective permitting regime for the atmosphere. And now that fast forward to present day, this is a figure sent to me by Malcolm Roberts. After high res MIP has taken place, we can see how it's evolved. Again, ocean resolution against atmosphere resolution. And there's a lot more in the kind of quite high resolution now. And in particular, the 1/4 degree ocean is very popular. It's called eddy permitting for the ocean. But still, this grid of a 1/4 degree atmosphere, 1/10 ocean, which is about here, is still pioneering and the highest resolution for climate models. So what do we learn from that? For our purposes, for IHESP, there was a big computing challenge. This is dealt a lot by the group in Qingdao, led up by Xiaoqing Zhang. And their computer was a different style to many. It's called a heterogeneous many-core system, where a CPU has 4 different groups, and each group has a master core which has to communicate with 64 what he calls slave cores. And this architecture is meant for a more complex decomposition. So in addition to the normal core and halo decomposition, there's another level of decomposition where you have to deal with this communication between master cores and computing processing elements. So this is a very complex task. It's been written up by Xiaoqing Zhang. I'll show that paper in a minute. And they succeeded in doing it. It's a remarkable achievement. It's a very energy efficient machine. These are some idealized tests. It does very well. And in addition to the runs at Qingdao, simulations were also ran at Texas on their high performance computing systems at Texas A&M and the Texas system. And in terms of how many years per day we could get, well, with the high resolution, somewhere between about 3 and 4 is typically achieved for high resolution global models. So on the left is this paper I mentioned, now published by Xiaoqing Zhang, which is all about the porting of the model. And that's published in GMD. And then on the right, we have a manuscript submitted to James on the main climate runs. And you can see the co-authors there. So that's in submission. So quickly moving on to the simulations that have been performed, starting at the top here with 1850 PI control. That's been run out to 500 years. And then branching from it, from year 250 of the PI control, we started a historical simulation for 1850 to 1920. And then from 1920 to about 2006, continue the historical, and then move to the RCP 8.5 up, and actually got to 2100 now. The proposal is an ensemble of 5 to 10. So far we have 1, but we have started a second and third. So that'll be a topic of discussion towards the end about ensembles. So we've also been proposing to do initialized decadal prediction runs. We haven't started those yet. We also participated in high-res MIP. So this was an alternative protocol where you're dealing with 1950 as your base year and do at least 100 years control and then a 1950 to 2050 transient. So we participated in that, also done ocean and sea ice simulations. This is 60-year simulations forced by JRA 55DO. That's by the product by Hiroyuki Sugino et al. So that's another nice data set. We've done a 1% CO2 run. And then finally, the data is freely available. There are these websites that you can go to. We've started putting the data there. We haven't put all the data there yet, but the plan is to put all the data there. And the code is available. So a few of the results, this is from the pre-industrial control. One of the first things that became apparent to us was a dominance of both Antarctic sea ice variability and basic global temperature variability. So multi-decadal variability in both of these fields. So this top left panel shows time series of the SST variability in red and the southern hemisphere sea ice extent in blue. So large multi-decadal variability. Turns out in the Antarctic domain, it's to do with these open ocean polynya in the Weddell Sea. I think Axel might have shown something like that from their simulations. So these are like 50-year or longer cycles, so quite long. And they're related to the global surface temperature signal and to the interdecadal Pacific Oscillation, IPO. So there's a global structure to this. And all I'm going to say, these seem to be related patterns. I'm not going to say anything about causality. And we're still working on this, but it's a dominant feature of this simulation is this large multi-decadal variability. Another thing we've noticed is, and also Axel pointed out something similar here, there's a lot of variability in the high resolution models, as you expect in the boundary currents and so on. It can be stronger than observed, although the observations are limited, particularly for things like SST, where the cloud cover affects the high resolution SST observations. Well, what we've found here is that, yes, in the high resolution model, there's a lot more variance of SST than in the low resolution. So this is showing the ratio between the high resolution and low resolution of SST variance. And mainly as a consequence of that, we have the same variance ratio for turbulent heat flux. You see it's got a similar pattern in boundary currents. And some of the results that Lucas Lorindo is a postdoc with us now, has been comparing the spectra of the SST between the high-res and low-res models and observations. Here's an example for the Agulhas return current system. And the low-resolution model is much weaker variability right up to wavelengths of about 2,500 kilometers, so quite long, longer than intrinsic eddy scale. So this is an interesting result, and the high resolution quite well matches observations in that region. That's not the case in the Gulf Stream, where the high resolution is much stronger than observed. And the key feature is that the SST and the turbulent heat flux are strongly correlated in the high-res model, such that you have more heat loss over warm SST. And this is a signature of ocean driving processes. And in the low resolution model is much less of that seen. Here's a plot of the coherency. And again, it matches quite well the observations, high resolution and low resolution. And they're basically in phase, the near zero. So these are some nice results on the variability. Talk a little bit more about the historical period, 1850 to 2006, and then the RCP 8.5. If you look at the global temperature change, this is a time series from 1850 to 2100. The top few lines here are SST, globally averaged. And what you see is the time series of SST and the increase. The blue line is the low resolution, red line is high resolution, and then we have some observational data sets. So in a global average, it looks very nice in the high resolution. I wouldn't say that's true of regionally, but it's a very nice picture for globally. The low resolution is much cooler, and you can see that, in fact, from these SST bias plots. So this is low resolution minus had SST, and you see the dominance of the cool blue colors is high resolution minus had SST. It's more dominated by positive warm colors. So quite a good behavior of the high resolution here. But if you remove that background cool state of the low resolution model and just plot the anomalies, which is shown at the bottom here, they actually all pretty well overlie. So what this is saying is, well, as you can see, the anomalies match very well. It's just the base state is different, and that base state does not seem to dramatically distinguish different anomalies. They all seem to follow a similar path. The Nino 3.4, this might be of interest to many people. And in the older paper, the Small et al. Paper in 2014, in a 100-year run, we found in that case that high resolution had much less power than low resolution and was more realistic when you compare to observations. While when you go to these new runs, which are longer and more equilibriized and so on, we actually get a different result. And we found the high resolution for the historical period actually has slightly stronger power than the low resolution. And this is shown in the spectral plots here. The high resolution is in blue, and low resolution is in green. So don't believe everything you see from a shorter run is probably one of the conclusions from this. But why do we get that difference? We don't know, but maybe it's a function of the record length was too short, or natural variability. But also there were changes in model physics between the version ran for the 2014 paper and the IBS version. And they're not dramatically large changes, but maybe they had some impact. Okay, extremes are one of the things, and small scale features, one of the things you want to see in high resolution, and you kind of hope that will give improvement and new information. So, and Axel talked a little bit about this as well. On the left, and Masaki, a previous speaker, on the left are tracks of tropical cyclones from observations, in the middle panel from high resolution, lower panel from low resolution. And the high resolution generally got similar patterns to observed, but if you look in detail, there are quite major differences. Less and weaker storms in the Atlantic, which is a very common problem. More storms in the South Atlantic. And then actually this extension of storms to higher latitude, this might be due to a sensitivity to the tracking method. So I won't go on too much about that. Low resolution obviously only captures kind of tropical storm strength systems. But then you can also relate these tropical cyclones to things like Nino 3.4 or the AMV. So in the observations at the top, okay, let's choose this left panel, Nino 3.4, you see the reduction of tropical cyclones in the Atlantic. You see an increase in the Pacific. The middle panel is high resolution, and it's difficult to see in the Atlantic because in general it has weaker storms there, but there's a hint of weaker storms in the Atlantic. There's an increase in the Pacific along with observations, and something slightly different in the Eastern Pacific. Low resolution is less distinct, but some similarities. Relationship to the AMV. So this is an advantage of using a long run in that you can relate to decadal variability like AMV. The observations show the increase in the Atlantic during positive AMV, a reduction in the Pacific, and there's a hint of that in the high resolution. But again, the Atlantic has deficient tropical cyclones in general. So these are the kind of things you can do with high resolution models and long high resolution models. Next, some regional warming patterns and differences. So this is how the surface air temperature changes the end of the century minus the 1950 to 1980 period. So this is the end of the 21st century. So the high resolution, note the color bar, everything is positive here. Blue just means less positive. And then the low resolution, and then probably more informative is the difference, high resolution to low resolution. And the things we've noticed here is there's stronger Arctic amplification in high resolution. You see that from the positive values here. But on the other hand, in Southern Ocean, it warms less. And there's been a few papers starting to discuss that. And maybe it's due to ocean eddy processes. Another interesting feature, which you can barely see in this global plot of air temperature, but if you look at SST, this is a high resolution SST change. It's very enhanced at the western boundary of the Atlantic, of the US and Canadian East Coast, the temperature 6 to 8 degrees and more in this kind of Grand Bank area. So quite an enhancement. There's been some science papers on that as well from previous models, and this seems to be confirming it. So enhanced warming of western boundaries is an interest of ours. I should speed up. There's some interesting stuff about AMOC, but I shan't cover it because of the time. Then some examples on extremes in future climate. This is how the tropical cyclone density changes under future climate. So there's a hint in high resolution of a reduction in the Atlantic and East Pacific, more increase West Pacific, reduction in the Indian Ocean. And actually you see something similar in low resolution, but for weaker storms. We can also look at atmospheric rivers, but I won't have much time to talk about that now, but that's another thing we're interested in. So I'm running out of time, but we had these questions at the beginning and basically related to how do the low resolution climate simulations compare to high resolution. Well, things like the global average quantities, they tend to behave similarly, but now there's a cooler background state in low resolution. But there are regional differences that I talked about earlier. How do multi-scale interactions affect large-scale climate variability? We saw unique air-sea interactions on scales of 2,500 kilometers or less. And also there's, I didn't talk about this much, but the AMV and MPO patterns seem to be more realistic in high resolution. And again, generally high resolution, consistent with low resolution, but some new aspects. We found large-scale polynomial variability related to IPO. We found more detail on how the tropical cyclones responds to modes and climate change, and similarly for atmospheric rivers. More questions arriving. This is something I'm interested in, this top question. How many ensemble members do you need at high resolution? And naturally, we don't have much computing time, and we're only proposing 10 or less, and we've only started, finished one so far. But with high resolution, need more ensemble members because there's more variability. And I think I need to wrap up to leave the 5 minutes of questions. Let me see if I've done everything. Now, let me just talk about the way forward. Again, more ensemble members, decadal prediction runs, role of missing parameterizations. This is brought up by, maybe it's Axel again. The sub-mesoscale and overflow parameterizations are not in a high resolution model. And then there's a number of science topics that we want to pursue, and there's many more that I couldn't list them all. So we're interested in discussions of this with the attendees and everyone. Thank you very much.
Thanks a lot, Justin, for this wonderful overview. We got 2 questions from the audience, one by Sriush. What is the possible information we can extract by looking at the high resolution versus low resolution SST variance ratio? Does it provide information on variability in different timescales?
Yeah, that's a good question. And actually, I think I deleted the panels which talked about different timescales. We're looking into the timescale question. And again, we're interested in whether these small scale features affect longer timescales. And I would say it's work in progress. I think off the top of my head, I'm not going to say a definitive answer, but that's what we're looking at. And the other key thing is we're comparing it with stochastic models of air-sea interaction like the Barsugli and Battisti and Franguignol type of models to try and understand what we're seeing in the high resolution model and differences from low resolution.
Next question by Danielle Lemon, more a philosophical question, I think. Is it possible that the computational ability embodied by global high resolution modeling is expanding faster than our field's ability to specialize and holistically analyze it?
It's a big question at NCAR, actually. At the moment, is data and how to data analyze huge data sets, like, as it is a question, I think, at your institute. Is it going beyond? I think the data analysis is having a hard time trying to keep up. But we are learning stuff from the high resolution modeling. And so I think it's not totally distinct. I think we are learning.
So I would agree to that statement, but also very much the kind of analysis that we do once these data become available is traditional analysis. We look at NINU3, we look at, so same of course on our side. We would like to see how well does the high resolution compare with lower resolution models and so on. But nevertheless, I think there is so much more in these data that we don't even have the tools developed yet to explore this. So yeah.
Agree.
Thanks a lot, Justin, for your great overview presentation.
Thank you.
Good night to you in Boulder. Okay, thank you.
Thank you. Not that late. Thank you.
We will move on to the last speaker in our session, Jong-Eun Chu from the IBS Center for Climate Physics, and so she's here today in person.
Hi everyone, my name is Jong-Eun Chu from IBS Center for Climate Physics. I am honored to be here to have an opportunity to introduce one of our high-resolution projects on future changes in tropical cyclones. This work is conducted together with my co-workers Sun-San Lee, Axel Timmerman, Christian Bengal, Malte Stücker, and Ryohei Yamaguchi. Tropical cyclones are intense atmospheric event that conveys tropical heat and moisture to higher latitude. These tropical cyclones threaten human lives and properties because of their heavy rain, strong wind, and storm surges during the landfall. For example, in 2003, Category 5 super typhoon Memi hit Busan, where is the largest coastal city in Korea and where our ICCP located in. In the harbor area, it wrecked 11 lifting cranes, each of them weighing about 900 tons. And in total, it killed 120 people and damaged about $4.8 billion US. So especially in this kind of coastal areas and where 40% of the world population lives, it is crucial to understand how their tracks, intensity, and associated rain will change in response to greenhouse warming. Thanks to the recent development of satellite observation and in-situ observation, now we have a better understanding about the structure of tropical cyclones. For example, when we look at the storm center in terms of minimum pressure, the maximum wind speed can be found at about 50 kilometers away from the storm center, and some others at even closer locations. In other words, in order to resolve this structure of the maximum wind speed, we definitely need model resolution higher than 50 kilometers, and that was one of the motivations of our high-resolution simulations. In addition to atmospheric resolution, resolving major-scale oceanic features is also important. In some cases, after a passage of tropical cyclone, the SST can decrease by up to 10 degrees Celsius. And if the speed of TC movement is slow enough, like the case of Typhoon Solik in 2018, the surface temperature drop can provide an immediate negative feedback on the TC development, weakening its intensity. In contrast, in case of Hurricane Michael at the same year, the ocean status acted as a positive feedback due to the combination between downwelling heat transport by previous storm and upper ocean heat wave response. In both cases, ocean resolution is important because higher resolution resolve better atmospheric ocean interactions. Until recently, previous studies on future changes in tropical cyclone have adopted three main approaches. First one is pseudo global warming experiment. This is basically using atmospheric model only. This approach ignores possible two-way interactions between atmosphere and ocean. Second approach is regional atmosphere or regional coupled model experiment. This approach in this approach, coarse resolution model simulations are used as a lateral boundary conditions, and therefore Model outputs are sensitive to domain size and lateral boundary conditions. Last one is fully coupled global Earth system simulations. This one is computationally expensive, but it captures the interaction between tropical cyclone and ocean more realistically. However, SST biases from the coupled model can still influence the representation of tropical cyclones. Fortunately, we could purchase our supercomputer, as Axel introduced. We named it Aleph. This is Korea's second fattest academic supercomputer, and the peak performance is about 1.43 petaflops. And our fully coupled CESM simulation performs about 3 simulation years per day. And Dr. Sun-Sun Lee will give you a more detailed information about our high-resolution simulation during the workshop. Let me explain about our simulations. We conducted fully coupled CESM simulation with atmospheric resolution of 25 kilometers with 30 vertical levels, and ocean resolution of 10 kilometers with 62 vertical levels. Because this resolution, especially ocean, is exceptionally high, we call it ultra-high resolution CSM simulations. We conducted 3 major experiments with different levels of fixed greenhouse gas concentration: present day, CO2 doubling, and CO2 quadrupling experiment. The experiment conducted by IHAPS is transient simulation, but our simulation is fixed greenhouse gas concentration. So present-day simulation was initialized from a near equilibrated climate state conducted by NCAR Group as a courtesy of Justin Small, and integrated for another 140 years. And CO2 doubling and quadrupling experiments were branched off from year 71 of the present day, and it was integrated for 100 years, respectively. This figure shows global mean time series of the surface air temperature, top of atmosphere radiation imbalance, and precipitation. Surface air temperature increased toward the end of simulation by 2.5 degrees Celsius and 5.1 degrees Celsius in the 2 times CO2 and 4 times CO2 respectively. And the ocean temperature increased by 1.8 and 3.8 degrees Celsius. Radiation imbalance reduced from about 1 watt per meter square to 0.2 watt per meter square in the present day simulation. And in response to greenhouse gas perturbations, there are large radiation imbalance at the beginning of the simulation, but it reduces by 1 watt per meter square and 2 watt per meter square at the end of simulations. And precipitation increased by 3.8% and 7.1%. So this general picture indicates that our coupled system is slowly approaching to the near equilibrium status. So when you require our data, please keep in mind that earlier period have a large radiation imbalance. For the tropical cyclone study, I used last 20 years of each simulations. Axel showed already, but this movie shows daily surface temperature and 10-meter wind speed. When you look at the surface temperature more closely, such as over crucial current region, you can see little eddies interacting with mean current. And tropical cyclones have its clear eyes in the center, like the snapshot image on the right, and it leaves a long track of cold wake, even after a few days of its passage. So it seems that our model realistically simulate the structure and ocean interaction of the tropical cyclones. In our study, we have 3 major questions. First one is more general question about how does greenhouse warming influence tropical cyclone frequency? And what is the possible explanation for that? And second question is that, are there any changes in TC impacts on the ocean? And if yes, is that simply due to changes in TC itself or upper ocean conditions? Last question is, how will landfalling tropical cyclones change in the future? And this will be an important question for people living in coastal areas. Detection and tracking of the tropical cyclones were applied using a similar approach in the NCAR group, Buckminster et al. 2014, using minimum sea level pressure anomaly, maximum 10-meter wind speed, and distance between storms at 2 different time steps, extrapolation, and surface vorticity, using 6-hourly instantaneous data. Here we have global distribution of the tropical cyclone genesis location and tracks from observation and present-day simulation. As you can see, our model captures general locations of the major genesis locations, including Western North Pacific, South Pacific, Indian Ocean, East Pacific, and Atlantic. But our model significantly underestimates the Atlantic hurricane activities, and that is quite common among the climate models. And our model also slightly overestimates over the central equatorial Pacific due to too strong ITCZ. On average, in the observation, the number of tropical cyclones are 84 per year, which last about 8.5 days and travels more than 3,000 kilometers with the speed of 18 kilometers per hour. Our model slightly underestimates the mean duration, travel distance, and maximum wind speed, and overestimate mean translation speed, but it captures the general pictures of the observed statistics. Following figures shows observed trend of the TC density and changes in TC density in the 2 times CO2 and 4 times CO2 experiment relative to present-day simulations. In the 2 times CO2 experiment, our model simulates a reduction in the tropical cyclone density over the almost entire tropics. There are some increases over the Western North Pacific and North Atlantic, but this reduction is even more pronounced in the 4 times CO2, expanding further into the subtropics. This pattern somehow resembles the observed trend of the TC density, which indicates that global warming signal may have already started to alter the observed trend. Globally, the TC track density decreased by 7% and 32% in the 2 times CO2 and 4 times CO2 experiment. Then what is the possible explanation for that? The first figure shows changes in latitudinal distribution of the PDF for TC tracks, relative humidity at 700 hectopascal, and negative omega at 500 hectopascal. As you can see, there are large reduction in TC frequency at around 10 degrees north and 10 degrees south, and those are very well matched to the reduction in relative humidity and the upward motion. Below 2 figures shows summertime mass stream function in the 2 times CO2 and 4 times CO2 experiment. Contour indicates the mean and shading indicates the difference. As you can see, there are large reductions. There are opposite signs in the equatorial region, indicating that the weakening of the rising branches of the summertime headerly circulation. So this result indicates that reduction in TC frequency can be linked to the large-scale environmental changes, which is also connected to the overall weakening of the rising branches of the summertime headerly circulation. Then let's move to the second question about TC impact on ocean. We defined TC-induced cold waves as the minimum SST anomaly within 5 days of its passage and within 200 kilometer radius. Left figure shows global distribution of the cold wakes by slow-moving tropical cyclones and fast-moving tropical cyclones. As you can see, cold wakes are pronounced for slow-moving tropical cyclones because of their longer residence time, over the 30° north to 30° south. And the magnitude of the cold wake is as large as -5 to -10°C. Previous studies using coarse resolution ocean model, their output shows that the maximum cooling is about -1 to -2°C. So compared to their resolution, compared to their results, our cold wake magnitude is considerably large. And cold wakes by fast-moving tropical cyclones are very weak, with less than 2°C in the tropics, but it's quite large over the western boundary current region, mostly due to the interaction with mesoscale eddies. We further searched some of the observed cold wakes and found that the strongest cooling is as large as -8 and -7, and some of them are even larger than -10°C. So we would like to say that cold wake amplitude from our high-resolution simulations are comparable to observational estimate. And from this result, we could learn that impacts of the ocean resolution, background ocean stratification, and residence time of the tropical cyclones play an important role in determining the magnitude of SST cold wakes. Then what about their future changes? To quantitatively represent the changes in tropical cyclone-induced SST cooling, we calculated annually accumulated SST cooling and its differences. In the below two figures, red color indicates the weakening of the cold wakes, and blue color indicates strengthening of the cold wakes. Although the pattern looks a bit noisy, you can see that in 4 times CO2, most of the subtropical and tropical region have reddish color, which means weakening of the cold wakes, and then higher latitude have a strengthening of the cold wakes. Right figure shows zonal mean SST cold wake by all tropical cyclones, slow-moving tropical cyclones, and fast-moving tropical cyclones. So you can see that most of the contributions in the subtropical region is due to slow-moving tropical cyclones, and then higher latitude is due to fast-moving tropical cyclones. And this tendency is very resembles the changes in TC frequency. So we can definitely say that accumulated SST cooling reduces due to the decreases in TC frequency. Then are there any other contributors, such as upper ocean thermal stratification? To further examine this, we found mixed layer depths and vertical temperature gradient between surface and 100-meter depths, and picked up 2 different regions where they have opposite signals of ocean status. For example, in the western North Pacific, the mixed layer depth becomes shallower and the temperature gradient becomes larger. This condition provides a favorable condition for stronger mixing. On the other hand, Southern Indian Ocean have opposite sign, and it provide a unfavorable condition for strong mixing. If these changes in upper ocean condition influences individual cold wake, the magnitude of cold wake per tropical cyclone would also change. However, we couldn't find any changes in the PDF distribution of the cold wakes in those 2 regions. Therefore, we concluded that the changes in accumulated cooling is unrelated to the changes in upper ocean thermal stratification, Instead, it is simply explained by changes in TC frequency. Lastly, we further investigated changes in landfalling tropical cyclones. This figure shows landfalling locations from observation and 3 experiments. Colors in the experiment indicate the precipitation averaged over 100 kilometer radius. As you can see in the present-day simulation, our model captures the landfalling locations even in the small islands, including maritime continents, Madagascar, and even Hawaii. And as you can see, there are dramatic increases in the precipitation in the landfalling locations. Quantitatively, we identify that wind speed increases by 2% in the 2 times CO2 and 6% in the 4 times CO2 experiment. And precipitation increased by 7.7% per degree Celsius and 9.5% per degree Celsius. Especially these changes in precipitation is much outpacing the one we expected from Clausius-Clapeyron equations, which support the idea that changes in tropical cyclone precipitation is due to the combination between changes in large-scale water vapor, changes in environmental water vapor, and increases in its intensity. Right side figure shows the number of tropical cyclones per its categories, and we found that there are large reductions in weak tropical cyclones from tropical storms to tropical cyclone category 2 range, and there are huge increases in strong tropical cyclones. In other words, in the landfalling locations, there will be less number of tropical cyclones in the future, but once it occurs, we will expect stronger wind and heavy precipitation. That's all of my talk. Let me summarize. We conducted a very high resolution, fully coupled experiment with 3 different levels of fixed greenhouse gas concentration. And I summarized my result in terms of 4 different aspects and compared them with some of the previous studies. Future changes in TC frequency is still controversial issues. So some models expect an increase, but some other models expect the decreases in TC frequency in the future. But most of the recent paper insist that the total number of tropical cyclones will decrease in the future, and our model results are the same. However, the magnitude of decreasing in our 2 times CO2 experiment is smaller than previous studies. And we further identify that these changes in TC frequency is due to the weakening of rising branches of the summertime headerly circulation, and these lead to a reduction in SST cooling. Secondly, strong versus weak tropical cyclone ratio in our model result shows quite a large number compared to previous studies. Lastly, intensity and precipitation. Majority of the models agree that the intensity and precipitation will increase in the future. However, our model result corresponds to the lower end of previous studies. For example, like IPCC reports have 2 to 11% increases, but our 2 times CO2 experiment result have 2% increases in its intensity. And the precipitation rate is even further lower than previous studies. We think this result is because of the capability of our model in resolving air-sea interactions, especially the negative feedbacks from cold waves. And I hope our study can provide a new insight in understanding the mechanisms of the future tropical cyclone changes. And that's it. Thank you for your attention.
Thank you very much, Jongen. We got one comment actually from Justin. He said, Jongen, very nice talk indeed. Your plots of TC density change under CO2 doubling and quadrupling are qualitatively similar to our RCP 8.5 minus 20th century results.
Yeah.
So, any comment back to Justin?
Yeah, thank you for confirming the result.
Okay.
Yeah.
So then we have, let me just move that over, Donghyun Cha asking the question, what about TC landfall changes in the extratropics such as Korea? Is it also increasing?
Oh, that's a very good question. The present changes that I mentioned is over subtropical region. So we removed the area higher than 30 degrees north and higher than 30 degrees south. But when I look at the tropical cyclone density patterns, there are increases in the number. So there are forward movement of the storm tracks. So I think Korea is at the end of like marginal area of that. So in the 2 times CO2 experiment, we expect increases in the number, but rainfall changes, I didn't check over the extratropical region, because if I calculate extratropical region, there is a mixture of extratropical storms effect, so I didn't check. But thank you for the question.
Okay, there are no more questions. Then I think we can close our atmosphere morning session, at least morning in Korea. So again, I would like to thank all the speakers for their contributions today, online and offline. And I would like to make one final announcement before the Korean group goes out for lunch. We will have the online poster session starting at 1 p.m., so which is exactly in 1 hour. So I would really like to encourage all of you participating online or offline to join that poster session. The information, the Zoom link was sent to you yesterday evening, and also if you have not received it, you can go to your registration on the web page and download the Zoom link or click on the Zoom link, and it will automatically guide you to the one of the 3 poster sessions that we have in parallel. So today there are 9 poster presenters, and I think tomorrow we have 12 poster presenters. So please join them. This is going to be a very interesting discussion. And I think the more questions you're able to ask, I think the better it is, the more feedback you can also provide to the early career researchers. Okay, we will meet for the poster session, and the oral session starts again in 2 hours, focusing then on the ocean. Okay, I hope we all have a good lunch, and see you in a bit.
Hello, everyone. I'm Sun Sunni from IBS Center for Crime Physics. I'd like to start this second session. This is for the ocean, and we will have 5 presentations. So we can see all, hopefully I can see the all presenters, speakers, and the 5 presentations, including the sub-major scale eddy activities, tropical cyclone, future changes, air-sea interactions, marine ecosystem, and approach for the reducing the mother bias. So I'd like to introduce first speakers. He is Kelvin Richard from the International Pacific Research Center, University of Hawaii, and he will talk about sub-major scale activity in the ocean, present and future. And please use the Slido for your questions. And hello, Kelvin, can you hear me?
Afternoon, good evening, and good morning. I think that just about covers everybody.
Yes, here. Yes, we can hear you, and let's start your presentations.
Okay. So I'm going to start with an animation that is used quite a lot, that demonstrates that if you have enough resolution, you can resolve the mesoscale eddies in the ocean. This is an animation done by people at NASA. Of course, the word high in high resolution modeling is a relative term. If we increase the resolution now to order 1 kilometer, we see a new class of motions appear. This is an animation done by John Gula. It's a section of the Gulf Stream, and it's showing the appearance of so-called sub-mesoscale motions of the order of a kilometer or so. Here we're looking at the relative vorticity. Hide Sasaki et al. Back in 2014 put this in the context of a basin scale model. Here they're comparing, tenth of a degree OFIS, so that's at 10 kilometers, with a basin scale model at 3 kilometers. This is looking at March and September. Oh, damn, sorry. The upper row is the relative vorticity. The middle row is the vertical component of velocity. And you can see by going to higher resolution, we get much finer scales in these quantities. And we also see that there's a change going from late winter to late summer or early autumn, with a big reduction in that fine scale structure as the mixed layer shallows. So the amount of sub-mesoscale activity has been shown to be very much influenced by the depth of the mixed layer. But the presence of this sub-mesoscale, as we see in the bottom row here, the presence of the sub-mesoscale tends to shallow the mixed layer through restratification events. So putting this in the context of a major theme of this conference, here we have a case where new tools, new observations, new finer scale modeling reveals new phenomena in the ocean, and there have been many studies that have shown that that affects upper ocean physics as well as upper ocean biogeochemistry. So there's a natural conjecture here and a question. The conjecture is that because stratification under global warming decreases the mixed layer depth, the conjecture is that that will lead to a reduction in sub-mesoscale activity, and that reduction in sub-mesoscale activity will change the spatial and temporal structure of things like the vertical heat and nutrient fluxes. And I guess, again, for this meeting is whether or not the presence of the submesoscale means that the change we see caused by global warming, is that change different in any way? Again, I guess associated with another theme of this, this conference, and that is disentangling what is happening. We're not going to go full pelt, and we're not going to run a high resolution Earth system model to look at the impact of the submesoscale. But we're going to start by looking at a simpler system. In particular, we're going to look at an ocean-only model, and the ocean-only model to begin with is POP, run by people at NCAR. That model has been run at 1/10 of a degree, order 10-kilometer horizontal resolution. And in order to compare the future with the present day, we're going to use a time slice method. So for the present day, this global 1/10 of a degree model has been forced with core typical year. So that's a typical year in the life of the planet, which is repeated endlessly. For the future, we're going to take the core forcing, but add on the anomaly associated with the seasonal forcing got from a projection into the 2100s. And here we're using the large ensemble CESM RCP 8.5 projection. So the weather remains the same, but the seasonal variation of winds and heating is going to change. In order to get down to the submesoscale, we're going to look at this regionally. We want to look at it in a reasonably realistic situation. So we're going to downscale from the 1/10 of a degree model to a region in the Northeast Atlantic using ROMs. And that will get us down to a 1.25 kilometer resolution. So just to give a quick impression of what we're seeing, this is from the present day runs. On the left is the mixed layer depth from the 1/10 of a degree POP model. This is in the northeast Atlantic. So in the upper right, you can see the southern tip of Ireland. In the lower right, you can see the northern part of Portugal. There's a lot of variation in the mixed layer depth on a range of scales. But you can see that there's a large scale variation going from relatively shallow in the red to relatively deep in the blue colors. The shallow layers here are being, the mixed layer depth is being influenced by the presence of fresh water advecting in, fresh surface water being advected in from the north. The right-hand panel here shows an insert with the ROMs run. This is done relatively soon after the higher resolution has been switched on. And almost immediately we see the production of much finer scales across the domain. If we look a little bit further into the run, this is looking at the mixed layer depth sometime in February. So the mixed layer depth is close to its deepest. The upper row is showing present climate. The lower row is showing future climate. So in the present climate case with high resolution, as we expect, we see a lot of small scale variations in the mixed layer depth. The middle column is showing supplementary runs where at a slightly higher grid spacing of 4 kilometers, we've increased the lateral diffusion coefficients in order to damp the submesoscale activity. As we will see, it doesn't totally eliminate the submesoscale activity. And if we look on the far right, this is a PDF of mixed layer depths red is the viscous case, blue is the high resolution case. And we can see that there's a reduction in the number of cases where the mixed layer depth is relatively deep, caused presumably by restratification events. The lower row is for the future case, 2100 case. Here we're seeing a reduction overall in the mixed layer depth. There's still relatively fine scale variations in the mixed layer depth. When we look at the PDF has become much narrower, so there's a narrower range of mixed layer depths. And something that I don't quite understand, or don't understand at all, is that at this particular time, we see an increase in the number of shallower mixed layer depths, shown here by the lighter colors. If we look at a time series of the aerial average of the mixed layer depth, so this is averaging the mixed layer depth across the computational domain. Here, blue is the present day, which we're calling run 2000. Red is a 2100 case. So as expected, the mixed layer depth has shallowed quite considerably from a wintertime maximum of around about 200 meters to a wintertime maximum between 50 to 75 meters. The dashed lines here are for the viscous case, so this is where the submesoscale activity is suppressed. And as we expect, without the submesoscale activity, we see a significantly deeper wintertime mixed layer depth. At least in the present case, in the year 2000, in the year 2100, we see that the change is much less. In fact, it's difficult to see much of a change between the viscous and the high resolution case. So in terms of looking at the change associated with global warming, we see that the addition of submesoscale activity has considerably reduced the reduction in the mixed layer depth going from the present day to the future. In the viscous case, when the submesoscale is suppressed, there's a much larger reduction in the mixed layer depth. This slide is showing not only the mixed layer depth, but is also showing the lateral gradient within the mixed layer of buoyancy or density. And I show this to show that there are seasonal variations in the gradient of buoyancy, but those seasonal variations are not related, are out of phase with the variations in the mixed layer depth. So the gradient in lateral gradient in buoyancy is at its maximum during a time when the mixed layer depth is relatively shallow, and the lateral buoyancy gradients are at a minimum when the mixed layer depth is deepest. If we look at spectra, this is for the high resolution runs. Here, the present day case is in the upper row, the future case is in the lower row. Start off by looking at the spectra of vertical kinetic energy. This is looking at it as a function of depth sometime in February. And we see a very distinct separation between vertical motions associated with the mesoscale, here at a scale of around about 100 kilometers, and at the submesoscale. The submesoscale vertical motions are confined to the mixed layer. The horizontal black line here is giving the mean depth of the mixed layer at this particular time. And we see a distinct reduction in the kinetic energy, vertical kinetic energy, going from the present to the future case. The panels to the left of this are the horizontal and vertical kinetic energy as a function of time, taken at a slice going through the middle of the mixed layer. We see a strong seasonal cycle, again, as previous studies have found. There's a strong seasonal cycle in the submesoscale activity, and that submesoscale activity is reduced as we go into the future. But we also note that in the horizontal kinetic energy, which peaks at around about 200 kilometers, that there's also a change in the kinetic energy of the mesoscale. So we see something like a 50% reduction in the energy at the mesoscale. That's in part because of the upscale energy transfer from the submesoscale to the mesoscale. If we look at the viscous run, then the high lateral diffusivities in the run damp the submesoscale, but it doesn't damp it out completely. There's still a signal of submesoscale motions. The scale at which this is happening has now increased somewhat, but again we see a reduction in submesoscale as we go from the present into the future. But the thing I want to point out here is that the change in horizontal kinetic energy is much less. In fact, there's only about a 20% reduction in the mesoscale energy, mesoscale kinetic energy, compared with the 50% reduction when we had the submesoscale activity. So in terms of the presence of submesoscale activity impacting the system, and impacting the change to the system under global warming, we see that there's a difference in the change in the mixed layer depth going between present day and future, but we also see that there's a change in the mesoscale, in that the change in the mesoscale kinetic energy is much greater when we have submesoscale activity. This is looking at the vertical buoyancy flux, W prime, B prime. This is again in February. It shows that the buoyancy flux tends to be positive. The solid lines here are the areal mean of the buoyancy flux. The buoyancy flux, it peaks within the center, towards the center of the mixed layer, and going to zero at the surface and close to the base of the mixed layer itself. And we see a reduction as we go from the present to future case situation. If we look at a time series of the maximum in W prime, B prime, the maximum in the vertical buoyancy flux, then the blue line is for the present day case. The red line is for 2100. We see a strong seasonal cycle in the buoyancy flux in the present day case, peaking in late winter. As we go to the future, we see a reduction in that buoyancy flux, and there's less of a peak in late winter. The dashed lines here are the scaling proposed by Fox, Kemper and friends, who scale the maximum buoyancy flux as the mixed layer depth squared times the buoyancy gradient squared. From idealized experiments, they find that C ranges from a value of about 0.06 to 0.08. The dashed line here is with a constant value, a scaling constant of equal to 0.08. And you can see that the Fox-Kemper scaling does remarkably well, in my opinion. Remember, we have a lot of spatial variation across the domain. So there are a lot of individual events occurring. But in the spatial average of the buoyancy flux, we find that the FFH scaling, as I call it here, reproduces the seasonal variation in the buoyancy flux, peaking in the late winter months, and even picks up some of this monthly variation on a monthly scale of the buoyancy flux. It also captures the reduction when we go into the future in terms of the year 2100, but it over predicts the reduction in the buoyancy flux in the future climate state. There we were looking at the aerial average buoyancy flux. It's instructive to look at spatial variation. So this is looking at the spatial variation of the buoyancy flux on the 15th of February, 2100. Sorry, my trackpad is too sensitive. So on the far left is the buoyancy flux. It's concentrated in fairly narrow regions across the domain. But there are both positive and negative values. If that is filtered spatially, to filter things down to the mesoscale, then the amount of negative values reduces, and you see quite distinct regions where the buoyancy flux is negative and associated with strong buoyancy gradients. Again, we see that the FFH scaling is doing a reasonably good job in that it traces out the regions of high buoyancy flux, both in terms of the instantaneous value and the filtered value. The aerial average here, as we saw in the previous plot, the aerial average here is under-predicted by the FFH scaling by something like a factor of 2. Looking at or deconstructing this FFH scaling in terms of the buoyancy gradient and the mixed layer depth, we find that the spatial variation is very much dominated by spatial variation in the gradient of buoyancy. And indeed, if we replace H in this expression by the aerial average of H, which is the bottom left-hand figure here, we find that it reproduces quite accurately the original FFH scalar. The reason why that's important is that it offers a chance to monitor the submesoscale activity through the use of this FFH scaling. And here I quickly compare 2 times off the islands of Hawaii. This is the gradient of SST squared, the mixed layer depth squared. So this is got from satellite. The mixed layer depth is much coarser and is got from Argo floats. And combined, this gives us the FFH scaling, indicating regions of strong submesoscale activity on the 14th of February. And I picked that particular, so something to take note of is this particular feature here. And we look at this particular time because it was a time when there was a glider in the water. This is that same feature. And the glider arrived at this front just after the 14th of February. And we see that there is indeed a strong frontal feature there. And even an indication that possibly there's a reduction in the mixed layer depth, possibly caused by a restratification caused by instability of that front. So I'll end it there. We see this as a preliminary study, but it does demonstrate that submesoscale activity is affected by climate change, and the presence of submesoscale activity, changes the way that the system changes as we go into the future. Here we found in terms of the mixed layer depth and the mesoscale variability. I put my title slide last. This lists the people involved in this project, both at the University of Hawaii and NCAR, and our sponsors, the NSF. And I will stop there. Thank you very much.
Thank you, Kelvin. We have 3 questions, so I will read it. First question is from Axel. And do we really need to reserve the sub-mesoscale realism? Or can we parameterize it?
Okay, so that's a good question. And we certainly need to look into the impact that having sub-mesoscale in your Earth system, if that is important in the way that the system operates. Can we parameterize it? I demonstrated that this Fox, Kemper, Ferrari, and Hallberg parameterization appears to work reasonably well. My understanding is that people at NCAR will run an eddy resolving model, but with the Fox, Kemper et al. Scaling parameterization for sub-mesoscale activity. It has been put into much coarser resolution models, but I think it's important to resolve the frontal features that we think are going unstable. So hopefully we do not have to resolve the sub-mesoscale, and I think there are promising ways forward in terms of its parameterization. So Axel, you need to run your model with the FFH scaling.
Okay, thank you. And next question is from Sang-Wook Ye. And can you give any comment on why there exist huge differences of sub-mesoscale buoyancy flux during winter time between the present and future time?
Oh, that is because the mixed layer depth is shallower. So the main reason why there's less, if what we're looking at is caused by baroclinic instability within the mixed layer, then that is consistent with the fact that the mixed layer depth has shallowed between the present day and the future climate states.
Okay.
What we did not find, the other thing that goes into that scaling is the lateral buoyancy gradient. And for our simulations, although the lateral buoyancy gradient is a minimum during the wintertime, we did not find a change in the lateral buoyancy gradient between the present day and the future climate. Of course, that may be different in other regions of the globe. So we need to look at both the variation in the mixed layer depth and also changes in the lateral buoyancy gradient.
Okay, thank you. Thank you for Kevin. So let's move on to the next second speakers. Second speaker is Malcolm Robert from the Met Ops Hadley Center, and his talk is on the projected future changes in tropical cyclones using CIMIC 6 high-res MIP. Malcolm, can you hear me?
Yes, thank you very much.
Thank you. Let's start your presentations.
Excuse me. All right. Okay. Shannon. Sorry, it's my simulations on the Mac. Okay, can you see that?
Not yet. Oh, now it is working.
Okay, great. Thank you very much, and thank you for the opportunity to talk to you today, and also thank you for shifting from the session I would have been in to the ocean session to make it a slightly friendlier time zone early morning here in the UK. So I'm going to talk about tropical cyclones in our CMIP6 high-risk MIP ensemble of models, primarily from the work we've done in Primavera in our European project, but also from some other models that have completed the high-risk MIP simulations. As you can see, there's lots of people involved in this work, both from Primavera and from the high-risk MIP community. So I kind of thank all of those people for their contributions. And so what I'm going to do is to talk a little bit about the Primavera project and CMIP6 high-risk MIP. Say something about the assessment of the model tropical cyclone performance in the historic period, and then the projected future changes to 2050, and then make some conclusions and talk a little bit about future work if there's time. So the Primavera project was a European project that finished just a few months ago in July this year. It had 7 modeling groups and 20 institutes around Europe involved. We used the high-risk MIP experiment design to do our simulations, which I'll tell you about in a minute. And then each group ran a kind of low resolution and a high resolution, where here low resolution is of order 100 kilometers and high resolution is order 25 kilometers in the atmosphere and the ocean. And then actually several groups have also either finished or are producing some eddy-rich simulations down to 10th or 12th degree in the ocean, coupled simulations. In Primavera, we wanted to understand the role that horizontal resolution plays in global climate simulation, but also focusing on Europe in particular. And then for CMIP6 high-risk MIP, so this is obviously a community CMIP-driven effort, looking at multi-models, so across as many models as we can, again, to look at the impact of grid spacing on model climate simulation, kind of mean variability and extremes, using both atmosphere only and coupled simulations. And then kind of just to say that because the simulations are high resolution and expensive, we had to make some kind of compromises, some idealizations in order to do them. So we kind of encourage people to do no or minimal tuning between model resolutions, so we could actually see the effect of grid spacing rather than clever tuning or clever other things that people could do. We simplified the aerosol, so we asked people to use a kind of the same aerosol forcing over time, so the models would be more comparable. We had a short spin up for the coupled simulations, which I'll say something about in a minute. We used only one future scenario, SSP 585 at 2050 only. And the simulations compared to the full CMIP6 are relatively short and with relatively few ensemble members. So it's a start, I think, to hopefully do more of this high resolution modeling, but using a common experimental design so we can compare across many models. And I think it's the first time that such a coordinated study of resolution has happened. So the CMIP6 high-risk experimental design is very, very straightforward. So for the atmosphere-only simulations, we started in 1950, and we used historic forcings to 2014, and then the future forcings to 2050. And then here, in order to do this, I had to kind of develop some SST and sea ice data sets to do this future period. So it's not a projection, but it's a way of forcing the models in the same way at 2050 and then seeing what the differences are in the models, be it the resolution or across models. And then for the coupled simulations, we again start in 1950. We have a short 30 to 50 year spin up, and then we kind of continue this control simulation, so the same kind of constant forcing, as well as having a historic kind of changing forcing, again, to 2014 with the future scenario to 2050. And then we can compare these two, the control and the historic, to look at the impact of forcing, understanding that the climate model will still be drifting because of the relatively short spin up. And then I thought this was just interesting to note. So this is the nominal resolutions both in the ocean and the atmosphere from CMIP6 for models that have data in the ESGF archive and for HiResMet. And so you can see that CMIP6, as typical, the ocean resolution is typically 100 kilometers, with maybe a few models beginning to get to 50 and perhaps 25 kilometers. And in the atmosphere, you know, they clump around 100 to 200, 250 kilometers. Whereas in CMIP6, we've been able, again, because of the simplified experiment and the shorter simulations, we can get a few models that are now down into the eddy-rich kind of 10-kilometer regime and be able to look at some of those processes. So I'm not talking about the ocean today, but as Kelvin showed, the ocean is a very interesting aspect of these simulations. But so we have 7 models from the European groups, and I'll use two models from Japan in this study, and then one, the CSM model from the IHES project. And so the resolutions here are ranging in the atmosphere from 200 or so kilometers to 25 kilometers, and in the ocean from 100 kilometers. Most of the high resolution ones are 25, but then there's some at 8 or 10 kilometers. And then there are a bunch of papers that are either out or coming out from this work on tropical cyclones with the data sets. I'm going to talk mostly about the first 2, my papers this year, but there are a bunch of others that are kind of delving more into the processes and understanding some of the processes. So please look out for those. And then just to note in terms of the tropical cyclone diagnostics. So here, when I talk about ACE, I'm actually using 925 hectopascal winds rather than 10-meter winds. And I'm not sure I talk much about intensity, but I tend to use a sea level pressure category for intensity, because as we know, for most models, the 10-meter wind speed is quite biased at these resolutions. There are a couple of models that are exceptional, actually, in that respect. And I used 2 algorithms. So I used Kevin Hodges' track algorithm, which uses vorticity for finding and tracking the tropical cyclones. And I also use Tempest Extremes, which uses sea level pressure. They both have a warm core test, but I don't use any wind threshold. So whatever the criteria comes out, I call a tropical cyclone and I use it. So we can look at the frequency of the tropical cyclones per year. So in the bottom corner here is the observations, and the numbers in each of these pies are the annual frequency in the northern hemisphere and the southern hemisphere, and then the segments of pies are the percentage of those northern hemisphere storms that are in the different basins, so the North Atlantic, Northwest Pacific, East Pacific, Northern Indian, and anywhere else. And the thickness of the pies scales with the observations. So if it's this thick, then it's just right with observations. So there's a few things to take away from this. I think one, for the most part, going from the low resolution to the high resolution, we typically have more tropical cyclones, which is probably what you would anticipate as you increase the resolution. Most models struggle to get this 20 or so % of tropical cyclones in the Atlantic. So you can see the CNRM model is different, better in that regard, but all the others are kind of typically 10 to 15%. And they generally have too many in the Northwest Pacific. So kind of that's one number. So that's using the track algorithm. So then with Tempest Extremes, we see a somewhat different picture, perhaps if I flick between those two, you can see that the numbers are quite different. And in particular, for the low resolution models, we have far fewer tropical cyclones detected with Tempest Extremes. The high resolution is not quite so changed. And this is because Tempest Extremes is using a different way of detecting the tropical cyclones. It's tracking them in a different way, different filtering. So it's not to say that one or the other is better or worse. They're both kind of validated against reanalyses, but they are different. So it's kind of a warning that it's difficult to take the absolute number here, because the absolute number rather depends on which tracking algorithm you're using. So it's just a kind of warning. but it's kind of saying much the same things, that apart from CNRM, you know, we're struggling to get the Atlantic tropical cyclones. And actually, for more of the models here, we're struggling to get the observed frequency. Probably the HGM3 model and the CSM model is good in this regard in terms of the high resolution and perhaps CNRM. So spatially, how do the models do? So here I've looked at the multi-model change in both the frequency, this is track density, between the higher resolution and low resolution ensemble. And in the lower panel is the change in the root mean squared error. So it's kind of the bias in the models, again, at high minus low. So for the top two panels, for the two different algorithms, you see that higher resolution, you get kind of more tropical cyclones pretty much everywhere. And in the lower panel, you can see that for the most part in the blue regions, that's good. So you reduce the bias at high resolution in the regions that are blue. So the Atlantic is generally much better. For the most part, the Eastern Pacific and certainly the southern part of the Northwest Pacific is generally improved. And there are perhaps some regions where you have too many, you now get too many storms at high resolution. But for that, that's for the atmosphere-only models. And then for the couple models, similarly, we get more storms everywhere at the higher resolution in the couple models. And again, the pattern is similar, although now we actually have far too many storms in the Central Pacific in the couple models compared to the observations. So actually we're making that bias worse at high resolution, but we're reducing the bias elsewhere. And this is pretty common bias. It's perhaps dominated by 2 or 3 of the models in this study, and it will be something to understand more fully. I won't dwell on this, but I think this is kind of interesting because it goes to kind of thinking about impacts of the tropical cyclones. And so this is a joint PDF of the TC lifetime minimum mean sea level pressure. So it's when it's at its peak intensity, and the latitude at which it's at its peak intensity. So again, we have observations down in the bottom right corner. And so observations, the tropical cyclones can, evolve to 900 hectopascals or less, but they typically do it at relatively low latitudes. So kind of maybe 10, 15 degrees to 25 or so north. But you can see that for the low resolution models, you don't see that pattern. They're not able to develop, they're not able to deepen that much, but it's much more a kind of linear. They either track northwards too quickly, or they just don't evolve in the tropics. So you wouldn't get the impacts that you might expect to get in the tropics from those. But you can see as we increase the resolution to the higher resolutions, you can see for these atmosphere-only models, for the MRI model, NICAM and a couple of others, you begin to see this kind of belly in the low latitude. So they begin to be able to develop to be deeper tropical cyclones at the right kind of latitudes compared to observations. And the couple model similarly, so again, the CSM model is very good in this regard. It can really deepen the tropical cyclones to very deep, similar to the observations, and it does that at the right kind of latitude. So then you have the potential to have the impacts in the models at the right latitudes compared to low resolution. This is a slight aside, but we did with one model look with 14 ensemble members simulating from 1979 to 2014 and looking at the correlation of the interannual variability against observation. So these are the forced SST runs. And we can see that the skill asymptotes certainly by 14 members, but we can see we get more skill as we increase the model from kind of 130 to 60 kilometers. And then there's some hints, we only could afford to do 5 members at 25 kilometers. There's maybe some hints that there's a little bit more skill to squeeze out at 25 kilometers. But that kind of gives you an idea. You can't really look at the interannual skill with one member because, from one member to another, you get a huge range of the correlation. And so you need to have multiple ensemble members to get a really firm grip on how well your model's doing the interannual variability. Going on to look at the intensity of the storms. Again, this kind of was suggested a little bit earlier, but this is the PDF of the 10-meter wind speeds in this case. And again, we can see the CSM model can kind of get the strongest storms out to 60, 70 meters per second, with a couple of the other models getting into the 50, 60 meters per second region. And then the dashed lines are the low resolution models. So as you would expect, those PDFs are much more crunched up to the low wind speeds. And I'll use this a bit later. So the black here is the observed PDF, and I'll later use the bias between the models and the observations in this wind speed to look at the future change. So in terms of the spatial distribution of the future change, so again, here we have on the left with track and on the right with tempest extremes, with low resolution and with high resolution. These are the changes in the future, so the future period minus the kind of historic period. So we see kind of fairly robustly, we see a reduction in tropical cyclones in the southern hemisphere across most of the basins. The northern hemisphere is more mixed. We don't really see any kind of strong signals in the Atlantic at all. And then there's some hints in the Pacific of perhaps a shift. So we get a reduction in storms further south and perhaps an increase in storms further north. And then maybe this increase in the Central Pacific. And kind of going from low to high resolution makes a little bit of difference, perhaps enhances that signal a little bit. The dots, if you can see them, are where more than half the models agree on the sign of the change. So again, it's kind of mixed, and perhaps using tempest extremes, again, the signal is kind of mixed. There's no obvious clear signal. This may be this dipole signal, but it's not a strong signal in terms of the northern hemisphere. And kind of, again, you can look at one model and trace that from the low resolution couple models all the way to the eddy rich simulation. And you get some idea that the kind of the signal is maybe enhanced as you increase the resolution, you know, maybe because you have more storms, so you get more signal. And some hints of this pattern in the Western North Pacific, but it's kind of noisy, and we only have one member for this latter simulation at the moment. So you have to be a bit careful of drawing conclusions for the future changes. We can summarize that in terms of the different basins. So here we've got 4 different metrics. So the frequency and the ACE with the 2 different algorithms. And again, for the Southern Hemisphere, we see a fairly systematic reduction in activity across most of the basins with kind of all of the metrics. But in the Northern Hemisphere, it's much more mixed. We don't see a kind of particularly strong difference either with resolution or in the different basins or across the different metrics. So they're all kind of for the most part crossing 0. So you couldn't say from this ensemble that there's kind of definite changes in the Northern Hemisphere basins. So then perhaps we could argue that if you want to look at future changes in tropical cyclone wind speed, so this kind of idea in the media and elsewhere that in the future maybe we get less tropical cyclones, but the ones that do develop are able to be stronger because that, you know, there's more energy in the system. So we might expect those tropical cyclones to be more intense, perhaps in terms of wind speed. So here, perhaps we'll kind of concentrate on the couple models. So here I've plotted the root mean squared error from that 10-meter wind speed PDF that I showed earlier. So on the left is where the models have smaller bias compared to that 10-meter wind speed. And the y-axis is the % change in the mean tropical cyclone wind speed, again, in the future period compared to the historic period. And the different symbols are kind of circles are low resolution, triangles are high resolution for the different models, and the filled symbols are with track and the open with tempest extremes. And so you would say, from looking at this, the couple model simulations, that for the models that have the lower bias, so these are in principle the models that can do that spectrum of tropical cyclone intensities, there is again no particularly clear signal as to what will happen in future. So the CSM model suggests maybe a few % increase in the wind speed intensity in the future, but there are models that say there's very little change or even a reduction in that 10-meter wind speed. And the low resolution models are similarly scattered. There's no particularly strong idea that in the future the storms that do develop will be more intense in the future. And indeed, several of our papers for these models, again, have not suggested any particular change in the future in terms of this intensity. There's some indication for precipitation, maybe, that the precipitation might increase. So to summarize, so we've now got a few papers on the assessing these models. I'd say some of them are out, some of them are coming up soon, and we'll hopefully be able to dig a bit more into understanding these changes. The models are obviously a bit idealized from the experimental design, so maybe we're missing, we haven't tuned, we haven't put the models into the right framework for the high resolution, so perhaps we're missing something there. For the most part, we see systematic improvement in the tropical cyclone performance as we increase the resolution. In terms of distribution, apart from the Central Pacific and the couple models, in terms of frequency and intensity, and I'd say with one model at least for the interannual variability. We have to be a bit careful with the tracking algorithm, looking at absolute frequency, but actually the changes both across resolutions and into the future are relatively robust to different algorithms. So you kind of see the similar things if you compare the models with both algorithms. And I'd say the future change is a bit more uncertain. There's no particularly clear, there's perhaps some large scale changes, but it's difficult to say in detail how those changes will play out, both in the spatial changes and the wind speeds. Maybe just to kind of make a few speculations. So we're running a couple more ensemble members of this Eddie Rich simulation, so we can do a little bit of an ensemble there. And hopefully you had a chance to look at some of the posters earlier. So Jeremy's poster and Eduardo's poster have been looking again at these Eddie Rich simulations and perhaps indicating that actually there's some large scale consequences of better representation of things like the Gulf Stream. So that we always kind of think that high resolution improves the mesoscale or the shorter scales. These are actually suggesting that actually doing that can have quite large scale regional impacts in the future changes. And then we're kind of considering now taking this resolution further. So there are some issues with running a 25-kilometer atmosphere and a kind of 10-kilometer ocean in terms of the coupling. And so we're considering we need to maybe increase the atmosphere resolution to a similar resolution to the ocean. And that might give us more of a chance to look at signal to noise issues and perhaps coupling strength and some other things. So that's kind of what we're planning over the next few years. And then happy to take questions. The tropical cyclone tracks from these studies are now all published on the CEDAR data catalog, so they are all available to download. And all of the model data from all of the Primavera simulations is now also all published on ESGF and available to download and use as well. Thank you very much.
Thank you. Thank you very much. And we have 2 questions from Axel. And first one is, do you have any hypothesis as to why the Central Pacific high-resolution performance decreased relative to lower resolution? Is it due to the ITCG or reduced easterly waves?
So that's a very good question. So I was reading your preprint on the tropical cyclones from your models, and actually when I saw that you were suggesting the ITCZ and that being too intense as potentially one of the reasons is definitely something to follow up. That's a really interesting idea. one thing I'd like to do would be to try and look at easterly waves, or look at what mechanisms cause the seeds for the tropical cyclones in that region, to see if that gives some indication as to what the source of that bias is. So I'd be really interested to maybe do some joint work on that, but I think it's something that we do see in a lot of the couple models, and it would be something would be very nice to fix or to improve. Yeah.
Yes, thank you. And next one is, next question is, what is the SYPD simulation year per day of your N512 Orca travelers?
Yes. Not very fast, I think, is the answer to that. So if I'm lucky, I can get 4 or 5 months per day of simulation. So it's going to take me the best part of 9 months to do my other 2 100-year ensemble members. So it's kind of slow. We have a new HPC coming in the next year or 2, and we hope to be able to run those a bit more quickly. But we know our model in particular is not the fastest, so it takes a long time to complete those simulations. Yeah.
Okay, thanks again. Let's move on to next speakers. Next speaker is Bolan Gan from Ocean University of China. And hello, Bolan. Can you hear me?
Hello.
Yeah, her talk is on the mesoscale ocean-atmosphere coupled pathway for decadal variability of crucial extension system. Yeah, please go ahead.
So can you see that?
Can you share
My
your screen? Please play the presentation mode.
It's okay?
Not yet. Please start the slideshow.
Yes, can you see the full screen of my PPT?
No, we cannot see your slide.
Oh, no shoes.
Can you press the F5? Function 5.
F5.
Function.
Screen.
Or okay.
Does this work?
Not yet. I think we can move.
How about this? Okay.
Yeah, it's working.
Okay.
Yeah, please start it.
Yeah.
Thank you.
Thank you. I'm wasting some time. And thank you for providing me the opportunity to report our recent work, recent progress in understanding the jagged variability of the crucial extension system. Our particular goal is to understand the atmospheric response to the crucial extension jagged variability. So let's start. Several studies have documented the dynamically stable and unstable states of the K system. This map illustrates the yearly passes of the crucial and its extension jets. When the K system is in a stable state, such as in 2002 and 2003, the jet path is relatively elongated and quasi-stationary meandering. Meanwhile, both the K jet strength and the southern recircular dry strength are stronger than normal, and also the position of the K jet tends to shift northward. Since 1993, the start of the satellite altimeter period, the crucial extension system has experienced 2 stable and unstable cycles. And this jagged variation of the K system was connected to PDO at first. For instance, during the positive phase of PDO, the intensified erosion load generates negative C-surface height anomalies through Ekman divergence in the eastern North Pacific, and this negative SSC anomaly then propagate westward as baroclinic Rossby waves and finally arrive at the K region in 3 or 4 years to modulate the jet strength. However, other studies have found a connection between the K jagged variation and the North Pacific gyre oscillation, since the North Pacific gyre oscillation also induces the SSH signal along the Ke latitude band. But in fact, it's hard to tell which climate mode plays the most important role, because the PDO and MPGO are linearly correlated since 1990. But in any case, change in the large-scale wind stress curve is required, especially in the eastern part of the Ke latitude band. From the air-sea coupling point of view, the wind forcing may result from the Ke feedback to the atmosphere. But to first propose that the stronger and northward shifted crucial extension drives warmer SST and stronger SAT front in the crucial axial extension region, which favors a northward migration of stone tracks. And this migration of stone tracks causes a zonal dipole structure of wind stress curve with a positive anomaly in the eastern part. So, and you can see the diagram. As the wind force the negative SSH anomalies propagate west into the K region, they shift the K system from the original stable state or to the unstable state, which completes the half of the coupled cycle. So this delayed negative feedback mechanism could be a key to producing the preferred dactyl timescale oscillation of the KE system. But a fundamental question remains on how the atmosphere responds to the KE dactyl variability. Some studies have touched upon this issue, but a divergence exists in the atmospheric response pattern. For instance, an earlier study by Franchino points to a positive NPO-like response pattern with weak surface low over the KOE region and a strong surface high to the north in response to a northward shift of the crucial extension. If focus on the crucial extension SAT front, O'Reilly and Chayer's work suggests that when the KE is less meandering, a stronger SST front is associated with zonal dipole structure of stone tracks. And the large-scale circulation response pattern shows a quadruple anomaly pattern. I will give another two examples which show different results. And here the work by Reverlad shows report that a stronger and northward shifted ST front seems to introduce a northward shift of stone tracks and an equivalent barotropical high over the northwestern basin. But a modeling study shows that in response to the stronger SST front, the stone track response is a zonal dipole structure, which is similar to this earlier work. But in terms of the large-scale atmosphere response, they report that a barotropic high over the northeastern basin. In general, this kind of response pattern seems to not favor a delayed negative feedback for the crucial extension decadal variability. So we address these fundamental questions from the view of ocean mesoscale thermal feedback, which is kind of overlooked by previous studies. We start by identifying the distinct response of atmosphere circulation based on the OI-SAT product and ERE in-train reanalysis during 2002 and 2016 year. This so-called high-res period is chosen because simulation of atmospheric fine structure is found to improve by increasing the prescribed SAT resolution since January 2002. The lagged and maximum covariance analysis is applied to SST anomalies confined in the KE region and the basin-wide SLP anomalies. In particular, ENSO signals has been removed from all atmospheric fields to suppress the tropical influence, which could mix up the response to the KE variability. So this figure shows the squared covariance and correlation of the first MSA mode as a function of time lag in months. Sorry, it's in months. Here the negative lag means SST leading SLP, and the y-axis is the calendar months of SLP anomalies fixed from October to April. The Monte Carlo test results, this is the orange circle, based on 100 random sets, point to that the most coherent and significant squared covariance and correlation occurring at the SST leading January SLP by 2 months. That is to say, SLT anomalies in crucial extension region in November have the most distinct influence on the North Pacific sea level pressure in the following January. Actually, the 2 months lag reflects the persistence of the SLT anomaly from October to January. And they are called SST anomalies in the upstream area. And the warm anomalies along the KE crucial extension and also spreading into the downstream area. The response, the atmospheric response to the SST anomaly shows a strong equivalent barotropic low anomaly extending from the crucial extension region to the northeastern Pacific. What's more interesting is beyond the local response, there is a hemispheric response in the upper troposphere. Here the vector, the green vector, is the anomalous Rossby wave flux, which illustrates how signal propagates downstream. We can clearly see the K region. The K region is a source of wave activity converging into the high anomaly over the Bering Straits. And the wave activity originating from the northeastern basin propagates into the North Atlantic and then forward to Greenland and then southward to Eurasia. If we look at the time coefficients of the November SST, the black curve, and January sea level pressure, the orange curve derived from the corresponding first MSA mode. Both of them actually are highly correlated with the wintertime KE index. The KE index is defined by Motu, which well represents the decadal modulation of the KE system between stable and unstable states. Actually, both the ST and KEI time series have a spectral peak at around 8 years. Therefore, the identified equivalent barotropic low anomaly response is supposed to be a response to decadal ST anomalies, which is driven by the decadal variability of the KE system. So next, we look into the physical processes governing the atmospheric response. We first focus on the stone track response, because stone tracks that or the synaptic eddies have been recognized as a key regulator in the biotropic response of large-scale circulation. This figure shows the V prime at upper level. The prime means the 6-day high-pass filtered quantity, and the V prime T prime at lower level. And the color is the stone track activity response. You can see a well-defined meridian dipole, which indicates the response of stone track activity in both the upper and the lower level is a southward shift. We further assess the feedback of synaptic eddies on low-frequency flow by calculating the geopotential height tendency induced by the convergence of eddy vorticity flux and the eddy heat flux. We also quantified the eddy feedback strength according to this form. The positive eddy feedback strength represent synaptic eddies acting to reinforce anomalous low-frequency flow. Here's the result. The color shading is the geopotential height tendency response, and the control curve is the eddy feedback strength, the EFS. So we can see the anomalous eddy heat flux induces the upside tendencies between the upper and lower troposphere. But meanwhile, the anomalous eddy vorticity flux induces cyclonic tendencies through the entire troposphere as a positive feedback to the mean flow. So in total, the southward shift of stone tracks acts to reinforce the basin scale cyclonic anomaly with a biotropic vertical structure. And if the large magnitude of EFS, especially in the mid and lower troposphere, indicate that the synaptic eddy feedback could be efficient enough to replenish the cyclonic anomaly within a week. So, but we move forward. Why does stone track shift southward? We further analyze the response of synaptic eddy temperature variance, which is proportional to the eddy potential energy. The response pattern at mid-level shows the dipole structure with positive anomalies along the Ke latitude band. Interesting, these positive anomalies are well coincides with the enhanced convective precipitation. However, the large scale precipitation response seems to result from the anomalous cyclonic circulation, which brings the warm, moist air northeastward and the cold, dry air southwestward. Now we consider the eddy potential energy budget, which is a balance between the horizontal transport, the vertical transport, the biokinetic conversion, the eddy conversion, and the diabatic processes. Basically, changing the biokinetic conversion results in the southward shifts of eddy potential energy generation in the upstream region. And the increased diabatic source foster increase in EP generation along the southern flank of in the downstream. And these two sources of EP generation are primarily balanced by conversion to EKE and horizontal transport. If we focus on the downstream area of crucial extension region, where both the added potential energy and convective precipitation are enhanced, the vertical profile of the biogeochemical conversion clearly shows the meridian dipole straddling its climatological way, which locates above the mixed water region. And this changing the biogeochemical conversion is largely balanced by the conversion to the EKE and also the horizontal transport of energy. Changing biogeochemical conversion can be decomposed into a component due to the temperature gradient, horizontal temperature gradient, and the other one component due to the changing in eddy heat flux. Here the contour is the total change in biogeochemical conversion, which is identical to the color in this figure. And here the color shows the change in each component, which reflects the biogeochemicity effect and also the transient heat eddy flux effects. So you can see the change in horizontal temperature gradient primarily contribute to the total change in biogeochemical conversion. Particularly this component shows significant negative anomaly with a larger magnitude than the other one. And this southward shift of this biogeochemical conversion is due to the corresponding change in the meridian temperature gradient. And this dipole of meridian temperature gradient actually can be traced back to be the cause of the mid-level anomalous cooling above the downstream mixed layer water region. Where does the yeah?
Yeah, 3 more minutes.
Okay. So where does the anomaly cooling come from? We diagnose the thermodynamic budget, and over the mixed water region, the warming, basically the warming from diabatic heating at a lower to mid level is largely balanced by the cooling from the vertical transport, and the total horizontal and the vertical transport can be broken down into the main component and eddy component. We can see that both the mean vertical and the horizontal transport contribute to the mid-level cooling. But looking more closely into contribution to the mean transport, there is the strong adiabatic cooling above the downstream mixed layer water region. This pattern is actually very similar to the response pattern of the vertical velocity. It shows an anomalous secondary circulation with upward motion reaching deep into the upper level. And this adiabatic cooling, in fact, induces local cold anomalies, and then mean horizontal circulation advanced cold anomalies poleward and eastward. According to the omega equation, the mean thermal advection is generally considered a major contribution to vertical motion, but the effect of diabatic heating is somewhat overlooked. So here we calculate the Laplacian of the mean thermal advection and the diabatic heating and compare the response pattern with the vertical velocity response. The positive sign in this figure shows upward motion. We can clearly see the response pattern of the diabatic heating Laplacian well aligns with the vertical velocity response, particularly at the lower and mid level. It suggests that the increased diabatic heating confined over the downstream mixed water region facilitates the deep rating upward motion. And we conject that the increased diabatic heating comes from the SST warming. And these two plots display SST anomaly in control and the associated change in turbulent heat flux and the vertical integrated diabatic heating. We can see the warm SST anomalies cause excessive release of latent heat flux to the atmosphere, and the largely increased diabatic heating occurs nearly above the warm SST anomaly, particularly in the K downstream region. If we look at the spatial high-pass filter regression map, which isolates the mesoscale anomalies, changing the surface wind convergence and the vertically integrated water vapor, and as well as the low level vertical velocity and the diabatic heating shows a good correspondence with each other. More importantly, their positive anomalies locate slight downstream of the mesoscale warm SST anomalies. That is to say, the mesoscale SST warming leads to local surface wind convergence and increasing moisture supply as well as diabatic heating, which is consistent with previous studies. The center of warm SST anomalies in the downstream region actually well aligns with the positive SSH anomaly center, likely reflecting the imprints of large warm eddies pinched off from the KE jet. And the wind stress curve response pattern indeed shows positive anomalies over the eastern basin. This is comparably opposite to the forcing pattern of KE stable states. Therefore, we conclude that the oceanic feedback on atmosphere identified here favors a delayed negative feedback loop. To summarize, we plot a diagram here. In the K stable states, its downstream region is populated with mesoscale SST warming, and such warming modifies the atmospheric boundary layer by providing more heat and moisture. And the resultant surface wind convergence and increased diabatic heating facilitates a deep rating upward motion. This upward motion adiabatically occurs the mid-level troposphere, and with such cooling, the baronicity is shifted southward and causes the local storm track to move southward as well. And through the synoptic diabatic conversion, the downstream storm track is shifted southward, and which fosters an equivalent barotropic cyclonical circulation over the eastern basin. And then the wind-driven negative SSH anomaly propagates westward into the KU region, while Biogeochemical raspberry waves in about 4 years. This acts as a delayed negative feedback to trigger an unstable state of the K system, yielding a decadal cycle. So basically, our present results is based on the high resolution satellite product, and also the R analysis. This is a diagnostic result. So I'm not sure if this mechanism is also works in the high resolution model simulation. So we are working on checking the results by using the high resolution model, couple model output. So I stop here. Thank you for listening.
Unfortunately, due to the time limitation, I think we have to move next to speakers. Thanks again, Bolan.
Thank you.
Next speaker is Bro Johnson from Plymouth Marine Laboratory. Can you hear me, Bro?
I can hear you. I'm just going to try to set up my presentation. Can you hear me?
Yes. Can you share your screen?
Yes. Let's see now if I can find it. Let's do it like that. Do you see anything now?
No, not yet.
That is not working?
Yeah, it is working.
Okay.
We can see.
It is working? Great. Thank you.
Thank you.
So, my name is Bro Johnson, and I am, as you said, at Plymouth Marine Laboratory in the UK. Thank you so much for inviting me. My talk will be a little bit from the left field because I'm somewhere between modeling and observations, and I'm also a biologist versus a physical oceanographer. So it tends to be that I'm talking to half of the people, or I'm either a biologist among physical oceanographers or the physical oceanographer among biologists. And everyone thinks I'm kind of wrong in what I'm saying, but we'll see how this works. As we know, there are many different spatial and temporal scales in the geophysical systems. And when we are talking about climate change and these questions, we're normally thinking about these scales, like 100 kilometers and larger, and maybe year and bigger. So, and once again, I should say that I know that I'm a little bit preaching to the choir since everyone here is into high resolution models, etc. But I'm trying to motivate other people to why our work is, or your work is important. So we know that these are the scales that we're interested in. And normally most model and satellite studies end up working in these in this domain of temporal and spatial scales. But the problem is that if we're looking at biological processes, which is a very important factor to understand how the future climate will change because of the uptake of carbon dioxide, etc., etc., etc. These processes are normally acting on much shorter timescales. So the question is, how can we combine this? How can we move between these domains of temporal and spatial scales? And these high resolution models allows us to get the modeling working, but how do we work with how do we connect that to the biological system, and especially with observations? And just to make sure that we're on the same page, I'm going to go through a couple of biological terms, and one is gross primary production. That is basically the raw assimilation of carbon by phytoplankton. So that's basically you're revving the engine without driving. That's how fast the phytoplankton can assimilate carbon. Net primary production is gross primary production minus their own respiration. So that means that the phytoplankton needs to use up some of the energy that they've assimilated to survive. And then when we include that into the budget, we get net primary production. And then we have growth rate, which is basically just how fast the phytoplankton can divide. So this is de-dimensionalized and de-dimensionalized NPP. So what that gives us is an understanding of basically how fast the system is churning without really knowing the biomass, so needing to know the biomass. And then we have another term that is net community production, which is basically what is the aggregation of carbon in an ecosystem. NCP is really important for carbon uptake, because that tells us how much an ecosystem can aggregate carbon and draw it down from the atmosphere. And we can estimate primary production from satellite by, if we know light, temperature, and nutrients, and if we can, because light, temperature, nutrients can tell us something about the growth rate. And then if we have the biomass, we can get primary production. So this is kind of a very basic and very important way that we have been assessing the global productivity of the ocean. And this is data that's always been used to a very high degree to assess and to tune the biogeochemical models that are being used today. And this is how it normally looks like. This is how we think of it. It's like, it's very nice, very smooth. We have areas with high production and areas with low production. So this is coming from this image comes from satellite, and it's based on an emission mean. So it's about 20 years of data. Everything is very nice and very smooth, and everyone's happy. And we of course know that this is not how the world works, because the world is complicated. We have these events coming in and out. We have a very stochastic system. So it's much more complicated than we think of it when we have these large scale averages. So what I've been working on, what I've been thinking about is like, how can I better quantify and depict this variability in the systems? And the reason why this is problematic is, if we look at from a modeling perspective, is that if we compare a model with a satellite, it looks something like this. So to the left side here, we have an output from the GFGL Topaz model. It's just a model year 2005, 10, 16, and it's based on a core 2 forcing. To the right, and this is sea surface temperature. And then to the right, you see the equivalent image from a satellite image. And I've been very afraid of changing these images, even if they're a couple of years old, because they look so great. I mean, I'm really impressed with how well this model output looks like. You can see, the large structures extremely well. But if you look on the coast of California, you see that the large scale model is completely missing the upwelling. So we're missing small scale structures. And that is quite important if we look at chlorophyll. So this is on the left, once again, the model output, onto the right, the satellite output, satellite data. And we can see that once again, the large scale looks really nice. We see the gradients and big structures fine, but we miss this whole upwelling event by the coast. And a lot of what the fisheries that we are surviving on, and a lot of the biological systems that we are interested in are near coast, are connected to these upwelling events. So we need to be able to understand these in a modeling perspective too. And of course, this is where higher resolution model comes in as a very important tool. And one of the reasons why this is a problem, and this is coming back to what Kelvin said, talked about in his extremely interesting talk, is that, well, if we think about vertical transport in models, we have tradition in the coarse models, everything is diffusion. We have nutrients at depth that are diffused up into the sunlit area where we get biologic production, which is a way of thinking that makes sense from long time scales and very large areas. But in reality, what we find is that processes are much more advective. So we have something is happening, and we're pushing up nutrients because of this. This can be a submesoscale, this can be eddy, or it can be a frontal system, or whatever. There are many different things that can make this happen. But first of all, it's much more effective, and it's also much less. It's much more episodic. It happens much more rarely, and vice versa. We can have a push down of material that is happening in a much less diffusive way. And this is an image that looks kind of, this is the terrible version of what Kelvin showed. But basically what we did was we took quarter of a degree run of ECHO, which is a state estimate out of MIT and JPL primarily. And we looked at the density, and then we just ran a process model south of Iceland. So this is Amala Mahadevan's a 1 kilometer process model called PSOM. And so you can see that slice in the middle. That is just how this high resolution model compares to the more coarse resolution model when it comes to density. So you can see that we have much more variability in the density structure, both in vertical and in horizontal. So this kind of indicates that we see this much more varying system and much more of episodic events happening. And we wanted to find a way of estimating this in as a quantitative or as a realistic way as possible. I mean, there are hundreds of different issues with this approach, but we try to not add too many assumptions. And the way we do that is by combining satellite data and physical fields, because what we thought was that the best way we can estimate how the biology works is from satellite data. And there are many issues with biogeochemical models, but we hope that we can get the physical fields as well as possible. And we're also assuming non-steady state. So that often you're thinking that you have a stock of phytoplankton, for example, and you use this stock to estimate all the fluxes. But we're saying that the change in stock is what is driving, that is a better indicator of what the fluxes are. And that is not in any way a non-controversial assumption, but it's just an assumption we're working with. And the way we do this is that we're just seeding a bunch of vertical particles in a velocity field. So here we have day 1, 2, 3, 4, a number of days. I can't count, as you can see, since I had 2 day 4. And then we attach these vertical satellite images, as vertical particle positions with satellite data. So in this case, we got data at day 1, 4, and 5. And that way we can calculate the change in satellite chlorophyll from day 1 to day 4 to day 5. And we can do that for day 3. So in this case, we can get a change of rate at day 3. And doing this for one particle makes no sense because the statistical significance is extremely low. But since we're playing with computers, we can do this with as many particle tracks as we want, and we can create a statistical average of what the changes are. So this way, we can create an approximation or a proxy for the rate of change of chlorophyll in this case. And doing so, we can estimate the biological production using the satellite observation in the Lagrangian framework. And when we do this for daily to weekly estimates, so we started doing this for daily to weekly estimates, and we did a case study in the South California Bight, because there we have pretty nice velocity fields that have a bit of data assimilation from ROMs. It was run in the operational mode. These fields are not around anymore, which is a very interesting question when you work with models, is that you do all this work and then suddenly money runs out somewhere and you have to figure out how to recoup the data. So, well, that's another question. But yes, it's run in operational mode. It was run in operational mode. They did a lot of data assimilation. It was a 1 kilometer resolution, and we were using 6 hourly snapshots. And then we used a satellite field of chlorophyll and sea surface temperature from generated by Matti Karhu with a 1 kilometer resolution. It's a blended product, so he took all the satellite, or he takes all the satellite products that are available, because there's several instruments flying. And it's really well validated for this area. And then I'm using a particle tracking code called TrackMass that I've been working on with for a very long time, which is an offline particle tracking package that can be used with very nice subgrid interpolation, we think. And this code can be run basically on any model fields around, as long as it's a finite difference. Yes. And the runs we've done is we've done it by locking the particle to the surface, and this is all run on a desktop. And doing that, we can actually estimate when we have increases and decreases in chlorophyll. So basically here, the red patches you can see popping up indicates that we have biological production. The blue ones that indicates a decrease in chlorophyll can be due to many different processes. It can be to vertical export, it can be dilution, it can be grazing, etc., etc. So we don't really know why the chlorophyll is decreasing, but we assume that when we see the chlorophyll to increase, that is because the bugs are growing. So this is really interesting. And if we do an average of this, we see something like this. So this is the California bite. You basically have Los Angeles at the top and San Diego at the bottom. This is the west, and it's the west coast of the United States. And you can see these red cells between the islands and in the south. So this indicates that this is persistent areas where you have increase in chlorophyll or biologic production. If we compare this, so this is the mean change over a year. If we compare this mean change of chlorophyll with the mean change of sea surface temperature, we see that these areas are areas we also see persistent cooling. So what we're saying here is that we can really connect these cooling areas, which suggest upwelling, with increased productivity. So this is a little bit of a trying to show that our method works. We can connect physical structures with biological structures in a way that is very nice. And this is an area that has a permanent study area for the NSF. It's called LTER, or Long-Term Ecological Research Area. And they've spent a tremendous amount of effort doing research here, but even they hadn't really picked up on these increased productivity regions. So it's pretty, we like these results. But at the same time, if you look at this image or this movie, you saw that these increases were kind of happening sometimes here and there. It wasn't a very consistent production. So it looks like the system is driven by episodic events. And we wanted to see what that meant. And to do that, we wanted to create a metric that we could use to quantify the level of episodicity. And to do that, we just took, basically what we did was that you take any kind of field with a property, and you convert it to a vector, and you sort it. So you have the highest value first and the lowest value last. And you create a cumulative distribution of these values. The slope of this curve will indicate how important rare events are. So just using a bunch of random values, we can show here that the green here is just taking random values from a rectangular distribution. The red is from a normal distribution, and the blue are from a log normal distribution. And you can see that the slope is getting steeper and steeper the more you have few values that are important, few high values, rare values that are important. So basically, a log normal distribution has a much longer tail. If we compare this with sea surface temperature from this model run that I've just described, we get a cumulative distribution that looks pretty much as we would expect from between log normal and normal distribution. If we do this with chlorophyll instead, we get a much steeper curve. So this indicates that rare episodic events are much more important than earlier thought when it comes to understanding these systems. So basically, we don't have this progressive constant production. We still instead we have just like episodic event pushing or being very, very, very important. And the reason why that is important is an important factor is that then frequencies of these rare events might be as important as the means. So I think about this. I normally use compare this to heat strokes. Basically, if you are the first time we knew that biology or climate change were affecting human lives was because we had an increase of heat strokes in France or in Central Europe, especially in France, in the 90s. And basically what they did was that they looked at extreme heat events and they looked at the number of heat strokes they saw. And they could see that the number of extreme heat events was going up, and they could connect that to climate change. And they saw that these heat events made people die. What we do with biology traditionally is a little bit like trying to correlate the average temperature in July to number of heat strokes. It's not the average temperature that's driving the heat strokes, it's the extreme heat events. It's the same thing here. It might not be the average chlorophyll concentration that is driving the productivity or driving the ecological system. It's these frequencies. So that means that we need to be able to model the processes that are generating these rare events. And that's where high resolution models have a tremendous potential. I'm just going to talk a little bit of another project we're doing, where we expanded this into the hourly domain, because when you have very high resolution models, you also want to look at biology with very high resolution, both in time and space, and that's where things get complicated. So we used Gochu, which is a Korean satellite, which is quite brilliant. This data is the only existing kind of satellite data from a geostationary imager. So it's hourly resolution. You get about 8 images per day, and it's centered over Korea in the Eastern Pacific. And we've been looked at 2016. And this is just the domain and the number of values we have for 2016. And what we did was that we used the Eulerian frame to calculate hourly changes. So we just looked at how chlorophyll changed from 1 hour to another, because we assumed that advection is not a big factor on those short timescales. And we can that way we can show how the daily means of hourly change is changing over the season. So here you have 4 different seasons, and you can see where you have high production on hourly timescales and low production. But even more so, if we take this whole system, this whole domain, we can look at what the average change of chlorophyll is between different hours, like early on to late in the day. And what we see is that we actually see a decrease in chlorophyll in the morning and an increase in the evening. So it takes the biological system a little bit of time to kind of spin up before they can start to get net producing. So there is a pretty significant importance of when you're looking at the system, or like this diurnal cycle is actually really, really important to understand. And that means that we can't just take our current biogeochemical models and scale them and just run them in a higher and higher resolution without including this new part of the physiology, because all our biogeochemical models today are tuned and scaled to work really well over monthly scales or annual scales. But when we're pushing it down, especially down into the diurnal scales, we need to understand the biology much, much better. And there is a lot of work that has started doing that, which is really interesting. But that is something to think about. And then we are expanding this to also looking at daily changes in this data set and using, in this case, we need to use a Lagrangian frame just because the effect of physics is so large. And what we can see is that, so this is basically a measurement of this NPP in the Eastern Sea over different seasons. And what we see is that if we're taking, so what you see here is that each group of bars is for one pastime, or for one time over the day. So if we look at the daily changes of NPP, and we're using the change from 9:30 in the morning, day 2, minus 9:30 in the morning, day 1, we get a different result in the spring than if we're looking at the change from day 2, 3:30 to day 3, 4:30. So there's a lot of dynamics here that is important, and we need to better understand. So once again, this is early results, and we just submitted it for publication. So we haven't gotten the reviews back. We'll see what the reviewers think about it. But it indicates that there is a lot of complexity with the biology in that sense. So basically, we see a lot of, yes?
3 more minutes.
Yeah, I'm wrapping up.
Yeah.
Yep, thank you. So we see a lot of diurnal variability in the productivity on both daily, like if we think about it from a daily perspective and when we think about it from an hourly perspective. And that is something that is really interesting to explore further. Another product, another instrument that we hope to fly, we have, it's funded, but they're still negotiating the contracts, is Glimmer, which is a NASA instrument that would be a geostationary imager of over the Gulf of Mexico. So this could be another really nice platform to use to better understand how biology and physics interact. And the launch date is 2027. So I'm kind of just flagging a little bit about it. I just want to finish with this image. This just shows how complex and important this is, because what you see here is, this is the north of Norway. And what you see here is 5 different phytoplankton communities blooming at the same time. So it's a really, for me as a biologist or half biologist, it's a really good indication of the complexities that the interaction between physics and biology does. Because we normally would assume that only one phytoplankton group would bloom. But in this case, we can see that there's a tremendous amount of wealth when we start to push into the high resolution domain. So I want to take, this is work we've done with a bunch of people and was primarily funded by NASA. And I want to thank them all. And thank you so much for listening. And I hope it made some kind of sense at least.
Thank you. Yes, and we have 3 questions. First one is from Noel. Offshore primary productivity was not well related to SST far offshore in the California Bight. Can you explain how the approach works here?
Yeah, so SST in this case is just a proxy or an indicator for upwelling. So depending on where you are in the ocean, there are different processes that are controlling it. And in this case, it's only really near the coast that you get SST to be that kind of proxy. If you're further out, you might not have a large difference in temperature between the surface and the deeper parts of the ocean. So it might be that what is controlling the mixing or vertical transport of nutrients or salinity instead. In that case, we won't see it. So this is a good question. It's really important to always think about the specificity and why do we have these relationships. It's not that we have a general understanding of everything, and that's always a challenge. That we need to know as much as possible about the domain to be able to say something about this. I'm just using SST and chlorophyll here near the coast because it makes sense just there.
Thank you. And next one is from Axel. Do you think that ecosystems are completely controlled by the physics, or is internal marine ecosystem variability relevant? Any ecosystem multiple equilibria?
It's a very good question. It's a really, really hard question to answer because, in principle, yes, there are a lot of biological controls and there's a lot of biological complexity that we need to bring in, and to 100%, that is a primary first order question to work on. at the same time, we are talking about a highly, highly dynamical system. So if you're looking at one point in the ocean at one point in time, everything you see there came from somewhere else, and it might have come from hundreds of miles away in a couple of days or a couple of weeks. So there is this dynamical equilibria between physics and biology that is really, really complicated. If you're at one place at one time, the upstream conditions are probably really, really important. But at the same time, the organism might have evolved to come to that point at some, it's just very complex. We have a couple of papers about this, about just the question of connectivity in the surface ocean. And what we find with these studies is that the fastest you can get from one part in the ocean to another part of the ocean, like any part in the oceans, is about 5 to 6 years. So the connectivity times are way, way, way faster than you think about it if you look at the absolute fastest pathways. But what that means is that we need to think about this in a much more, it's much more complicated than just thinking of it as a local community and the dynamics there. But yeah, no, that is also definitely important.
Okay. We have some more questions, but I just read it. Are you sure that?
Sure.
Are you sure that chlorophyll diurnal cycle at coastal region are well reserved?
No, I'm not sure about anything. This is the modeling. We're using satellite data and model work. We need to get more observations. We have some in situ cruises that have gone there. We're looking at. There are definitely questions. We've worked really hard to remove other factors. So we removed water masses, so we have a lot of suspension. We basically removed the entire yellow river plume, etc., etc. So we try to be as conservative as possible where we think that we are picking up a diurnal cycle. There's a lot of physiology included in this. So you have what's called non-chemical photochemical quenching. Basically, the bugs, the phytoplankton, hides their chlorophyll to not get burned by the sun, and that is something that we are not compensating for. So there's definitely different theories and ways of thinking about this, but with that said, we do see a pretty strong signal, and we think it is coming to by the first order from productivity. Read the paper when it comes out, and you'll see a little bit more how we have tried to figure these things out. But yes, no, I'm not sure about it. I've definitely could see that there are other issues around there.
Okay, thank you, bro.
Thank you so much.
Yeah. Let's move on to the last speakers. Last speaker is Noel Kniside from the Biogeochemical Center for Climate Research. And can you hear me, Noel? His talk is on the approaches to reduce model biases and initial high-resolution climate models. And
I can hear you, but I lost your picture, yeah.
You can hear me, right?
Yes.
Yes. And can you share your screen?
I think I have shared my screen.
We cannot see your slide yet. Yeah, it is working now. Please go ahead.
So you can see my first slide?
Yes.
Okay. So, well, thank you very much for inviting me to this very interesting conference. I'm afraid because of the time I haven't caught much of it, being here in Bergen, which you can see here at on the figure here. So it was very nice to see in the previous talk that, talking about the phytoplankton variability in the Barents Sea, northern Norway region. I'm not going to talk about biogeochemistry related things here, although we're very interested in that in Bergen as well. What I'd like to talk to you about today is about approaches to reduce model biases and to how to initialize high resolution climate models. So there will be two parts to this talk. One will be sort of the more things fitting to this conference, the use of high resolution models, and the other is an alternative way, which we refer to as supermodeling, which is an interactive ensemble for reducing model biases. So you can see the main contributors to the presentation here: Fei Li, Sebastian Barthelemy, Francois Connellion, Shu Wang, and Ingo Bethke. So I'd just like to start off by making sure that you know that a lot of the figures that you will see here are basically from them. So I have one slide of motivation, and it's, here's the CMIP5, multi-model mean sea surface temperature error or bias. I couldn't find the CMIP6 one from a very quick look, but I'm pretty sure that we would see a very similar bias pattern in the SST and also in rainfall if we looked at it. So you can see that there's a problem in the lower resolution models. So whether this problem, we know to some extent that this problem disappears as we go to high resolution models. So that's one of the key motivations to go to high resolution models, but we're also interested to see how we can deal with reduce these errors using standard resolution models. So we see that the biases are larger than the signals we often analyze or predict. And so for the purposes of this presentation, I'm going to talk a lot about prediction, since that's one of my key interests here. So, these biases are a big problem when it comes to making climate predictions. So in Norway, we are developing what we refer to as the Norwegian climate prediction model, and I want to just point out what this model is. So the current version of the Norwegian Earth System model is based on NOISM, which is at the moment in a 2-degree resolution for the atmosphere and 1-degree resolution for the ocean. We use the ensemble Kalman filter data simulation, which is typically we use 30 ensemble members for computing the covariances. And so this is the first challenge here, and one of the things that I will deal with is discuss how to compute covariances with high resolution models where it's challenging to run large ensembles. And with the current setup, we've been assimilating a variety of variables from the ocean, so sea surface temperature and ocean hydrographic data. We've been assimilating sea ice data, and we've been doing this both in a weakly and strongly coupled modes in the ocean and sea ice components. You can see a few references there if you're interested for further reading. So what I'd like to talk about today is mostly the new developments. So we are working on development of a high resolution version of the Norwegian climate prediction model. So for us, it's not the type of resolutions that you've been discussing here. So we are a little bit more modest. We've been moving from a 1-degree model to a 1/4 degree. So this is the sort of thing that we are capable of doing in Norway at the moment. And I'd like to mostly talk about the data assimilation scheme that we're developing. And the second part of the talk will deal with the supermodel that we've been developing, which is based on the Norwegian Earth System model, CSM, and MPISM. So a combination or interactive ensemble of these 3 Earth System models. So here's just a first result from the high resolution version of the Norwegian Earth System model that we've been developing. And the model, as I said, is a 1/4 degree resolution globally in ocean and atmosphere. We've done now more than 100 years of simulation. And in terms of speed, we can achieve around 5 models per year on the supercomputers that we have available to us in Norway, from Sigma 2, the high performance computing infrastructure here. And we're currently working on tuning this model further. So hopefully you'll have seen some of these results earlier today in a poster presented by Fei Li. So I have just this one slide. And here I'm showing you on the top the bias, the sea surface temperature bias from the high resolution model, and on the lower panel the sea surface temperature bias from our standard version of the model that we've been using in climate prediction. So you can see there's large biases, but there's also some improvements. You can see here, particularly in the tropical Atlantic, one of the large biases that is common to the to standard climate resolution models, standard to the current versions of climate models, is here in the southeastern tropical Atlantic. In our high resolution model, it is largely gone, and we assume that this is related to improvements in the atmospheric resolution based on previous work. And but we do see that there's particularly problematic for us here in the northern region. We have we actually have much larger sea surface temperature biases, and so there's a challenge here to work further and to tune the model and to understand what is the problems with the biases. So now let me talk a little bit about how we're dealing with the data assimilation problem. So we've been working in parallel with the development of a system for high resolution initialization. So first of all, just explain a few things about our current data assimilation method. It's the deterministic, we use the deterministic ensemble Kalman filter formulation. And here's just I don't want to show too many equations, but it's quite important to understand what we will refer to as covariance hybridization, or hybridization of the covariance matrix. So in data assimilation, we have here the analysis. So this is what we want to produce after the data assimilation step. We have the forecast from the model, which is here XF. And then we have the update, which is here the last term here on the right. And you have the Kalman gain, which I'll explain just in a minute. And you have the difference between the observations here, D, and the forecast. And so the Kalman gain is the amount by which you update the forecast based on confidence in the observation in the observations and model. And this comes through the Kalman gain, which is formulated here in terms of I only want to point, well, you have here the background error covariance from the observations and the model, but I want to point out here that the Kalman gain, a very important component of the Kalman gain here is the background error covariance matrix, which we compute here from an ensemble. In our case, it is from 30 ensemble members. So it's the covariance that relates different quantities in the model to each other, so that we can know how to, if we have an observation in, say, for example, in sea surface temperature, we could update the subsurface ocean conditions based on the covariance. So if there's errors in this covariance, you will not be able to update consistently other parts of the system. So it's a big challenge when it comes to high resolution models because of the number of ensemble members. It's not possible to run a lot of these, and so the statistics of the covariance matrix will be compromised. So one approach which we've been testing here is covariance hybridization, which is to enhance the statistics so that we can better estimate the covariance matrix. And here's the equation essentially that we're implementing, and this is for the background error covariance. So this is the forecasted background error covariance, and so we compose it of two estimates of the covariance matrix, which are shown here on the right. One is from a high resolution model ensemble, from a smaller ensemble of a high resolution model. And the second term is from a cheaper model, either from a model that we've already run. So not, in this case, it's not cheaper, but it's not cheaper during the simulation. So it's a static ensemble of a high resolution model. Or secondly, we might choose to run an ensemble of a lower resolution model, and it'll be dynamic in this case. And so you're getting a combination of the covariance matrix of the high resolution expensive model and the lower resolution cheaper model, and you have this weighting factor, which we can optimize to achieve more accurate representation of the error covariance matrix. So that's essentially what we're trying to do and what we've been doing. And I'll just show you two slides on the results. So I just wanted to explain basically the method, and if you're interested, you can, this paper is not published, but you can get in touch with us, and we'll be able to, Sebastian Barthelemy or Francois Conlion will be able to explain to you exactly what has been done. So here, we've tested this approach in a quasi-geostrophic model and also in perfect reanalysis experiments with the Norwegian climate prediction model and a low resolution model. So first, here's the results from testing with a quasi-geostrophic model. So essentially, a variety of simulations have been done with a quasi-geostrophic model in a low and a high resolution version of the model. And then we have looked at how these hybridization methods can be used to improve, or in this case, reduce the RMS error of the reanalysis. The RMS error is plotted here on this axis here, the y-axis. And the first point that I show you here is from the ensemble optimal interpolation. So this is basically using the covariance matrix from a single simulation of the model. So it's the cheapest thing that you can do, and it has the largest RMS error. The black line on this graph is the ensemble Kalman filter. And on this bottom axis, you can see essentially the computational cost associated with that. And it's not in terms, I guess it's in terms of ensemble members here. So you can study from 20 to 30 and so on. Actually, I don't think it is the ensemble size. But it shows you the computational cost of the different versions of the ensemble Kalman filter that we've been implementing. So as you increase the ensemble size, you become more expensive and you reduce the RMS error. That's what this black line is showing. And all the other curves on here are different methods for the hybridization. The red one is, for example, the dual resolution hybridization. And so you can see if you use a low resolution version of the model, a larger ensemble of a low resolution version of the model, and you combine it with a smaller ensemble of a high resolution model, you can actually achieve a similar RMS error, but for half the cost. So you can see that this is a smarter way to do it. So you can see that there's a variety of ways in which you could combine these, or you could hybridize the covariance matrix to achieve either much cheaper estimate of much cheaper but equally accurate estimate of the covariance matrix, or you could use the same computational power and reduce the RMS error, as you can see if you go vertically on this graph. So how does that work in a real context, or a real climate modeling context? So we have been testing this in the NOR-CPM in a standard resolution. We've been using 30 dynamical members and 315 static members from a pre-industrial control simulation. And at the moment, we've done 10 years of a simulation of SST data in a perfect model experiments. So this is still rather preliminary. It seems that in an online talk, the time seems to run quite quickly as well, so I better speed up a little bit. So the Norwegian climate prediction, so here you just see one graph in which we use alpha equals 0, so that is no hybridization. And on the right, you see alpha equals 0.2, so it's a partial hybridization. And we're looking here at the temperature error at 1500 meters to 2500 meters. And it's the mean absolute error percentage reduction compared to the free run. And first of all, I'd like to point out that if we looked at the global metrics, we actually see that the hybridization is quite similar to the ensemble Kalman filter in terms of the global metrics. So first, that is a little bit disappointing, that we would have expected a greater improvement, and we're looking a little bit more into that. But we do see, which you see on the bottom graphs, that hybridization actually is able to mitigate a large error that we know exists in our ensemble Kalman filter, which is here in the North Atlantic at lower levels. So we can see here, compared to the free run, actually we degrade the simulation, and we believe that's because of errors in the covariance matrix. As we do the hybridization, we basically remove this error. Unfortunately, we don't really get an improvement. So let me just now, so I think we're doing some very interesting work, or some work that may interest many of you there in this methods for initializing high resolution models. And I'd encourage you to get in touch with Sebastian or Francois if you want further details on this. Now let me talk a little bit about what we refer to as supermodeling. So first, in a standard on what we're doing, for example, in seasonal predictions these days, or climate predictions in general, or in the IPCC context, we run independent models, and we combine the outputs. Often we may use a weighted ensemble, and these days there's even more advanced methods for combining models based on machine learning or artificial intelligence methods. So what we are proposing is to develop a model in which we combine the models as they run, so that there's an interactive combination of these models. And we learn the connections between these models from observations. So in order to best reproduce the observations. And the advantage here is that we're able to reduce errors or compensate errors at an early stage of their development. And so that through the nonlinearity of the climate system, we're able to achieve greater gains. So there's a variety of things that we've been working on this approach for a number of years as a group. So Gregory Dwayne is actually the initiator of these ideas. We've been working with low order systems. We've been working with atmospheric general circulation models. You can see a few references. We've been working also with coupled general circulation models. And now we're working with state-of-the-art Earth system models. So I'll just show you a slide based on this paper from Maolin Shen, 2016, which is from a coupled general circulation model. And then I'll show you some initial results from what we're doing with Earth system models. And I'd just also like to point out that there's a sort of a relatively similar approach to what we're doing now with the Earth system models that has been developed independently by Hailiang Du and Lenny Smith, and it's called Cross-Pollination in Time 2. So, as I pointed out, it's interesting to be able to compensate errors at an early stage of their development, because you can get, through the nonlinearity of the system, you're able to achieve error reductions that you may not expect. And so here you see from our coarse resolution experiments with an earlier version of the MPISM model, the simulated rainfall of the tropical Pacific. So you have how we're able to improve the structure of the simulated precipitation in the tropical Pacific. So on the left you see the observed precipitation climatology. In the middle panel you see the result of the combined two atmospheric models with different convection schemes to one ocean model, in which the combination is of the air-sea fluxes are optimally combined or optimally weighted. And in the right you see the independent average of these two models, so the standard ensemble. So in the independent average of the models run separately, you have the common double ITCZ error. After running the models in this interactive ensemble with optimal weights, so this earlier version of the supermodel, we're able to dramatically change the structure of the rainfall in the tropical Pacific. So we're able, to a certain extent, to mitigate the double ITCZ error. The model still has a large rainfall or precipitation errors, but you have to remember that it's a relatively coarse resolution version of the model. So we were very excited by this result, by the fact that we're able to change the structure of the errors dramatically. And so we're working further on these approaches. So now we're working with Earth system models. We're combining three different Earth system models, the MPISM, the NOISM, and the CESM. And we're connecting or aiming to connect the atmospheric models together and the ocean models interactively. At this stage, we've managed to connect ocean models quite well. We've had some success in connecting atmospheric models, but I'm not going to show you results from this in this presentation. So the current approach that we're doing, also based on data assimilation, is to generate a pseudo observations of the sea surface temperature from the three different models, and to assimilate this sea surface temperature into those three models at, in this case, it's at monthly time step. And we've been looking at several different approaches to train this this pseudo observation, so a weighted combination of the three different sea surface temperatures of the models. And I'll just show you a few slides based on 25 years of simulations from one of these methods for training, which is based on short-term forecasts, so 1 month long forecasts of the model. So the left figure is first I would like to show you the sea surface temperature bias. The left figure is the sea surface temperature bias figure from the average of the three models run separately, the MPISM, NOISM, and CSM. And the right figure is the bias from the interactive ensemble, so the supermodel that I've shown, just connected by the ocean states, and in particular only through sea surface temperature data. And so you can see there's a dramatic reduction in SST biases over much of the globe. And you can see from hopefully you can see the RMS error here in red. This is the global value, is 0.91, so it is reduced to about 0.6. And so there's also overall a global reduction in RMS error. So we think this is quite promising. Less promising is if we look at the rainfall errors, which was a part of the motivation for this work. So you can see here that On the left is the standard average of the three models, and on the right is the interactive ensemble or the supermodel. And so you can see to some extent there's some reduction in the error, but it's marginal. So you can see in terms of the global RMS error. You can see, for example, in the tropical Atlantic, it looks like the rainfall bias has been reduced, and there's some indications of improvement in the double RTCZ. But still, it's a little bit disappointing that the model still has such large rainfall biases in the tropical Pacific. So another issue in this type of interactive ensemble is the variability. I'd just like to point out that we're able to synchronize the systems, and so we have these three F-system models that are synchronized through the SST data. And you can see here the behavior in the tropical Pacific. And so on the left is just the three models run separately, and you can see NINU 3.4 SST. So the models are not synchronized and they have large variability. On the right, you can see in our supermodel context, now the sea surface temperature of the three models is strongly synchronized, but on the other hand, the variability is strongly reduced. And we know that's because we are essentially removing or reducing the impact of atmospheric noise in the simulations. At least that's what we believe it to be. And
three
yes.
more minutes.
Yeah, so I think I won't show. This is just a figure that shows the standard deviation of sea surface temperature anomalies, and you can see the observed. You can see the ensemble of the unconnected models and of the supermodel. So you can see, as I just pointed out, in the tropical Pacific, that there's a reduction in error, not error. There's a reduction in variability, and so it's actually a similar order of magnitude to the average of the unconnected models. So I'd just like to wrap up now. So what I've tried to, so as I said, it's a bit funny to talk online and at this time of the morning, and time has run a bit fast for me. I didn't have so many slides, but I'd hoped to get a little bit of discussion. So what I've tried to explain is the standard approach that we're developing for reducing model errors and improving prediction. So we're looking at developing high resolution models, and we have a strong focus on the data assimilation, and I presented some results from a method to hybridize the covariance matrix, which I hope should interest many of you. And as an alternative approach to reduce model biases, I've introduced the supermodel approach, in which we can optimally connect a sort of a standard resolution versions of the models to also achieve a reduction in error. And this is able to potentially reduce long-standing errors through compensation of short-term errors during the initial development. And we've developed a supermodel, or we're developing a supermodel based on the Norwegian Earth System model, CSM and NPISM. So thank you for your attention.
Thank you. We have several questions. And first one is from Daniel. Between the standard and high resolution NOR ESM SST result, there is a clear trade-off between bias in the North Atlantic and West African coast. Do you have any idea on this? Why?
Well, I think it's, as I said, we're still in a tuning phase, so we know that there's problems and we haven't had time to resolve all the issues. So it's not a trade-off that we're willing to accept. We understand what the bias reduction is in the tropical Atlantic, but we're not sure about why we have such large biases in the North Atlantic region. We assume it's related to the ocean. Well, we looked at the ocean circulation, so we have an excessively strong ocean circulation, but we don't really understand what's driving these issues. Yeah.
Okay. The next one is from Kyungjaha. Noel, good to see you again. Your hybrid data assimilation method seems practical. However, it has strong regionality. How do you overcome it?
Yeah, this is a challenge. So we'd hope to see, improved results from this method. And so we did a lot. I mean, it's again one of these things. We're in a development phase. So we've done a lot of work in a perfect model context first in the QG model, and we see good results. And now we're starting to work on the real context, and we're starting to see issues there that we hadn't anticipated. So we need to work further to understand what is causing this. We should expect to have benefits everywhere from the hybridization, and So either have equal results or benefits everywhere. And so when we see negative results, we know that the system is not working properly yet.
Okay, thank you. And third one is from Sang-Wook Ye. Do you have any ideas of why the supermodel strategy reduced the ITCG bias?
Yes, so we did quite a lot of work. That refers to the paper from Maolin Chen. So we did quite a lot of work to try to understand the issues, and we found that in this model there were sort of two compensating effects. So there were small differences in the wind fields between these two different atmospheric models. This is because of differences in the atmospheric convection scheme. And those small differences in the wind field were able to control differently the effect of zonal wind-driven upwelling versus upwelling related to the meridional circulation of winds. And through the compensation of these two effects, so through the the shallow tropical cells driven by the meridional winds, we're able to compensate the error, SST development error, development of SST error in the central part of the tropical Pacific. And that was able to reduce this error development, and then leads to this change in the ITCZ pattern. And that we described that in the second paper there from Maolin Chen. It's in 2017 in Chaos.
Okay, the last question is from Junhee Lee. Supermodel has stronger precipitation biases over the Indian Ocean, suggesting larger SST bias. Do you know major causes for the larger bias in the Indian Oceans?
Yeah, unfortunately not. So we've been working very hard in the last few months, and we're challenged again also by computing. Our computing has been a bit unstable. So these are really recent results. So we've had like 8 simulations, 8 different ways to optimize the model, and I've shown you one of them. It has some benefits in some regions and less in other regions, and we still haven't really understood why. I'm sorry we couldn't explain that better.
Okay, thank you again, Noel.
Thank you very much for this opportunity.
Yeah, I think it's perfect time to close the ocean sessions. And thanks again all speakers and audience. Thank you.
Okay, we will move on to the CI session. Where are the speakers? Thomas and Usok, are you there?
Yes, we are. I am, at least.
You are. Usok, are you also available? Well, we'll try to reach you a little bit later. Anyways, Thomas, you're the first speaker. How are things in Bremerhaven?
Excellent, very well, thank you.
Okay, good to see you. Why don't you share your screen and then we can get started?
I'm actually sharing my screen. Perhaps it's just like with Noel, that just takes a couple of seconds.
Now we can see it. Go ahead, Thomas.
Okay, thank you very much. Yeah, and thank you very much for giving me the opportunity to present at this exciting conference, being part of a nice lineup of excellent speakers. I have to say, coming back to Bremerhaven, I was a bit in a dilemma a couple of weeks ago. As some of you may know, today our research icebreaker is coming back from its 1-year-long expedition to the Arctic. And I was asked whether I want to join a small vessel, with lots of politicians and the press on board. And I thought a couple of minutes, but then I gave priority to high-resolution climate modeling. So here I am today.
Very grateful for that.
It's going on somewhere in the harbor of Bremerhaven. Okay. Right. So high-resolution climate modeling in polar regions. That is a bit of an overview of some of the activities in my group that involves Sergei Danilov, Niels Hutter, Nikolai Koldunov, Martin Losch, Thomas Racco, Dimitri Zain, Dmitry Sidorenko, and Qiang Wang, and some others, external collaborators that will be part of the list of authors on the papers I will be mentioning as I go along. And I will be doing 3 bits. I will be briefly saying sort of what we think is unique in terms of our contribution to climate modeling, and then I will be touching on the Antarctic sea ice paradox, and then zoom in on the Arctic and see what high-resolution sea ice models can do in terms of linear kinematic features, in particular leads. And I think that what was Axel interested anyway. So I will spend some time on that, what models, high-resolution models can do in that regard. And when it comes to our contribution, I mean, at least the contribution at RVF from my group, and I think it's fair to say that it is global sea ice ocean models on unstructured meshes that allow multi-resolution experiments, okay? And we developed what probably is one of the first mature sea ice ocean models on unstructured meshes, FESOM, the finite element sea ice ocean model. And more recently, the fast sibling, FESOM2, a finite volume version, which is 3 to 5 times faster than its predecessor, okay? And we have this coupled to an atmosphere, ECHAM and ECMWF, that makes it the climate model. And we also recently included ice sheets and cavities and so forth, moving us also towards Earth system modeling. But I will be focusing here a little bit on the sea ice ocean component and especially sea ice in the latter part of the presentation. And there are two things that are potentially very nice with these kind of methods. That number one is mesh flexibility. Okay, it allows you to generate meshes like this one here, where the resolution basically follows half the Rossby radius of the formation, with some capping in the north, 4 kilometer here, and in the south, 8 kilometer to make things computationally tractable at these resolutions. And so you see how here the resolution increases towards higher latitudes in line with what we think from this Rossby radius of deformation. Okay, there are some further modification here, but I don't have the time to go into this. So this is something in terms of surface node that represents a 1/10 of a degree ocean model, okay, but just redistributed differently. And I should probably say that currently we think 1/4 of a Rossby radius is probably what we need in order to get things right. But I also put in here challenge, you know, because this freedom to generate meshes can also slow you down. Sorry, when it comes to designing meshes, because you always find a place where you can add and change something. That's something one needs to be aware of. The second bit is that these things come with a very nice scalability. So running them with many CPUs on high performance computing system actually generates a nice throughput. And that's shown here on the y-axis, simulated years per day, or something like the equivalent 1/10 of a degree global model. Okay. So simulated years per day, throughput versus the number of cores on 2 high-performance computing systems. Blue, Mistral is a German climate computing center, and Jülich supercomputing center here in orange. And the main point to make is here that you have almost linear scaling all the way to 60,000 cores. So you could say, these kind of systems are close to being exascale ready. You see some leveling off here. I don't have the time to discuss this in detail. That you can find in Koldunov's and Nikolai's paper. It has to do with sea surface height and to a certain degree also with sea ice, so 2-dimensional aspects. You also see that when you include output here, then the performance goes down. Recently, we introduced parallel asynchronous output, which brings the green spot almost onto the blue line. So I think we are now in a situation where I think we have a very nicely scalable system that allows us to do things like this. This is an animation of surface currents here. I think it's a 1/2 degree Rossby radius mesh here, and you see rich dynamics. But I think these kind of animations you have seen before, and so, but again, exciting things here along the west coast of the North and South American continents, where it sort of bends thousands of kilometer longs of eddy, spinning off and, moving westward. Gulf Stream dynamics seem to be there, so very exciting. But I think a very important thing that comes back to scalability is that these things also produce throughput. So these are very nice animations, but if you want to become quantitative in climate research, you need throughput as well. And for these configurations, we are able to run 40 simulated years per day on 18,000 CPUs. So, in a matter of days, you can run through the 21st century with this configuration. And in fact, I think probably, and I come back to this in the discussion perhaps, our biggest remaining challenge at this stage actually is analyzing the wealth of data. Okay, and that's a main challenge here. So does it matter? I would like to show this from some experiments from Thomas Rako, who run this high-resolution model coupled to an atmosphere using the high-res MIP protocol all the way until the end of the 21st century. And then you see here the climate change signal in terms of temperature. Here, left is high resolution, right is low resolution. And you see many known features, the warming hole here in the North Atlantic, Arctic amplification, stronger warming over the continents than over the ocean. But you probably just see many commonalities, but you also see major differences, and especially that's true in the Southern Ocean, you know, where the warming low resolution indicates a warming of something like 3 to 4K, versus this warming is lacking almost altogether in high resolution run. And of course, when we saw this, the first thing that occurred to us was, you know, perhaps this might also explain what some people may call the Antarctic sea ice paradox. So these are results from CMIP6 models. On the right-hand side, in blue, you see the observations, which basically show no trend whatsoever, happy, you know, variability along the same mean state, and the models consistently show a decline. And you can look at almost every single CMIP6 model, and it shows it. So there seems to be something structurally wrong with these systems. Now, if you look at these high resolution runs from Thomas, this is here the low resolution world. So the light curve here is low resolution control. And then here is the scenario run in blue. And you see like all the CMIP6 models, you know, Arctic sea ice declines, which is in contrast to what sea ice observations tell us. Now, if you go to a high resolution version, which, you know, has an Indian Ocean in the Southern Ocean here, then in gray you see the control experiment, and then in black you see the projection. And what you see is some large scale variability, which has to long-term variability, which primarily has to do with the pollinia opening and closing. But what you also see is here clearly that, you know, there is no decline, and actually Antarctic sea ice and these high resolution configurations doesn't actually decline before the mid of the 21st century. Now, I don't have too much time to talk about the drivers of this, but essentially we think it has to do with the difference in the heat transport, the Mediterranean Ocean heat transport, which is shown here in petawatt versus here the latitude. And you see the climate change signal here in green for low resolution, and then black for high resolution, and in gray you see the difference. So basically the high resolution model is more efficient at transporting, you know, some of the heat that's dumped in the ocean, you know, away to the north, and also, which is not shown here, into the depth of the ocean, which we think is contributing to the fact that we see this delayed decline here. Okay. Which brings me to the second point, so switching hemispheres and now going to the Arctic and touching on the topic of high resolution sea ice modeling. And the starting point, how it started, there's currently on social media this how it started and where we are now, so that's my contribution. How it started was when we looked at these simulation, I together with Martin Losch from our colleagues at JPL in Pasadena with the MIT GCM, and you see here sea ice thickness, and you clearly saw in these simulations something that looked like leads. Okay, and we were very much excited about this, and quite a bit of our research followed this. Now that we are sort of progressed a little bit in how we visualize this, and this is an animation from a 1 kilometer simulation, a global simulation with FESOM 2 with a 1 kilometer zoom into the Arctic. And again, you see quite rich dynamics. And I think that's something, you know, Axel sees in his simulations as well, and other groups as well. And it looks very exciting. There's no doubt about this. But the question, there are basically three questions probably. What does it take to get them? How realistic are these features? And then number three, do they matter, okay, in a climate context? And I want to touch on all of those. Now, when it comes to FESOM, we use classical viscous plastic rheology using the EVP formulation, which is used in probably all ocean and climate models, almost all. And it requires subcycling steps, NEVP, within the ocean model time step in order to ensure stability. And in principle, the higher the model resolution, the larger the number of cycles that are needed, okay? Yeah, and if you take EVP and apply it on a high resolution mesh, I think that is here a 4 kilometer mesh with FESOM, then you see the following animation. So same mesh, the only difference being the number of subcycling steps. And this is 50 here, this is 150, and then going all the way to, I can't see it, it's hidden there, I think it's 900 cycles. And what you see is these NEVP matters, okay? You know, at 50, you hardly see any of those features. and it becomes quite rich, the picture, if you go to larger cycles. What you also see is luckily, you see some kind of saturation here around 600 cycles. So a larger NEVP, more LKFs, and EVP can do it apparently, and saturation around NEVP 600. Now, the problem is a little bit, if you do it like this, with these NEVP of 600, your sea ice costs as much as a full ocean, which is slightly unsatisfactory, okay? So the outcome is nice, but what it takes is actually quite expensive. Partly to overcome this, there have been two recent proposals to revise EVP. It's called modified and adaptive EVP, okay? And the idea is to separate, the stability that's sitting with the cycling from the accuracy. I don't have much time to discuss this, but you can find references in Nikolai's paper by Lemieux and Kimritz and others. But if you look at the standard version of EVP that is shown on the left with 150 subcycle steps, and then go to 550 here at almost 5 to 6 times the cost, and then you use this adaptive EVP, then you see that you get away with 100 of these steps and get the level of realism that where you have to pay a high price with the standard EVP system. So, I mean, that's certainly something that sped up high resolution modeling to a degree, that I think we can now make with a reasonable amount of resources, we can carry out quite nice research studies. Which brings me to my last topic, how realistic are these LKFs? Now, I would refer to the work of Niels Sutter and Martin Losch in my group, and they developed a technique based on total deformation here for the Arctic. You see, yellow means areas of high deformation. Could be leads, could be ridges, could be shear. From this, then they developed an automatic scheme, to track leads, okay? And then a lead is here, a single lead is indicated here by colors. And once you have this, you can compute the number, density, length, and so forth. And all this is automatic, there's software around there. There are data there from satellite that you can use to challenge your models if you are interested as well. And to make a long story short, there's a recent paper by Niels and Martin in the cryosphere, where they looked at a 2-kilometer configuration of the MIT GCM, and masked being they look at dark data only where radar sat data or GPS data are available. And there are two configurations. One is the pure MIT GCM at 2 kilometer, and one is with thickness distribution, okay? And which is green. And in principle, what they find is, and that's summarized here in this citation from the paper, that actually the model simulations, if they have these ice class thickness distribution, then actually they do a remarkable job in getting the observations right. So this, for my taste, I mean, I like it, it's great, but it was probably still a little bit on the, something probably it doesn't necessarily convince observational people. So we asked Niels, we had a retreat of my section last week, an online retreat, and I asked him, can we zoom in further and see how these leads look like at the grid scale, okay? And that's what he did, and he picked 2 leads here, number one lead enclosed ice pack, okay? And then a reopening of the lead somewhere here, okay? And you see here the grid boxes. I think it's a 1 kilometer version. And then you see sea ice white. The shadowing basically indicates thickness, and the color indicates concentration. And if it's blue, then you have a high degree of open water, okay? And so if you look into this, that's how these leads look like at the 1 kilometer scale. So in principle, it looks like, what we see in nature. The only thing is, if you ask and talk to an observational person, probably they will argue that more of those, live at smaller scales. But I think in principle, it looks pretty much like what we think they should look like. And even in regions here, that is the reopened one, where you have old leads, you still see that in the ones where your concentration is almost 1, you still have very low sea ice thickness, which is indicative, suggests that, there's a thermal heat conductive heat transport and flux through the ice in those regions as well. So that's fairly new, and that's how they look like, these leads at the kilometer scale. And I think we are just starting to understand, how realistic these things are, what they are doing. So do leads matter? What we know is there's certainly strong interest from the prediction community, the weather prediction community, and we had a paper where we explore the predictability of leads on weather timescales. We know that leads influence sea ice itself. You can see it from some of the plots before. Basically, with leads, we have thicker and more ice, more volume. What we don't know is yet the impact on the atmosphere. And I'm not super optimistic that when it comes to large-scale impacts on lower latitudes, whether there will be an overwhelming impact, given the lectures what we've understood from these PAMIP experiments. And what the impact is on the ocean, we see when there are leads sometimes, long lines of eddies, for thousands of kilometers, but also impact on the biogeochemistry remains to be understood. Which brings me to my summary. So in my view, but I may be biased, sea ice ocean models on unstructured meshes are quite promising tools in climate research. They come with a high degree of mesh flexibility. We can increase resolution, dynamically active region, in ice sheet cavities, can resolve gates and so forth. But building perfect meshes is also a challenge. And then they scale very nice, which gives you good throughput on high performance computing system. My personal view is that analyzing these data has become, certainly in my group, a main challenge. So running them is one thing, and it's challenging, no doubt about this, but making sense of the data is probably at this stage our main bottleneck. High resolution simulations provide a possible explanation for the Antarctic sea ice paradox. Okay, and we hope that this will be published fairly soon, after a surprisingly long time in the review, as I find. Classical sea ice models at ultra high resolution, we think, sort of kilometer scale, show some skill in simulating leads and ridges when it comes to satellite data. The climate relevance of those leads and features probably still needs to be determined. And with this, I close here, and I'm happy to take questions. Thank you.
Thank you so much, Thomas. That was really exciting. When I think about these leads, I think these are wonderful experiments, actually, to understand air-sea interactions, because, icebreakers go through these leads all the time. They measure air-sea fluxes and so on. So they have a wealth of data that could be analyzed, and that could help also understand boundary layer processes in climate models, because now you can really track across a lead given certain wind speed directions and so on, what's happening there in terms of air-sea interactions, in terms of Ekman spirals in the atmosphere and so on. So even if they're not climate relevant, they're fantastic ways of probing parameterizations in the Arctic of atmospheric models. What do you think?
Absolutely, absolutely. I completely agree. And talking about the Mosaic campaign, we have a wealth of data, of confronting these kind of systems with observational data. Having said that, we also have currently a project together with ECMWF where we basically run the high resolution 1 kilometer model with something like it, initially with a 4 kilometer atmosphere, but the idea is also to couple this with 1 kilometer atmosphere. And that's part of the Diamond 2 experiment, but usually is meant to target actually the tropical Atlantic and the tropical Pacific. But we will be having a high resolution 1 kilometer atmosphere coupled to the 1 kilometer ocean, and I think we can start then to see, as you describe, how air-sea interaction actually looks like in these models. So yeah, I agree completely. That's an exciting development.
We have one question from Jeannie Lee. What are major drivers for less warming in the Southern Ocean and Antarctic under global warming in high-resolution model than low-resolution model?
Yeah, it seems to be, normally the Southern Ocean, there's a delicate balance between sort of an overturning that's driven by winds and that, that's compensated by the eddies. And it seems to be, and there's some other literature on that there's some saturation, when it comes to the eddy balancing. And our current hypothesis is that this is probably the main explanation for this. But there seems to be also a story when it comes to the vertical. The low resolution one, brings much more warm water into the deep Southern Ocean. Okay, and that increases stability as well. So that can contribute as well. By the way, that's another issue as well. The water, the hydrography looks quite different. So with the water that can come onto the shelves in Antarctica, that's something that is discussed in the context of sea level rise and ice sheet or ocean interaction, shelf or ocean interaction. That can have a very strong implication here as well, because the water in high resolution is much colder than the one at low resolution. So I think there are some implications for the whole sea level discussion of this as well.
Then on top of this, you will have the melting of Antarctica contributing fresh water, which will further stabilize actually the Southern Ocean stratification and sea ice. So that might be an additional slowdown of Southern Hemisphere warming, or at least Southern Ocean warming there.
Absolutely.
We have quite a bit of time, so I'm just wondering, would you like to say something about your ice sheet modeling activities and how these high-resolution models can contribute to better resolve ice sheet, ice shelf, ocean interactions?
Yeah, that is something that at our institute, especially our paleo people are pushing, but also our physical oceanographers. And in the past, they used basically Phezon, and then you had a very simple way of representing the ice sheets. And I think some of you, probably many of you, know these influential papers that suggest that these coastal current, they can be redirected and warm water put on top of the shelves. Currently there are two streams. Number one is there's coupling with PISM, and that's what our paleo people are doing. And then, sort of more our process people and the physical oceanographers, they're also thinking of bringing together ISSM and Phezon in that regard. But that's work that is ongoing. One has to say, from an ocean perspective, it's also quite challenging to simulate those cavities, especially the transition from the deep ocean onto the shelf, where you have to be very careful when it comes to spurious mixing and so forth. But that's work in progress. But our aim is that in principle, that we would like in the next few years to run cavity-aware climate change projections, and if you will, that would also be tipping point aware climate change projection. That would be our ultimate goal. In terms of the timeline, not 100% sure when we will be able to deliver, but it's a major selling point of our multi-resolution modeling capability, I think. Of course, you can do it with nesting, but it comes naturally with these kind of models.
Coming back to the Arctic Ocean and all these leads cracks that open up, I wonder, are they opening up for the right reasons? We think really what they're supposed to do, given that we use Hilbert type of rheology and so on, or is it a different reason? Is this some kind of numerical issue that seems to show up near the grid scale? Have you further explored this, that we are really looking at the right physics causing these phenomena?
Yeah, probably not to the degree what you have in mind, but we see clearly that these opening events have to do with storms entering the Arctic, and a strong wind forcing there. What we also know, of course, it depends a little bit on where the leads is opening, on previous damage of the ice. So really tracing it back becomes actually quite complicated task. Once you have this ice that has been exposed to storms for months, if not years, and you have seen this in the, some of the leads you have seen in the animation are very old leads, they're legacy leads, and we know that damage, can determine, how, how leads connect. But in principle, I think we are optimistic that that's done for the right reason. But probably the full proof, I have to think about this, would need still probably to be delivered. But I would be quite optimistic that they're doing that correctly, given that there's uncertainty, given previous damages where exactly things form. So the degree to which this is deterministic in a way, I mean, you could imagine they're taking the same forcing and running a trajectory with two models, and you see divergence, not because of the rheology differences, but simply due to the fact that you get small differences that lead to development of different leads there. So,
do you have any sense whether these leads may play a role in the polar amplification?
Well, remains to be seen. I mean, in principle, we know that half of the heat flux from the ocean into the atmosphere, from observational estimates, is coming through leads. Okay. That tells you if you don't have any leads or the ice is too thick, then the only actor is really heat conduction, and that's probably less efficient than heat flux, turbulent heat flux through open water. So I think there's good reason to believe that in winter, at least, if you have leads, that you have an uptake there. Interestingly, we recently studied an opening for an opening of well, but that's probably a slightly different story. The only thing is what I want to say is yes, I think potentially they could. The only thing is with the warming atmosphere, probably the impact of leads is slightly decreasing. We recently studied a Polynya north of Greenland, which opened, I think, in February 2018. And what we found was the heat wave flux, although in a future climate it's much larger, it still produces similar kind of fluxes and also sea ice production, probably because the atmosphere is warmer. Therefore, reducing the fluxes because of the reduced temperature difference. So there's some damping influence of that effect, probably in a warming climate.
Okay, yeah, this leads us also to the next presentation, which will be about polar amplification. Thank you very much. It was great having you today, Thomas. Our next presenter is Dr. Eusok Jong. Are you there, Eusok? Okay, great. Let's see if, can you hear me? We can't hear you yet. Can you please unmute Eusok?
Can you hear me?
Yeah, now it works. And let's do the screen share. Does it work?
There's some problem.
On your side or on our side?
I'm trying to share, but it doesn't.
It does not allow you to share?
Yeah, now it's worked.
Can you turn on the play button on PowerPoint?
Yes. Can you see?
Ah, now it's there. Okay, great, thanks.
Yeah. Thank you, Axel. I'm Eusok Chung. Today I'm going to talk about the physical process driving Arctic amplification and its seasonality. And this ongoing work is conducted together with colleagues at ICCP. And so let me start. As you know, the Arctic has been warming at a much faster rate than the global average. For instance, this figure shows annual mean zonal mean surface air temperature change between two 20-year periods from Japanese VNS dataset JRA55, CSM large ensemble project, and SME5 models. Here for model simulation, a solid line denotes ensemble mean or multimodal mean change, and associated shading representing minimum to maximum range. Although there are some differences, all three indicate that the warming response to the external forcing is greatest in the Arctic. So these rose pictures of amplified warming has been initially linked to the surface albedo feedback associated with sea ice melting, because sea ice covered surface reflects substantial amount of incoming solar radiation. However, the Arctic also exhibits largest intermittent spread in the magnitude of project warming. To find whether this intermittent spread can be explained by internal variability, temperature changes are computed for stronger person case. And comparison with CSM Large Ensemble project suggests that this intermittent spread cannot be explained by internal variability alone, but rather result mainly from the difference in model physics and parameterization scheme among climate models, implying the incomplete understanding of physical process driving Arctic warming implication. An important aspect of Arctic implication is its seasonality. The first three panels shows the geothermal surface temperature change as a function of latitude and season. Here, these panels show that in the Arctic, while warming is muted in the summer, but amplified warming is evident in the cold season, especially late fall. And some might think this cold season peak is induced by the surface albedo feedback. However, as shown in the rightmost panel, due to the lack of incoming solar radiation, surface albedo feedback cannot work, cannot act during the cold season. So it is questionable whether the surface albedo feedback is root cause of Arctic warming amplification. Furthermore, some studies show that in model simulation, Arctic amplification can occur even without surface albedo feedback. For instance, a recent study examined the warming response to CO2 increase in aquaplanet model simulation, in which sea ice is not present. As you can see, for most of the models analyzed in the study, the warming response to CO2 increase is greatest in the polar region, despite the lack of sea ice. And so for these regions, numerous studies have tried to emphasize positive local long-wave feedback processes or enhanced forward energy transport as the main driver. And to determine the main contributor to annual mean Arctic amplification, Pithen and Morrison quantified relative contribution of various processes associated with Arctic warming. In this plot, x-axis denotes contribution of given process to tropical warming, and y-axis corresponding contribution to Arctic warming. So if a given process locates above the 1-ton line, that means that process contributes to Arctic amplification. So according to their analysis, lapse-rate feedback, which is associated with a vertically non-uniform warming in the troposphere, is the main contributor, with surface albedo feedback being identified as a second leading contributor. On the other hand, other processes are found to play minor role or oppose Arctic amplification. And Stoker error confirmed that lapse-rate feedback is the main contributor to annual mean Arctic amplification. However, unlike in Pithen and Morrison, surface albedo feedback is found to play minor role in their study. On the other hand, Lane et al. Argued that the surface albedo feedback is a main contributor. Furthermore, some studies also show that in model simulation, Arctic amplification weakens greatly if there is no sea ice melting, arguing that the related ocean heat release is essential for Arctic amplification. So still substantial uncertainty remain regarding the physical process driving Arctic warming amplification. The key to resolving this inconsistency and contradiction is the enhanced understanding of the law of ocean to atmosphere heat release associated with sea ice melting. Panels on the left-hand side show spatial pattern of sea ice concentration and turbulent heat flux anomaly for January in a given year, simulated from CSM1 high-range model under present-day condition. As you can see, the sea ice melting in the Barents Coral Sea is accompanied by a huge increase in turbulent flux, which is expected to warm and moisten the overlying atmosphere. So following questions emerge. The first question to address is whether sea ice reduction and resulting anomalous sea heat uptake and release is indeed essential for Arctic amplification and seasonality. And related question is whether the cold season maximum of Arctic amplification can be explained by long-wave feedback process alone without ocean to atmosphere heat release. So to answer these questions, we have analyzed Leonard's data set and variety of climate model simulations. In this plot, the first column shows surface air temperature change from JRI 55 for August, October, and December. In August, there is no warming amplification in the Arctic, but in October, amplified warming is found over the Arctic Ocean with marked spatial inhomogeneity. The amplified warming is also found in part of the Arctic Ocean in December. And second column shows corresponding change in sea ice concentration from ocean realized data set. In August, the sea ice region does not show amplified warming, but in October and December, amplified warming is found in sea ice region. So the next cold season warming is closely related to sea ice changes, although the surface albedo feedback cannot be a main driver. And third column shows ocean potential temperature change at a depth around 5 meters. Here, ocean warming also closely related to sea ice changes. And interestingly, in this case, largest oceanic warming occurs summer, so the preceding the warming peak in the atmosphere. And this slide shows similar plot for CSM large ensemble simulation. And these are ensemble mean changes. So they represent the mostly external force response. Although there are some differences in spatial pattern and magnitude, the phase relationships seen in the realized data set were captured by CSM model. And again, both oceanic warming and atmospheric warming are closely related to sea ice changes. And then we examined the particle structure of atmospheric temperature and humidity changes. The top panels on the left-hand side shows the Arctic mean atmospheric temperature change from J55. In the colder season, the amplified warming is confined in boundary layer. In contrast, in summer, largest warming is found mid to upper troposphere. And previous studies attributed this surface intensified warming in the colder season to stably stratified Arctic lower troposphere, which inhibit the mixing of air between the boundary layer and the pre-troposphere. And warming maxima in the mid to upper troposphere have been linked to enhanced port and transport. And humidity change shows similar seasonal contrast in the particle structure. In terms of fractional change, largest moistening is found near the surface in colder season, but in the upper troposphere in summer. And bottom panels shows changes ocean potential temperature. Here, the subsurface water temperature in the upper 50-meter layer attain their maximum in late summer. So the preceding the warming and moistening peak in the Arctic lower troposphere. So this phase relationship seems to imply that ocean to atmosphere heat and moisture release leads to the surface intensified particle structure in conjunction with stable condition in the Arctic lower troposphere. And panels on the right-hand side shows similar plot but for CSM large ensemble simulation. And this ensemble change also shows similar seasonal evolution and particle structure. So to find the primary contributor to enhanced cold season warming, the energy budget composition analysis conducted. From a top of atmosphere perspective, surface air temperature change average over the Arctic can be related to imposed rate forcing and changes in radiant flux due to lapse rate, water vapor, surface albedo, cloud, feedbacks, and also changes in forward energy transport, and also changes in ocean heat storage and transport. Here, ocean heat storage and transport is determined by net downward shoulder wave flux, net downward long wave flux, sensible heat flux, and latent heat flux at the surface. And these feedback variables are defined as positive in the downward direction. And although we do not separate the ocean heat storage component from the ocean heat transport component, and previous study assumed that the changes ocean heat storage in response to greenhouse gas forcing is much greater than corresponding change in ocean heat transport. And meanwhile, radiant flux change at the top of atmosphere might not be directly translated into surface temperature change because the Arctic troposphere is not well mixed. So we also examine the Arctic implication from a surface perspective. And from a surface perspective, the Arctic mean surface warming can be related to changes in net downward shoulder flux, downward long wave rate flux, ocean heat storage transport, and turbulent heat flux. And panels on the left-hand side shows seasonal evolution of Arctic mean ocean heat storage and transport change for CSM large ensemble simulation and SME5. Here, a dashed line denotes ocean heat storage and transport, and red line is the net downward shoulder wave flux, and brown line net downward long wave rate flux, and dark blue line is turbulent heat flux. So comparison of seasonal evolution indicates that the increase in net downward shoulder wave flux during summer is observed in the Arctic Ocean, and then part of the energy is released to the atmosphere in the cold season, mainly in the form of turbulent heat flux in the case of semi-pipe, and in the form of both turbulent heat flux and long-wave radial flux in the case of CSM large ensemble simulation. And panels on the right-hand side show spatial pattern of net downward short wave flux, net downward long-wave radial flux, and turbulent heat flux change for October for CSM and semi-pipe. Here we can see in CI's retreat region, heat is released from the ocean to the atmosphere, mainly in the form of turbulent heat flux. And so the seasonal evolution of Arctic mid warming is related to the flux changes. The top panel on the left-hand side shows Arctic mean surface air temperature change and showing the peak in fall. And in contrast, the change in that downward radial flux at top of atmosphere shows anomalous energy surplus during summer and showing phase inconsistency with surface temperature. And to determine whether this energy surplus might be an artifact, we examined the observations, but because there is no available long-term observation, we just compared 4-year average between ERBI and CIS satellite observations. And this panel shows zonal mean changes. Although there are some potential uncertainties and missing values, especially for ERBI, this zonal mean change shows the anomalous energy surplus during summer. And the spatial pattern further show that this energy surplus occurs mainly in CIS retreat region. And bottom panel on the left-hand side shows the changes in port energy transport. Here, a subset of ensemble members and semi-pipe models show positive values, but ensemble mean and multimodal mean change in negative. So the cold season, it is questionable whether the cold season, enhanced cold season warming can be explained by port energy transport. And top panel on the right-hand side shows changes in ocean heat storage and transport. Here we can see the anomalous ocean heat uptake during summer and followed by heat release during cold season. So this change appears to explain the apparent inconsistency between the radial flux change at top of atmosphere and surface air temperature change. And second panel on the right-hand side shows radial flux change due to left slip feedback. Although left slip feedback has been suggested as a main contributor to annual mean Arctic amplification, its magnitude in the cold season is not greater than the ocean heat storage transport term. And bottom panel shows cloud change. Cloud change contribute to the enhanced cold season warming by reducing outgoing long-wave radiation, but its magnitude is smaller than both ocean heat storage transport term and left slip feedback terms. So from a top of atmosphere perspective, the ocean heat storage transport and left slip feedback are likely to be a primary contributor to any enhanced cold season warming. So their spatial pattern are further examined. The first column shows a spatial pattern of ocean heat storage transport change for August and October and December. In August, the heat is observed in the Arctic Ocean, and then October and December, heat is released from the ocean to the atmosphere, mainly in CIS retreat regions. And this heat release is accompanied by ocean to moisture, atmosphere moisture flux. And second column shows radial flux changes due to left slip feedback. In August, there is no spatial similarity between the left slip feedback and ocean heat storage and transport changes. However, in October and December, a strongly positive value is found in CIS region where substantial amount of heat and moisture is released from the ocean to the atmosphere. So given this spatial similarity, it is unlikely that long-wave feedback processes are independent of ocean to atmosphere heat and moisture release. And this slide shows a multimodal mean change from semi-pipe models from July to November. This slide also shows that in the cold season, long-wave feedback processes are intricately connected to ocean to atmosphere moisture and heat and moisture release. And from a surface perspective, increase in downward long-wave flux is the main contributor to enhanced cold season warming, because in the cold season, the changes in that downward short wave flux is negligible due to the lack of sunshine. And also heat is released from the ocean to the atmosphere, mainly in the form of turbulent flux. So for that reason, the increased downward flux has been suggested as the main contributor to enhanced cold season warming. And the first column shows spatial pattern for August and this October and December. Here, the strongly positive value is combined in CIS region in October and December. And this increase is accompanied by increase over long wave radiative flux as shown in the second column. And the comparison of magnitude indicates that increase in upward long wave radiative flux is greater than increase in downward long wave radiative flux for CS and large ensemble simulation. So it appears that this increase in downward long wave radiative flux is a response to surface warming rather than the other way around. And again, this spatial similarity also implies that even the increase in downward long wave radiative flux is intricately connected to ocean to atmosphere heat and moisture release. And we started to analyze Arctic warming implication depicted CSM1 high resolution models. And panels on the left-hand side shows the time series of Arctic mean surface air temperature change for each month for 4 times CO2 and 2 times CO2 scenario relative to the present day condition. In both cases, largest warming is found around February. In contrast, the warming is muted in summer consistent with low resolution model simulations. And panels on the right-hand side show spatial pattern of surface air temperature change for annual mean, February and June case. And these are the average over the last 20 years of the experiment. In the case of annual mean and February, the warming is distinctly greater over the Arctic Ocean than surrounding land regions. But this land sea contrast disappears in June, or even the warming is greater over the surrounding land regions. And this slide shows corresponding changes in sea surface temperature for January, April, July, and October. These are again the average over the last 20 years of the experiment. Despite huge marked spatial inhomogeneity, the largest oceanic warming occurs in summer, again the preceding the warming peak in the atmosphere. And this slide shows time series of ocean heat storage and transport change for each month. Here we can see the ocean heat uptake take place from spring to mid-summer, and then heat is released from the ocean to the atmosphere mainly during the winter. So this heat release during the winter contribute to the warming peak in February. We assume that ocean heat storage change is much greater than corresponding change in ocean transport change. And to assess the validity of that assumption, we examined potential temperature change at Fram Strait. So the panel in the top left corner shows climatological mean potential temperature for January under present day condition. Here we can see on the left-hand side, cold water outflows through transpolar drift. And on the right-hand side, we can see the warm Atlantic water inflows. And because the Atlantic water is much saltier than Arctic surface water, this Atlantic water is gradually subside over time. And the other panel shows potential temperature anomaly relative to this climatology in the present day condition in year 80, year 90, year 170. And in the subsurface water temperature changes, for most cases, the subsurface water temperature changes is greater in the cold water outflow region than in the warm Atlantic water inflow regions. So this result imply that although the warm Atlantic water inflows contribute to Arctic warming implication, they are likely the major driver. And to further demonstrate the importance of ocean to atmosphere heat release associated with sea ice melting, we analyzed two AMI simulation along with CS large ensemble simulation. In the first AMI experiment, the atmospheric only model is forced by the observed time-varying radiative forcing sea ice concentration SSTs. And second AMI experiment is referred to as clean polar, is same as the control AMI experiment, but with climatological mean sea ice concentration and SSTs over polar regions. So any difference in simulated Arctic climate between two AMI simulations can be attributed mainly to the sea ice and SST variability in the Arctic regions. The panels on the upper left panel shows annual mean zonal mean surface air temperature change between two 10-year periods. Here, in both control AMI and CS and large ensemble simulation show the Arctic amplification. But this Arctic amplification created weakness in the clean polar AMI experiment. And panels on the right-hand side show spatial pattern of annual mean surface air temperature change for control AMIP and clean polar AMIP and CSM Lagrange simulation. In the case of control AMIP and CSM Lagrange simulation, the warming is significantly greater over this Arctic Ocean than in surrounding land regions. But this landscape contrast disappears in clean polar AMI experiment, where the CIS and SSE variability is not accounted. And lower left panel shows seasonal evolution of Arctic mean surface air temperature change. Here again, these both control AMIP and CSM Lagrange will show the warming peak in the fall, but the seasonal contrast disappears in clean polar AMI experiment. And panels on the right-hand side shows measured pattern of surface air temperature change for October. And here we can see clean polar AMI experiment failed to capture the amplified warming in CIS regions. And also we examined the particle structure of atmospheric temperature change. And here, despite substantial difference in experimental design, or the warming is quantitatively comparable in the pre-troposphere among the three experiments. But the clean polar AMI experiment failed to capture the enhanced cold season warming in the cold season. So this discrepancy suggests that the ocean to atmosphere heat release is essential for the surface intensified warming in the cold season in the Arctic. And so this schematic diagram summarizes the presentation. In short, the warm season ocean heat recharge and cold season heat discharge link and integrate warm and cold season feedbacks together. So they effectively explain the cold season Arctic warming implication. So if ocean atmosphere CIS interactions are suppressed or muted, then Arctic implication will weaken greatly. So that's all I have today. Thank you for attention.
Thank you very much, Isak. The previous speaker, Thomas Jung, he talked about the lack of warming in the Southern Ocean, in particular if you go to high resolution ocean models, or reduced warming, of course, relative to the Arctic. So I'm wondering, I mean, he indicated that ocean resolution, maybe eddies and heat transport play a bigger role also in the Southern Hemisphere. But if we just think about the Arctic Ocean, it's a very shallow bathtub. So any heat that we are pumping in will be nicely distributed, and it will be available to melt sea ice in the winter season. However, we have very deep mixed layers in the Southern Ocean. Is that maybe one of the reasons why the Southern Ocean is less efficient in accommodating this feedback that you're talking about, this heat capacitor effect?
Yes, I think so. I agree with your opinion. And also because in the Arctic Ocean, the CIS is more vulnerable to the pulsing from the atmosphere or wind compared to the Southern Hemisphere. So I think so that is one reason.
So if we then look at the IPCC typical precipitation maps, we usually like to focus our eyes on the tropics, but actually where we have the most robust responses in the Arctic Ocean. So we see a strong amplification of precipitation there, which will also, not only in the Arctic region, but also on land. So it looks like the hydrological cycle is intensifying, and as a result also we would expect a stronger halocline and shallower mixed layers. How would this process maybe contribute to the polar amplification? Would it be an accelerator?
Yes, at first, but later maybe the process will slow down because CI is gone, then this effect is more less effective.
Okay, I think there are no more questions from the audience as far as I can see. Then I would like to thank you, Isak, again for your presentation. So it's time to close our first day. We had quite an interesting journey from the atmosphere to the ocean to the freezing cold Arctic regions, polar regions. And I think we got a very good idea today of what high-resolution Earth system models can do and what open questions still remain. We will continue these discussions tomorrow morning, again at 9 o'clock Korean Standard Time. We will resume. Then we will look much more into the regional aspects of future climate change using these high-resolution Earth system models. This will be our first session, and I hope to see you all again tomorrow. Please, again, get engaged and active also on Slido. It's a very simple system to ask questions, and we'll see you tomorrow. Thank you very much, everybody, for joining today.